Beyond the familiar expanse of our blue sky, a vast and mysterious universe unfolds, filled with enigmas that stretch the boundaries of our understanding. From the violent, fiery hearts of stars to the silent, empty expanses between galaxies, space constantly challenges our grasp on reality. It beckons us to dive deeper into the unknown, inviting us to explore the phenomena that not only astound, but often defy the very laws of nature as we know them. In this journey, we embark together on a quest to uncover the secrets of black holes, venture in search of distant alien worlds, and probe the very fabric of time and space itself. Take, for instance, Venus, a planet so close yet so utterly alien. Beneath its dense toxic clouds lies an environment both fascinating and hostile. The atmosphere is almost entirely composed of carbon dioxide, with thick clouds of sulfuric acid creating surface pressures approximately 90 times that of Earth's. These oppressive conditions are compounded by surface temperatures that soar to a staggering 450 degrees Celsius, making Venus the hottest planet in our solar system. The landscape below is a jagged, rocky expanse dotted with towering volcanoes, deep valleys, and vast plains. Geological evidence suggests that Venus is geologically active, and scientists have uncovered signs of ancient lava flows that may have reshaped the planet's surface over time. There are more than 1,000 major volcanoes on Venus, some of which could still be active. This prompts compelling questions about the ongoing volcanic processes and the planet's evolution. One of the most unexpected revelations from space missions, such as the Soviet Union's Venera probes and more recently the European Space Agency's Venus Express, has been the discovery of mountainous regions such as Ishtar Terra and Aphrodite Terra. These highland areas suggest that Venus has undergone substantial geological changes over its history. Exploring the secrets concealed beneath these thick clouds could provide crucial insights not just into Venus's past, but into the broader processes that shape rocky planets in our solar system and beyond. Understanding how Venus' atmosphere interacts with its surface and uncovering any signs of past water can radically alter our perspective on this enigmatic planet. The ongoing pursuit of knowledge about Venus continues to capture the imaginations of scientists and space enthusiasts alike, offering a glimpse into the dynamic forces at play on a neighboring world. The search for life beyond Earth has also turned our attention to the icy moons of Jupiter and Saturn, particularly Europa and Enceladus. These moons harbor hidden oceans beneath thick ice sheets, and the prospect of life, however primitive, existing within them tantalizes scientists and stirs the imaginations of many. Europa, one of Jupiter's largest moons, is thought to conceal a vast liquid ocean beneath its icy crust. This ocean could potentially harbor the conditions necessary for life to exist. Similarly, Enceladus, a moon of Saturn, has provided fascinating evidence of a subsurface salty ocean, particularly through geysers that shoot water vapor and organic molecules into space. The environment beneath these icy surfaces shares striking similarities with some of Earth's most extreme habitats, such as hydrothermal vents, dark, high-pressure regions where life thrives in complete darkness, sustained by heat and chemical energy rather than sunlight. If similar hydrothermal activity and chemical processes are happening on Europa or Enceladus, they could create an environment where life could flourish, despite the cold and darkness. Organic compounds have already been detected in the plumes of Enceladus, and Europa's surface is thought to be enriched with materials that could provide the chemical ingredients necessary for life. The hunt for biosignatures, indicators of past or present life, drives many space missions today. Future missions, such as NASA's Europa Clipper, aim to study Europa's surface and subsurface and subsurface more closely of these alien oceans. While we have yet to discover definitive evidence of life beyond Earth, the conditions on these moons suggest that life, even in its simplest forms, could exist in these distant, hidden oceans. As exploration continues, the answers we uncover may dramatically shift our understanding of life's potential in the universe. Moving farther out in our solar system, Uranus stands as a remarkable ice giant, not only because of its striking blue color, but also due to its peculiar rotational tilt. With an axial tilt of nearly 98 degrees, Uranus essentially rolls along its orbit. This unusual tilt is thought to be the result of a violent past, likely involving a massive collision with another celestial body during its early formation. Such a catastrophic impact could have been powerful enough to knock the planet onto its side, altering its rotational dynamics. This kind of dramatic reorientation may not be unique to Uranus, as similar processes may have shaped other gas giants in the outer solar system. This tilt has fascinating consequences for the planet's seasons. A single day on Uranus lasts about 17 hours, but its seasons can stretch for more than 20 years due to its long orbital period of about 84 Earth years. As a result, one hemisphere of Uranus can experience years of uninterrupted sunlight, while the other is cast into perpetual darkness. Understanding why Uranus rotates on its side not only deepens our understanding of the planet itself, but also provides vital clues about planetary formation and the evolution of our solar system. As we continue to study Uranus and its fellow gas giants, we gain a deeper appreciation of the forces that have shaped our solar system and the vast array of planetary systems in the universe. Perhaps one of the most captivating phenomena in our solar system is Saturn's hexagonal storm at its north pole. This massive six-sided jet stream spans more than 20,000 kilometers across and exhibits remarkable stability. Scientists believe the unusual shape is caused by a combination of atmospheric dynamics and fluid mechanics. At high altitudes, fast-moving air interacts with cooler layers of the atmosphere, creating a wave pattern that forms the six-sided shape. This formation is similar to how a rotating fluid can develop polygonal shapes when subjected to specific velocities and temperatures. The hexagon's stability is remarkable, persisting for decades as observed by the Voyager spacecraft and later the Cassini mission. While the precise mechanisms behind the formation of such a structure remain elusive, scientists are actively studying how these phenomena form and endure in planetary atmospheres. Saturn's rapid rotation and extreme atmospheric conditions make it an ideal laboratory for these unique weather patterns. The hexagonal storm is not only a curiosity in planetary weather, but also provides a broader context for understanding atmospheric physics, both on Saturn and potentially on other planets across the universe. Far beyond the gas giants, the dwarf planet Ceres has revealed fascinating geological features that continue to captivate scientists. In 2014, NASA's Dawn spacecraft captured images of bright spots on Ceres, primarily located within a large crater named Occator. These bright patches are thought to be composed of sodium carbonate, a type of salt that reflects sunlight more efficiently than the surrounding material. The discovery of these bright spots points to a history of geological activity on Ceres, particularly involving briny water. One theory suggests that the bright spots are salt deposits left behind when salty water traveled to the surface and evaporated. Ceres is believed to harbor a subsurface reservoir of water ice, creating the conditions for brine to seep up through fractures in the crust. When the water reaches the surface, it either freezes or evaporates, leaving behind the distinctive bright salt deposits. This process indicates that Ceres is not a completely dormant body, but rather one with ongoing geological activity. The study of these bright spots has unveiled a complex interplay of factors. Alongside sodium carbonate, scientists have identified other minerals like magnesium sulfate, further suggesting the presence of liquid water in Ceres' past. These findings provide valuable insights into the dwarf planet's internal processes and its thermal history, offering clues about its potential for organic chemistry. More broadly, this research contributes to our understanding of other celestial bodies in the asteroid belt and beyond, adding a new layer of depth to our exploration of the solar system. In the end, the cosmos holds countless mysteries, many of which we are only beginning to uncover. As we explore the hidden realms of planets, moons, and distant stars, our understanding of the universe continues to evolve. Each discovery, whether it's the possibility of life on distant moons or the violent past of distant planets, challenges our assumptions about the nature of existence itself. The answers to these questions may be waiting just beyond our reach, and with each new mission, we get one step closer to understanding the vast, intricate web of the cosmos that surrounds us. The discovery of bright spots on distant celestial bodies continues to challenge our preconceived notions of the solar system. These small but fascinating features on objects like Pluto suggest that even the most remote bodies harbor secrets that challenge our understanding of their geological and chemical processes. One such discovery that has captivated scientists is Tombao Regio, the heart-shaped region on Pluto. This remarkable landscape, stretching over 1,600 kilometers, was revealed during the New Horizons mission in 2015, offering an unprecedented view of Pluto's icy terrain. Dominated by a vast, smooth expanse of nitrogen ice, Tombao Regio is a stark reminder that there is still much to learn about the processes shaping the bodies at the outer reaches of our solar system. Tombao Regio, with its striking heart-shaped formation, is more than just a visual marvel. Its smooth surface suggests that it has undergone recent geological processes in the context of Pluto's long history. This challenges the conventional view of Pluto as a frozen, inactive world. Rather, Tombao Regio seems to be a region of geological activity, pointing to a dynamic and evolving planetary body. The presence of ridges and possible cryovolcanoes, ice volcanoes that erupt slushy mixtures rather than molten rock, further supports the idea that Pluto's interior is not as cold and dormant as once thought. These features hint at the possibility of a subsurface ocean or vast reservoirs of liquid-like materials beneath the frozen surface. Perhaps the most intriguing aspect of Tombao Regio is Sputnik Planitia, the left lobe of Pluto's iconic heart. This vast plain, primarily composed of nitrogen ice, is characterized by polygonal patterns that suggest convection processes. These patterns are a clear indicator of active material movement beneath the surface, driven by heat and pressure. Such evidence reinforces the idea that Pluto's surface is not a rigid shell, but one that is shaped by dynamic interactions between its internal heat, volatile substances, and the cold, distant environment it resides in. Exploring Tombao Regio has not only expanded our knowledge of Pluto, but also broadened our understanding of other icy bodies in the Kuiper Belt and beyond. The New Horizons mission continues to unveil astonishing insights into the complex geological processes at play on these distant worlds, offering a remarkable glimpse into the dynamics and evolution of a planetary body that was once considered little more than a frozen rock in space. As exploration of the outer solar system continues, Pluto's mysteries serve as a compelling invitation for scientists to delve deeper into the unknown. Moving closer to the inner reaches of our solar system, Mercury presents its own set of surprising features that defy expectations. One of the most striking characteristics of Mercury is its exceptionally large core, which makes up a significant portion of the planet's total volume. Approximately 70% of Mercury's radius is composed of this metallic core, while the surrounding silicate mantle and crust are relatively thin. This unusual internal structure has intrigued scientists for decades, prompting them to ask why Mercury's core is so disproportionately large. One prevailing theory posits that Mercury's large core is a result of catastrophic collisions during the planet's early history. As the solar system formed, planetary bodies underwent frequent and violent impacts, which caused much of their original material to be stripped away. Being the closest planet to the Sun, Mercury likely experienced more frequent and intense collisions, which may have caused it to lose much of its mantle. The result is a planet with an unusually large core compared to its overall size. Another factor to consider is Mercury's proximity to the Sun. The intense heat from the Sun may have influenced the composition of the planet, causing a greater retention of heavier elements like iron in the core. This would explain the dense metallic core, and, in turn, the planet's unusual internal structure. The idea that Mercury accreted from a mixture rich in metallic content fits with the current understanding of the planet's composition. Recent data from NASA's Messenger spacecraft supports this theory, showing that Mercury's large core plays a crucial role in its magnetic field. Though weak, the magnetic field suggests that Mercury has a partially liquid outer core capable of generating a dynamo effect, which further emphasizes the importance of its surprising internal structure. The study of Mercury's core provides valuable insights into the processes that govern planetary formation, offering a better understanding of not only Mercury itself, but also the broader dynamics of terrestrial planets in our solar system. But Mercury's mysteries don't stop at its core. The planet experiences some of the most extreme temperature variations in the entire solar system, with temperatures fluctuating wildly between day and night. Due to the planet's lack of a significant atmosphere and its slow rotation, these temperature swings are far more dramatic than those experienced on Earth or other planets. Mercury's atmosphere is composed mostly of oxygen, sodium, hydrogen, helium, and potassium, but it is incredibly thin, unable to trap heat effectively. This leads to rapid temperature loss once the sun sets. Mercury's slow rotation exacerbates the temperature extremes. With an axial rotation period of about 58 Earth days, a single day on Mercury lasts longer than an entire year, which lasts approximately 88 Earth days. During the day, surface temperatures soar to around 420 degrees Celsius as the sun's harsh rays relentlessly bake the planet. However, as night falls, temperatures can plummet to a bone-chilling -170 degrees Celsius, exposing just how extreme the temperature fluctuations can be. This dramatic contrast between scorching heat and freezing cold highlights Mercury's unique position in the solar system, where its proximity to the sun and its lack of atmospheric protection create one of the most inhospitable environments imaginable. Both Pluto and Mercury, though vastly different in many respects, challenge our assumptions about planetary bodies in the solar system. Pluto's dynamic geology and Mercury's bizarre internal structure serve as stark reminders that even the smallest and most distant objects in our solar neighborhood can harbor complex histories, geological processes, and mysteries that continue to intrigue and inspire further exploration. As we continue to probe these worlds, we gain not only new knowledge about the outer and inner reaches of our solar system, but also about the very processes that shape the evolution of planets and their environments. Mercury's surface composition plays a crucial role in its dramatic temperature swings. The planet's terrain is a harsh combination of rocky and metallic surfaces with an exceptionally low heat capacity. This means it heats up quickly when exposed to the sun's relentless rays. However, this same property works against it when the sun sets. Without much to retain the heat, Mercury rapidly loses warmth, plunging its surface into the freezing cold of night. The absence of moderating features like oceans or vast land masses, structures capable of stabilizing temperature, further exacerbates these extreme fluctuations. These rapid temperature changes present an additional challenge for any would-be explorers, emphasizing Mercury's unusual place among the terrestrial planets. Investigating these temperature swings not only sheds light on Mercury's volatile climate, but also provides valuable insights into similar conditions that could exist on other rocky bodies scattered throughout our solar system. Shifting attention to Neptune's largest moon, Triton, one encounters a world that is equally puzzling and intriguing. Triton is distinctive not just because of its peculiar physical features, but also because of its unusual retrograde orbit. Unlike most moons, which orbit in the same direction as their parent planet's rotation, Triton moves in the opposite direction. This odd orbital behavior points to a turbulent past, setting it apart from other moons in the solar system. The leading theory suggests that Triton didn't form alongside Neptune, but was captured by the planet's gravitational pull in the early days of the solar system. In those ancient times, many objects wandered the outskirts of the solar system, and Triton was likely a much larger Kuiper Belt object, possibly comparable in size to Pluto. As Triton ventured too close to Neptune, the planet's immense gravity snagged it, pulling it into orbit. This capture process, which disturbs the object's trajectory, often results in a retrograde orbit, a direct consequence of the gravitational dynamics at play. Furthermore, the process likely involved interactions with other celestial bodies or Neptune itself, causing significant alterations in Triton's speed and trajectory. The end result is that Triton now orbits Neptune in the opposite direction of the planet's rotation, an extremely rare occurrence among large moons. The implications of Triton's retrograde orbit are far-reaching. Not only does it provide clues about the moon's tumultuous past, but it also signals a potentially dramatic future. Due to tidal forces exerted by Neptune, Triton is gradually spiraling inward, moving ever closer to the planet. This inward journey will eventually lead to one of two possible outcomes. Triton will either collide with Neptune or break apart, forming a spectacular ring system around the planet. The potential for such an event makes Triton an object of great interest, as studying this moon helps astronomers understand the intricacies of celestial mechanics and the violent histories that shape many of the solar system's moons. Beneath the tempestuous clouds of Jupiter's Great Red Spot lies an enigmatic and complex system that continues to captivate scientists. This massive storm, which has been raging for at least 350 years, is a cyclonic vortex of immense proportions, spanning an astonishing 16,000 kilometers. While the storm's swirling clouds are visible to the naked eye, much of its inner workings remain a mystery. The Great Red Spot resides within Jupiter's thick atmosphere, composed mostly of hydrogen and helium, though ammonia, methane, and water vapor are also present. The winds on the outer edges of the storm can reach speeds up to 450 kilometers per hour, a force that drives its surface dynamics. However, the story becomes even more fascinating as we dive deeper into the storm's layers. As we descend beneath the visible clouds, atmospheric pressure and temperature rise significantly, and the storm's behavior changes dramatically. Recent research has uncovered a crucial link between the storm's surface dynamics and the deeper layers of Jupiter's atmosphere. The Great Red Spot may extend far below the cloud tops, plunging into depths where temperatures and pressures are extreme. These conditions could give rise to unique energy and fluid dynamics that remain poorly understood, but are critical to the storm's persistence. It is also hypothesized that deeper systems of circulation below the storm might help sustain its longevity. While the outer layers of the storm continuously feed off the surrounding atmosphere, the underlying fluid motion may be supplying the energy needed to keep it alive. This suggests that the Great Red Spot is far more than just a surface phenomenon. It's likely connected to deeper, more complex storm systems within Jupiter's atmosphere. As research continues, scientists may uncover even more secrets about this colossal storm, offering a glimpse into the turbulent processes that govern Jupiter's chaotic weather. On a different front, the concept of life on a tidally locked planet presents an intriguing scenario for astrobiologists. A tidally locked planet is one that has one side constantly facing its star, while the other side remains in eternal darkness. This unique positioning creates extreme environmental conditions that could have profound effects on the evolution of life forms. The illuminated side would likely experience intense heat from constant sunlight, potentially creating desert-like conditions where water may be scarce and temperatures could soar to extreme levels. Conversely, the dark side of the planet would be locked in perpetual cold, with freezing temperatures that could pose significant challenges to life. The stark contrasts between the two sides would likely foster unique adaptations among any potential life forms, driving evolutionary processes in ways that are hard to predict. The study of such planets is not just theoretical, it provides valuable insights into the possibilities of life in extreme environments, both within our solar system and beyond. However, the presence of liquid water on a tidally locked planet could serve as a pivotal factor in determining the potential for life. If conditions allow for the existence of oceans, it's possible that life forms could arise with highly specialized adaptations to cope with extreme environmental factors, such as intense heat and high radiation levels. These organisms might evolve to develop reflective surfaces or even complex biochemical mechanisms to counteract the harsh sunlight they would constantly be exposed to. These traits would resemble some of the extremophiles found on Earth, such as desert plants that thrive under brutal conditions, or the resilient organisms living around hydrothermal vents deep in the ocean. In this environment, life could potentially find a way to thrive, despite the unrelenting solar radiation. On the other side of the planet, the dark side, life would face an entirely different set of challenges. This region would experience freezing temperatures and total darkness, offering a stark contrast to the perpetual daylight on the planet's sunlit side. Yet, life here might adapt in ways that we can only imagine. One possibility is that life forms could evolve in subterranean environments, where they would rely on geothermal energy or chemical reactions for sustenance, much like some extremophiles here on Earth. These organisms might develop features to help them survive in the perpetual darkness, perhaps evolving enhanced sensory perceptions to navigate without light. This could lead to a species that communicates and interacts using touch, chemical signals, or even vibrations, similar to some cave-dwelling species on Earth that rely on non-visual methods to find their way and survive. The region along the Terminator, the boundary between the day and night sides, could be the most habitable zone on a tidally locked planet. In this zone, temperatures would be more moderate, creating conditions potentially suitable for life. Here, you could find a blending of ecosystems that incorporate species from both the sunlit and dark sides. Photosynthetic organisms might flourish in the shifting light, while also evolving ways to survive the dynamic range of light conditions. This unique blend of species could represent the most diverse and resilient ecosystems found on the planet, a fusion of life from the harsh extremes of constant daylight and eternal darkness. Life on a tidally locked planet would undoubtedly be diverse and specialized, shaped by the distinctive and extreme environments it exists within. The constant exposure to sunlight on one side of the planet and the eternal darkness on the other would impose profound evolutionary pressures, leading to the development of life forms with unique traits and adaptations. Studying how life could potentially adapt in such radically different conditions expands our appreciation for the potential for life beyond Earth. It may even guide future explorations of exoplanets that lie within habitable zones, shedding light on the possibilities of extraterrestrial life. The quest for Earth-like planets has become one of the most exciting frontiers of scientific discovery, especially with the advancements in telescope technology and space missions. Recent data, notably from the Kepler Space Telescope, suggests that Earth-sized, potentially habitable planets could be more common than we once thought. Estimates indicate that billions of such planets may exist within our galaxy alone, many of them orbiting stars that lie within the habitable zone. This is the region around a star where temperatures are ideal for liquid water to exist on a planet's surface. Depending on the size and brightness of the star, this zone could vary widely, offering a range of potential Earth-like environments. Research suggests that 20 to 40% of Sun-like stars could host Earth-sized planets within their habitable zones. This statistic indicates that our galaxy, the Milky Way, could be home to countless worlds that share similarities with our own. In addition to these discoveries in the Milky Way, the growing list of exoplanets discovered in other galaxies provides further evidence that Earth-like planets are not just a rarity, but a common feature throughout the universe. As the number of exoplanets cataloged continues to increase, scientists are uncovering planetary systems of great diversity, planets of varying compositions, sizes, and atmospheric characteristics. Some of these exoplanets bear striking similarities to Earth, prompting researchers to probe deeper into their potential for habitability. While the existence of Earth-like planets appears to be common, determining the likelihood of life arising on these planets is an immensely complex issue and remains a subject of active study. Factors such as the presence of liquid water, a stable climate, and protective atmospheres all play a critical role in the potential for life to develop. As technology advances and space missions continue, our understanding of how planets form and how common Earth-like worlds are will deepen, keeping the search for extraterrestrial life vivid and compelling. One particularly fascinating class of exoplanets that have emerged from our discoveries are the hot Jupiters. These gas giants orbit very close to their parent stars, subjecting them to extreme temperatures and atmospheric conditions. Take, for example, WASP 121b, a hot Jupiter with surface temperatures exceeding 2D 500 degrees Celsius. The intense heat creates bizarre and dramatic atmospheric phenomena, including gases such as iron and titanium existing in vapor form. Another example is HD 973b, which also falls into the hot Jupiter category. This planet experiences supersonic winds that can reach speeds over 2,000 kilometers per hour, while its atmosphere contains clouds of glass which rain sideways due to the extreme weather conditions. These extreme exoplanets challenge our understanding of planetary formation and environmental conditions, pushing the boundaries of what we consider to be habitable. Shifting to the opposite end of the spectrum, we find planets like GJ 1214b, a sub-Neptune with a thick atmosphere rich in water vapor. This exoplanet orbits a red dwarf star and is intriguing because its atmosphere hints at the possibility of a water-rich world. Such conditions could potentially support life, making GJ1214b an exciting subject of study. Then there is the curious case of LHS 3844b, a rocky exoplanet that is believed to orbit its star so closely that its surface might be molten, leading to a hostile, uninhabitable environment. With a permanent day side and an equally harsh night side, this planet provides yet another example of the extreme conditions found on distant worlds. The discovery of these unusual exoplanets pushes the boundaries of our knowledge about what constitutes a habitable planet. As we explore worlds that are wildly different from Earth, we are forced to reconsider our assumptions about planetary habitability, expanding our perspective on what might be possible beyond our own solar system. One of the more captivating ideas gaining traction in the scientific community is the concept of diamond planets. These worlds, primarily composed of carbon, could form under extreme conditions of high pressure and temperature, where carbon crystallizes into diamond structures. Such conditions might occur on planets rich in graphite or other carbon-based minerals. One of the most promising candidates for a diamond planet is 55 Cancri e, a super-Earth about 40 light-years away. This planet is thought to have a carbon-rich composition, and its extreme surface temperatures of over 1,000 degrees Celsius might create the conditions necessary for diamond structures to form. While direct evidence is still lacking, the idea of diamond planets is a fascinating concept that challenges our understanding of planetary formation and the variety of worlds that could exist beyond our own. In addition to diamond planets, super-Earths are another class of exoplanets that could offer an intriguing glimpse into the future of planetary exploration. Super-Earths are planets with a mass greater than Earth's, but smaller than that of Neptune or Uranus. These planets tend to be rocky, much like Earth, but with a much higher gravitational pull. The stronger gravity would result in everyday objects, including humans, weighing more than they do on Earth. Activities such as walking or running would feel markedly different, potentially requiring more strength and endurance. The atmosphere of a super-Earth could vary significantly, depending on the planet's proximity to its star and its other characteristics. Some super-Earths may have dense atmospheres, rich in gases like carbon dioxide or methane, which could lead to extreme weather conditions. If located within the habitable zone of its star, a super-Earth could have conditions just right for liquid water to exist, which is essential for life as we know it. The unique environmental factors of super-Earths could lead to diverse ecosystems and life forms that are radically different from those on Earth. For example, the stronger gravity may lead to shorter, stockier plants and animals, evolved to maintain balance in a world of increased gravitational force. These features would offer a fascinating look into how life could adapt on a super-Earth, providing a rich field for future exploration. Imagine a world far beyond our own, a super-Earth where vast stretches of land create expansive ecosystems, offering the perfect environment for life to flourish. The sheer size of these land masses would support a rich diversity of habitats, teeming with unique species, each adapted to the complex conditions of this extraordinary planet. The sky above would be a canvas of unimaginable beauty, as the night reveals not just one, but possibly several stars, each casting a different hue across the firmament. The constellations would be unrecognizable, shaped by the unique motions and patterns of these distant suns, and the colors, rich and vibrant, would take on new dimensions, showcasing a celestial spectacle like no other. On such a planet, sunsets and sunrises would be unlike anything we've experienced. The thick atmosphere would intensify the sun's light, creating vivid, almost surreal colors as the day shifts into night. These breathtaking vistas would ignite curiosity, inviting us to ponder life beyond our own planet and the limitless potential that the universe holds. In this realm, challenges would naturally arise, as the harsh conditions and unpredictable weather patterns demand innovation and resilience. Yet, these difficulties would also open doors to new discoveries, offering profound insights into the nature of life and the forces that shape planets. A super-Earth is not just a theoretical concept. It's an invitation to imagine how life could adapt and thrive in ways we have never before considered. Hot Jupiters, a unique class of exoplanets, add yet another fascinating chapter to the cosmic story. These massive gas giants, often much larger than Jupiter itself, orbit their stars at dangerously close distances, sometimes even closer than Mercury orbits our Sun. The formation of these planets is a result of a delicate interplay of gravitational forces, gas dynamics, and the evolution of the protoplanetary disk, the swirling cloud of gas and dust that surrounds a young star. Initially, these planets likely form farther out in their systems, where cooler temperatures and abundant icy materials allow them to grow to massive sizes. But as these planets mature, their gravitational pull begins to influence the surrounding material, pulling in more gas and dust. Through a series of complex interactions with other massive bodies, these planets may begin to migrate inward, slowly spiraling closer to their star. It's a bit like a cosmic game of pinball, where the movement of other celestial bodies can send a planet on an entirely new path. The dissipation of the protoplanetary disk over time only accelerates this process, allowing the gas giant to move closer to the star, sometimes in a dramatic and rapid manner. Once these hot Jupiters settle into their tight orbits, the intense heat they experience causes extreme atmospheric changes. Lighter elements are stripped away while powerful weather systems take shape. Some of these planets even exhibit unique phenomena, such as atmospheric tides, where the very atmosphere itself shifts and moves in response to the planet's close proximity to its star. These extreme environments raise important questions about the possibility of life elsewhere in the universe and challenge our traditional understanding of planetary formation. Similarly, rogue planets, celestial bodies that drift through the galaxy without being bound to any star, offer a completely different but equally captivating story. These planets, which could have formed in a similar way to regular planets, are ejected from their original systems due to gravitational interactions or violent collisions. Estimates suggest that billions of rogue planets roam the Milky Way, making them a hidden but significant part of the cosmos. Without the warmth and light of a star, rogue planets face numerous challenges, not the least of which is their inability to support life as we know it. However, these planets are not entirely lifeless. Many retain internal heat from their formation, which could create pockets of warmth beneath their frozen surfaces, potentially allowing them to maintain an atmosphere. In some cases, rogue planets might even harbor atmospheres rich in hydrogen or other gases, which could stabilize over time. Despite the vast coldness of deep space, the possibility of life on rogue planets has sparked considerable interest. If conditions are right, these planets might have subsurface oceans or even geothermal activity, similar to the volcanic heat found on moons like Europa and Enceladus in our own solar system. These environments could provide the necessary conditions for microbial life to exist, albeit in complete darkness, far from the warmth of a star. Rogue planets also challenge our understanding of planetary formation and evolution. Their very existence forces us to reconsider how celestial bodies interact and evolve. Each new discovery of a rogue planet broadens our view of what is possible in the universe, showing us that planetary systems can be far more diverse than we ever imagined. As technology advances, so does our ability to detect and study these enigmatic wanderers. Every new finding brings us closer to uncovering the secrets of these free-floating planets, expanding our knowledge of the universe and the processes that govern it. The concept of habitable moons orbiting gas giants in distant solar systems has captivated scientists and astrobiologists for years. These moons, often referred to as exomoons, could harbor the conditions necessary for life, especially if they lie within the habitable zone of their parent gas giant. This zone is a region where temperatures are just right for liquid water to exist, an essential ingredient for life as we know it. Tidal forces created by the gravitational interactions between a gas giant and its moons could also play a crucial role. These forces could help maintain subsurface oceans in a liquid state, even if the surface of the moon is frozen. Moons like Europa and Enceladus, which orbit Jupiter and Saturn respectively, provide evidence of this possibility, as both are thought to have vast oceans hidden beneath their icy exteriors. In addition to liquid water, the atmosphere of a moon plays a critical role in its habitability. A stable atmosphere can help regulate temperatures and protect potential life from harmful cosmic radiation. If the right balance of elements, carbon, nitrogen, and hydrogen exists, it's possible that complex ecosystems could develop even in the harshest of environments. The idea of life existing on moons orbiting gas giants is a tantalizing possibility. If conditions are right, these moons could serve as hidden sanctuaries, teeming with life in environments that we are only beginning to understand. Each new discovery about these moons brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? As we continue to explore the vastness of space, the potential for discovery seems boundless. Whether on distant super-Earths, rogue planets, or the moons of gas giants, the universe is filled with extraordinary possibilities waiting to be uncovered. And with every breakthrough, we edge closer to understanding the diverse and often surprising ways in which life might exist beyond our planet. The search for habitable exomoon systems presents unique challenges, especially when it comes to detecting moons orbiting distant gas giants. These moons are incredibly difficult to observe directly, largely due to their small size relative to their host planets and the limitations of our current observational technologies. As these technologies continue to evolve and improve, scientists are delving deeper into the mysteries of exomoons, theorizing about the potential for life beyond Earth. The concept of habitable moons expands the possibilities of where life could exist in the universe, suggesting that the potential pathways for life are far more diverse and complex than we ever imagined. For a planet orbiting a binary star system, the sky would present an awe-inspiring spectacle, constantly shifting and changing. In a binary star system, two stars orbit a common center of mass. Depending on their relative positions, a planet could experience dramatically different lighting conditions throughout its orbit. The most immediate impact of this dual star setup would be variations in light intensity and color, as the stars would likely differ significantly in size, brightness, and even the color spectrum of their emitted light. During the day, if both stars are visible in the sky, a planet would be illuminated by their combined light, creating a unique and surreal daylight experience. Sunrises and sunsets would become vibrant displays of red, orange, and purple hues, as the light from the two stars blends together in fascinating ways. If one star is much brighter than the other, it could dominate the sky, while the dimmer star would remain a subtle but beautiful complement. When one of the stars sets, the remaining star would cast longer shadows, and the planet's temperature would fluctuate, influencing the local climate and weather patterns. These changing light conditions would also create an interesting rhythm to the day, with varying durations of daylight and twilight, depending on the orientation of the planet's orbit and axial tilt. One particularly captivating effect would be during eclipses, when one star passes in front of the other. The sky would shift dramatically, plunging the environment into a temporary, otherworldly darkness that casts a unique and ethereal light over the landscape. If the binary stars were of different types, such as a red dwarf paired with a larger blue giant, the contrast in color would be especially striking. The scattering of light in the atmosphere could enhance this effect, producing skies painted with a dynamic range of colors throughout the day. For the inhabitants of such a world, the changing sky would not just be an environmental feature, it would also play a central role in cultural life. The constantly shifting celestial display could inspire a rich tapestry of myths, rituals, and meanings, deeply intertwined with the stars that shine in their sky. Detecting exoplanets that are too far away to see directly involves a variety of sophisticated, indirect observation methods. One of the most widely used techniques is the transit method, which observes the brightness of a star over time. When a planet passes in front of its host star, from our viewpoint, it blocks a small fraction of the star's light, causing a temporary dip in brightness. By measuring the size and duration of these dips, scientists can infer key characteristics of the planet, such as its size, orbital period, and distance from its star. Another key method for detecting distant exoplanets is known as radial velocity, or the Doppler method. As a planet orbits its star, it exerts a gravitational pull on the star, causing the star to wobble slightly around a common center of mass. This wobble affects the star's light spectrum, shifting its wavelengths due to the Doppler effect. By carefully analyzing these shifts, astronomers can detect the presence of a planet, its mass, and its orbit, even if the planet itself remains invisible. Gravitational microlensing is yet another innovative technique used to detect exoplanets. This phenomenon occurs when the gravitational field of a star and its orbiting planets temporarily magnifies the light from a more distant star. If an exoplanet crosses the line of sight between the distant star and the observer, the resulting light curve will reveal distinct patterns that point to the presence of the planet. This method is particularly useful for detecting planets that are too faint to observe directly or that may lie outside of the habitable zone. Finally, direct imaging can occasionally be used to capture the light of exoplanets, though this is generally reserved for larger gas giant planets located far from their host stars. Advanced telescope technologies such as coronagraphs or starshades can block out the light from the host star, allowing astronomers to observe the much dimmer light reflected from the planet itself. As detection methods continue to improve, our understanding of exoplanetary systems will expand, revealing more about the incredible diversity of worlds beyond our solar system. The event horizon of a black hole remains one of the most captivating and mysterious features in the realm of astrophysics. This boundary represents the point of no return. Once an object crosses the event horizon, it is unable to escape the black hole's gravitational pull, regardless of its velocity. However, the event horizon is not a tangible surface. It is a mathematical concept that marks the threshold where the escape velocity exceeds the speed of light. Consequently, anything that crosses this boundary is drawn inward inescapably, no matter how fast it may be moving. As an object approaches the event horizon, it experiences a range of fascinating phenomena due to the extreme gravitational forces at play. One of the most dramatic effects is gravitational time dilation, which causes time to appear to slow down for an observer at a distance. To an outside observer, a clock falling into the black hole would seem to tick more slowly as it approaches the event horizon, making it appear as if the object takes an infinite amount of time to cross the threshold. However, for the object itself, crossing the event horizon would occur in finite time, with no noticeable delay. Another unique phenomenon near the event horizon is spaghettification. This term refers to the intense tidal forces experienced by an object due to the differing gravitational pull exerted on various parts of it. For example, if an astronaut were to fall feet first into a black hole, the gravitational force on their feet would be far stronger than at their head. This would stretch the astronaut's body into a long, thin shape, resembling spaghetti, before ultimately tearing them apart. Once an object crosses the event horizon, all information about it is effectively lost to the outside universe. This raises one of the most debated questions in theoretical physics, the information paradox. According to quantum mechanics, information should never be lost, but the fate of matter inside a black hole remains unclear. This paradox challenges our understanding of both gravity and quantum theory, suggesting that our grasp of the nature of black holes and the information they contain is still far from complete. Supermassive black holes, which can have masses ranging from millions to billions of times that of our Sun, reside at the centers of nearly all large galaxies, including our own Milky Way. The process by which these immense black holes form is complex and likely involves several stages. The formation of supermassive black holes likely began shortly after the Big Bang, when small black holes formed from the collapse of massive stars in the early universe. These intermediate black holes, which often have dozens of times the mass of the Sun, gradually populated the universe, merging with one another to form increasingly larger black holes. Over time, the gravitational attraction and the accumulation of mass through processes like accretion helped these black holes grow. As they accumulated more mass, their gravitational influence grew stronger, causing them to attract even more material. This process of growth is particularly accelerated in the dense environments of galactic centers, where gas and dust are funneled toward the black hole, fueling its expansion. Another possible mechanism for the formation of supermassive black holes involves the collapse of massive gas clouds, When these clouds condense under the force of gravity, they can directly form black holes of enormous size without going through the intermediate stages. This direct formation could lead to the creation of supermassive black holes very early in the universe's history, helping to establish them in the centers of galaxies during their formation. The interaction between supermassive black holes and their host galaxies is equally significant, as the feedback from these black holes, through energetic winds and jets, can influence star formation and the movement of gas within the galaxy. This process shapes the evolution of the galaxy, with observations suggesting that when galaxies merge, their central black holes often combine to form the even larger black holes seen today. The formation of supermassive black holes represents one of the most captivating and intricate narratives in the universe, blending the processes of star formation, gravitational dynamics, and cosmic evolution. These extraordinary entities play a pivotal role in shaping the very structure of the cosmos. Their existence challenges our understanding of gravity, time, and space itself, standing as colossal anchors at the center of galaxies and shaping their behaviors. It is through these cosmic giants that we begin to grasp the profound mysteries of the universe. In 1974, renowned physicist Stephen Hawking proposed a groundbreaking theory about black holes, known as Hawking radiation. This theory suggested a process through which black holes could gradually lose mass and energy, a concept that stirred the foundations of theoretical physics. Hawking's hypothesis emerged from the strange and paradoxical world of quantum mechanics. According to quantum theory, empty space is never truly empty. Rather, it is filled with fluctuations that give rise to virtual particles and antiparticles that flicker in and out of existence. These ephemeral particles exist only for brief moments before annihilating each other, disappearing without leaving a trace. However, when these particle pairs form near the event horizon of a black hole, the boundary beyond which nothing can escape, their fate takes a dramatic turn. In certain circumstances, one particle may fall into the black hole while the other escapes into the vastness of space. This escaping particle is what we now refer to as Hawking radiation. Intriguingly, the particle that is drawn into the black hole carries negative energy, which means that the black hole effectively loses a small amount of its mass in the process. Although this loss is minuscule compared to the immense size of a supermassive black hole, the gradual shedding of mass over time adds up. For the most massive black holes, the process of losing mass through Hawking radiation is incredibly slow, taking billions of years to result in any noticeable change. However, for smaller black holes, such as primordial black holes thought to have formed in the early universe, the evaporation process could occur on much shorter timescales. In theory, these smaller black holes could eventually disappear entirely, leaving behind no trace of their once formidable presence. This evaporation concept introduces profound implications for our understanding of black hole physics, particularly in terms of how black holes evolve and what their ultimate fate might be. One of the most intriguing consequences of this process is the so-called information paradox, a dilemma that has puzzled physicists for decades. If black holes can evaporate, what happens to the information about the matter that once fell into them? According to the principles of quantum mechanics, information cannot be destroyed, but black holes appear to violate this rule. As information is drawn into a black hole, it seems to be lost forever, raising profound questions about the nature of reality and the limits of human understanding. This paradox has sparked intense debates and research within the realms of theoretical physics as scientists seek a deeper reconciliation between the frameworks of quantum mechanics and general relativity. Despite these mysteries, Hawking radiation has altered the way we perceive black holes. Once thought to be immutable and permanent objects, black holes are now understood to be dynamic, evolving entities that eventually fade away. This discovery provides fresh insights into the fundamental nature of the universe and continues to inspire exploration into the deep, hidden workings of the cosmos. Equally captivating are the theoretical entities known as white holes. In some ways, they represent the antithesis of black holes, and their existence stems from the same equations of general relativity that describe the formation of black holes. While black holes are regions of space where matter and light are drawn inward, never to escape white holes are theorized to expel matter and energy, preventing anything from entering them. In essence, where black holes trap anything that crosses their event horizon, white holes would do the opposite, ejecting particles and radiation outward. White holes emerge from solutions to Einstein's field equations, particularly those associated with the Schwarzschild metric, and have sparked the imagination of physicists for decades. They are often conceptualized as existing at the end of a black hole's event horizon, suggesting the possibility of a link between the black hole and a separate region of spacetime. Some speculative theories suggest that matter which falls into a black hole could potentially emerge from a white hole located in another part of the universe, or even in an entirely different universe. This leads to fascinating ideas about wormholes, theoretical passages that might connect disparate regions of space and time, allowing for the transfer of matter across vast distances, or even between different universes. Despite the allure of such theories, there is currently no observational evidence supporting the existence of white holes. Their theoretical existence remains an intriguing possibility, but one that is far from proven. Furthermore, questions about their stability abound. If a white hole were to expel matter, that matter would inevitably interact with surrounding space and objects, potentially causing the white hole to destabilize and cease to exist. This presents a significant challenge to the viability of white holes as real physical phenomena. While both black holes and white holes remain central to our understanding of the universe, they serve as key puzzle pieces in a larger, ongoing effort to comprehend the fundamental laws of physics. As our observations deepen and our theoretical models evolve, the exploration of these extraordinary cosmic entities will continue to shape the way we perceive the cosmos, challenging our knowledge of time, space, and the very fabric of reality itself. White holes, though deeply intriguing, challenge many of the concepts we hold dear in the realm of physics. Their characteristics suggest that they could behave in ways that are fundamentally different from black holes, and this complexity significantly complicates our understanding of causality. As much as they spark our imaginations, the true existence of white holes remains a purely theoretical concept, with no empirical evidence to substantiate their reality, at least for now. These exotic phenomena push the boundaries of what we know about the universe, posing profound questions about the very fabric of space-time. While speculation about them serves to deepen the mysteries of the cosmos, their potential reality lies in the realm of theoretical physics, awaiting further exploration and understanding. As we delve deeper into the behavior of black holes, the consequences of falling into one become chillingly clear. The experience would be nothing short of catastrophic, shaped by the black hole's immense gravitational pull and the extreme conditions defined by the laws of physics. Initially, the overwhelming force of gravity would be felt as you approached, becoming stronger and more intense the closer you got to the event horizon, the boundary beyond which not even light can escape. For smaller black holes, this gravitational force is so pronounced that it would stretch you out in an effect known as spaghettification. The difference in gravitational force between your head and feet would cause your body to elongate, distorting into a thin, elongated shape resembling spaghetti. As you cross the event horizon, time itself would begin to warp. From the perspective of an outside observer, it would appear as though you were slowing down, caught in the grip of gravitational time dilation. Your image would grow increasingly red-shifted, fading into a dim, twilight-like state. In contrast, from your point of view, there would be no immediate indication that you had crossed the threshold. The event would seem to happen without any dramatic change, and before you could realize it, it would already be too late. Once inside, all paths inevitably lead toward the singularity, the point of infinite density at the core of the black hole, where gravity compresses matter to an unimaginable degree. Here, the laws of physics as we know them cease to function, and any matter, whether you or anything else, would be crushed into an infinitely dense state. What happens within the singularity is a complete mystery. Theoretical physics cannot yet describe the extreme conditions that govern this region, and so the fate of anything that enters remains elusive. Though the notion of falling into a black hole conjures unsettling images of destruction, It also invites deeper questions about the fundamental nature of space, time, and reality. The event poses philosophical as well as scientific puzzles, pushing us to reconsider our understanding of the universe's most basic principles. Moreover, it highlights the terrifying yet captivating unknowns that exist beyond our observational limits, propelling both scientific inquiry and philosophical debate forward. When two black holes are in close proximity, orbiting one another, they form what is known as a binary black hole system. These systems exhibit fascinating dynamics driven by the gravitational interactions between the two massive objects. As the black holes orbit, they send ripples through the fabric of space-time, gravitational waves that propagate across vast distances. The intensity of these waves grows as the black holes spiral ever closer, particularly near the final stages of their dance when they are on the brink of merging. The detection of these waves provides profound insights into the existence of black holes and opens up an entirely new avenue for exploring the universe. The behavior of these binary systems is largely dictated by the masses of the black holes and the distance between them. As they orbit each other, they lose energy in the form of gravitational radiation, causing them to gradually spiral inward. Over time, this process accelerates, drawing the black holes closer and faster. Eventually, the two will collide and merge into a single, more massive black hole. This merger produces a unique and easily identifiable signal known as a chirp. The chirp is characterized by an increasing frequency, followed by a sharp drop as the black holes collide, offering a glimpse into the final moments before the catastrophic event. Advanced observatories such as LIGO and Virgo have successfully detected these gravitational waves, allowing scientists to catalog various binary black hole mergers. These detections not only confirm the existence of black holes, but also provide valuable data on their population, formation, and evolution. In the aftermath of a merger, the newly formed black hole may initially be in an unstable, excited state, emitting strong gravitational waves as it settles into a more stable configuration. The merger process may also expel matter and energy, offering additional clues about the environments surrounding black holes. Studying these systems enhances our understanding of general relativity, highlighting the intricate gravitational interactions at play and revealing deeper truths about space-time itself. Quasars are among the most luminous objects in the universe, capable of outshining entire galaxies. Their astonishing brightness is intrinsically linked to the presence of supermassive black holes that reside at their cores. A quasar represents an active galactic nucleus, where a supermassive black hole is actively consuming material from its surroundings, generating vast amounts of energy in the form of electromagnetic radiation. This radiation spans the spectrum from visible light to radio waves to X-rays, all produced as matter spirals toward the black hole. As it does, it forms an accretion disk, a rotating disk of gas and dust that is heated to extreme temperatures by friction and gravitational forces. The energy released in this process can be many orders of magnitude greater than the total energy output of all the stars in a galaxy, making quasars detectable from billions of light years away. The relationship between quasars and supermassive black holes is key to understanding both the growth of these enigmatic objects and the evolution of galaxies themselves. It is believed that supermassive black holes formed early in the universe's history, rapidly accumulating mass by accreting gas and merging with other black holes. During this period, the black hole would become a quasar, a state of high activity and brightness. Studying how and when these black holes transition into quasars gives us valuable insights into galaxy formation and the evolution of cosmic structures. Moreover, quasars serve as essential tools for exploring cosmic distances and understanding the expansion of the universe. By observing quasars at varying redshifts, astronomers can glean information about the conditions of the early universe, shedding light on the evolution of galaxies and the interplay between black holes and their host galaxies. In this way, quasars not only deepen our understanding of supermassive black holes, but also play a significant role in unraveling the mysteries of cosmic evolution. Detecting black holes remains one of the most challenging tasks in modern astronomy. Since black holes do not emit light, they cannot be observed directly. However, scientists have developed clever techniques to infer their presence, such as detecting the gravitational effects they have on nearby objects, or the radiation emitted as matter is consumed by the black hole's immense gravitational pull. Despite the challenges, our ongoing efforts to observe and understand black holes continue to illuminate some of the most fundamental questions about the universe. Astronomers have developed several innovative methods to detect the presence of black holes and gain insight into their mysterious characteristics. Although these enigmatic objects are invisible by nature, the gravitational effects they exert on their surroundings provide an indirect yet reliable means of detection. One of the most widely employed techniques involves tracking the influence of a black hole's intense gravitational pull on nearby stars and gas clouds. This is particularly effective when the black hole is part of a binary system or is in close proximity to other stellar objects. When a black hole is part of such a system, its massive gravitational force can be observed in the movements of nearby stars and gas. Scientists closely monitor the orbits of these objects, observing how they move in patterns that can only be explained by the presence of an unseen but extremely massive object. By applying the principles of Newtonian physics, or in more extreme cases, general relativity, researchers can deduce the mass of the black hole. Even if the black hole itself remains invisible, these gravitational interactions provide a clear picture of its size and influence. This method has led to the discovery of numerous black holes, including the famous supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A Sa. Another key method of detecting black holes involves observing the X-rays emitted when matter is pulled toward the black hole. As gas, dust, and other debris are drawn into a black hole, they form a swirling accretion disk. This disk experiences intense friction and is subjected to extreme gravitational forces, causing the material within it to heat up to incredibly high temperatures. This process produces X-rays, which can be detected by specialized telescopes designed for this purpose. By studying these emissions, astronomers can identify the presence of black holes, particularly those that are actively accreting material. Yet another groundbreaking approach to black hole detection comes from the study of gravitational waves. These ripples in spacetime are created when two black holes collide, producing an event of extraordinary energy. These waves travel across the universe, carrying with them critical information about the masses, spins, and other properties of the merging black holes. Observatories like LIGO and Virgo have been instrumental in detecting these gravitational waves, allowing scientists to study cosmic events that occurred billions of years ago. The ability to observe such phenomena opens up an entirely new realm of black hole research. Through the combination of studying stellar motion, detecting X-ray emissions, and observing gravitational waves, our understanding of black holes has expanded dramatically. These indirect methods of detection not only confirm the existence of black holes, but also provide a wealth of information about their properties, how they form, and their crucial role in the evolution of galaxies. Together, they paint a more comprehensive picture of the complex and dynamic universe we inhabit. Among the many varieties of black holes, intermediate mass black holes are some of the most intriguing and elusive. These objects, with masses ranging from hundreds to tens of thousands of times the mass of the Sun, occupy a mysterious middle ground between stellar mass black holes, which form from the collapse of individual massive stars, and supermassive black holes, which reside at the centers of galaxies. Despite being theorized for decades, intermediate mass black holes have remained difficult to detect, posing a significant challenge to astrophysicists. One of the key reasons intermediate mass black holes are so hard to identify is related to their formation processes. While stellar mass black holes are relatively common and well understood, formed from the remnants of massive stars that have exhausted their nuclear fuel, the origins of intermediate mass black holes are still a subject of active research. Scientists speculate that these black holes may form through the merging of smaller black holes within dense star clusters, or through the collapse of very massive star clusters. Understanding these formation pathways is crucial, as it would help distinguish intermediate mass black holes from both their smaller and larger counterparts. The observational signatures of intermediate mass black holes are also more subtle than those of their larger or smaller relatives. Unlike supermassive black holes, which known to produce strong X-ray emissions when they actively accrete material, intermediate mass black holes typically do not exhibit this kind of activity. Instead, they may only reveal their presence through their gravitational influence on nearby stars or gas clouds. In many ways, detecting an intermediate mass black hole is like searching for a shadow rather than a direct source of light. Their relatively low luminosity and the fact that they are often located far from the centers of galaxies make them even more challenging to identify using traditional observation techniques. Despite these challenges, recent advancements in technology and observational methods are providing renewed hope in the search for these elusive black holes. One promising avenue involves the detection of gravitational wave produced by the merger of smaller black holes, which could lead to the discovery of intermediate mass black holes as they collide and form more massive objects. Observations of star clusters, especially those in regions where stellar interactions are intense, could also yield valuable clues about the existence of these black holes. Understanding intermediate mass black holes is crucial for several reasons. Not only could their discovery provide important insights into the processes of black hole formation, but it could also help bridge the gap between the formation of stellar mass and supermassive black holes. By studying these intermediate mass objects, scientists could gain a better understanding of how black holes evolve and the role they play in the broader cosmic landscape. Primordial black holes, another fascinating class of theoretical black holes, are believed to have formed in the chaotic conditions of the early universe shortly after the Big Bang. These ancient objects are thought to have emerged during a period of rapid cosmic expansion, when density fluctuations in the fabric of spacetime itself created regions of intense gravitational collapse. Unlike the black holes that form from collapsing stars, primordial black holes may have originated directly from the high-energy conditions of the early universe. There is a possibility that some primordial black holes still exist today. If these black holes are small, perhaps weighing less than 100,000 times the mass of the Sun, they could have evaporated over time due to a process known as Hawking radiation. This theoretical form of radiation predicts that black holes emit energy and lose mass gradually, eventually leading to their complete disappearance. However, larger primordial black holes, those with several times the mass of the Sun, may have endured and could even contribute to the elusive dark matter that makes up much of the universe's mass. While there is currently no direct evidence for the existence of primordial black holes, scientists are actively searching for signs of them. One potential method involves detecting the effects of primordial black holes interacting with normal matter, or looking for evidence of their influence on gravitational waves produced by colliding objects in space. The discovery of primordial black holes would not only confirm their existence, but also offer crucial insights into the conditions of the early universe, helping to refine our understanding of cosmic evolution. The possibility that primordial black holes might still be lingering in the universe is both exciting and intriguing. These ancient black holes could offer a unique link to the universe's infancy, allowing us to peer into the earliest moments of cosmic history. If they exist, primordial black holes could play a vital role in shaping the cosmic landscape we observe today, offering new avenues for exploration and discovery. As scientists continue to gather more data and refine existing theories, the enigmatic nature of primordial black holes may reveal new chapters in our understanding of the cosmos. These mysterious objects could hold answers to questions about the very formation of the universe and its most complex structures. One of the most captivating cosmic phenomena is the Great Attractor, a massive gravitational anomaly located in the vicinity of the Milky Way galaxy. Approximately 100 million light-years away in the direction of the Centaurus constellation, this gravitational anomaly pulls entire galaxies, clusters, and other celestial structures toward it. This immense force is so potent that it influences the motion of galaxies across a vast region of space, suggesting that there is far more at play in the universe than meets the eye. The exact nature of the Great Attractor remains elusive, mainly due to its location behind the dense plane of our own galaxy, which makes direct observation incredibly difficult. However, astronomers believe it harbors a tremendous concentration of mass, potentially composed of dark matter and numerous galaxy clusters. This gravitational pull impacts not only our own Milky Way, but also many other galaxies within the same region, all of which are being drawn toward the center of this cosmic mass. The movement of these galaxies paints a compelling picture of the complex gravitational forces shaping the cosmos. Scientists have identified several galaxy clusters that seem to contribute to the Great Attractor's gravitational field. The Norma cluster, one of the most massive in the region, plays a significant role in this colossal pull. As these clusters interact with each other and the surrounding dark matter, their combined gravitational effects cause an array of galaxies to drift toward the central concentration of mass. This fascinating dynamic challenges our understanding of how galaxies and clusters interact, revealing the vast complexities of gravitational forces at play across the universe. The Great Attractor is an intriguing anomaly that forces astronomers to rethink our understanding of cosmic structures and their intricate relationships. It highlights the critical role that gravitational forces play in shaping the distribution and movement of galaxies, further illustrating the cosmic forces that govern the vast expanse of space. Studying such phenomena not only provides a deeper understanding of galaxy formation, but also offers critical insights into the behavior of dark matter and the evolution of the universe itself. In stark contrast to these massive, gravitationally bound structures are cosmic voids, vast, empty regions that exist between galaxies and galaxy clusters. These voids, which can span tens to hundreds of millions of light years, are among the largest structures in the universe. Their formation is closely tied to the overall evolution of the universe and the distribution of matter. Early in the universe's history, matter was spread more or less evenly, but as the universe expanded and cooled, slight fluctuations in density began to emerge. Over billions of years, regions with higher density attracted more matter, forming galaxies and clusters, while areas with lower density expanded, leaving behind the large voids we observe today. The interplay between gravity and cosmic expansion has been crucial in shaping these vast, empty regions. As galaxies clump together due to the pull of gravity, voids continue to emerge in areas where this gravitational influence is weaker. While you might expect these voids to be entirely empty, they are not devoid of matter. In fact, these expansive regions can contain sparse populations of galaxies, dark matter, and gas. However, the galaxies found within voids tend to be fewer and less massive compared to those located in denser regions of the universe. Moreover, cosmic voids can also harbor intergalactic gas and dark matter, further contributing to the intricate structure of the universe. Studying these voids is essential for understanding the dynamics of the universe on a large scale. They provide valuable insights into the nature of dark energy, gravitational interactions, and the overall cosmic structure. The size, shape, and distribution of voids offer observational clues about the history of the universe's expansion and the fundamental forces that have shaped it over billions of years. By examining these vast empty spaces, astronomers are able to glean important information about the forces that drive the universe's growth and evolution. The cosmic web, a vast network of interconnected structures, is the result of gravitational interactions between galaxies, dark matter, and gas over unimaginable distances. This intricate web-like arrangement is a direct consequence of the universe's ongoing expansion, with higher density regions attracting surrounding matter and establishing a network of filaments that stretch across space. These filaments, composed primarily of dark matter, remain invisible to conventional observations because dark matter does not emit light. Nonetheless, its gravitational influence is unmistakable, causing visible matter, like galaxies and gas, to congregate along these cosmic threads. The formation of the cosmic web is a long process that has unfolded over billions of years. As the universe cooled and expanded, regions with slightly higher density began to attract surrounding matter, forming a network of galactic filaments. These filaments eventually became the backbone of the universe's large-scale structure, with galaxies predominantly located in the denser regions of the filaments and clusters. Voids, conversely, exist between these threads of dark matter where the gravitational pull is weaker. Over time, these filaments have continued to evolve. The cosmic web is far from static. It stretches and adapts as galaxies and galaxy clusters interact with one another. This dynamic process helps to shape the universe's large-scale architecture, providing a vivid demonstration of how gravitational forces influence the structure and evolution of the cosmos. Studying the cosmic web is crucial for understanding dark matter, the expansion of the universe, and the overall evolution of cosmic structures. Mapping the filaments that make up the cosmic web allows scientists to better understand the distribution of galaxies and the physical forces that shape them. By observing the interactions between filaments, galaxies, and clusters, astronomers can gain a deeper understanding of the fundamental forces driving the growth of the universe. These insights help scientists piece together the grand puzzle of the universe's formation and evolution. Galaxy clusters, which are the largest gravitationally bound structures in the universe, also provide crucial clues about cosmic evolution. As these massive clusters form, they exert gravitational influence on each other, leading to a variety of fascinating interactions. These include mergers, tidal forces, and the creation of superclusters, vast collections of galaxy clusters bound together by gravity. When two galaxy clusters collide, the result can be extraordinarily energetic. Although the galaxies themselves rarely collide due to the immense distances between them, the hot gas surrounding the galaxies can interact, generating shock waves and emitting X-rays. Over time, these collisions can lead to the merging of the clusters, a process that may take hundreds of millions of years. This merging not only alters the characteristics of the clusters involved, but can also trigger bursts of star formation, reshaping the galaxies within. In addition to collisions, tidal forces between galaxy clusters can distort their structures. These forces can stretch and deform the clusters, affecting the distribution of galaxies and gas within them. Tidal interactions can even strip away galaxies or gas from one cluster and transfer them to another, a phenomenon known as galaxy harassment. These interactions have profound implications for the orbits of galaxies, influencing their future trajectories and relationships with neighboring clusters. Understanding these interactions is key to grasping the larger dynamics of the universe's evolution. Observing and studying galaxy clusters provides significant insights into the nature of dark matter, intergalactic gas, and the behavior of cosmic structures. By examining the ways in which galaxy clusters interact, scientists can better comprehend the complex processes that drive the evolution of the universe, shedding light on the vast forces that shape the cosmos. The largest known structures in the universe are truly mind-boggling in scale and complexity. These colossal formations of galaxies and cosmic materials stretch across unimaginable distances, interconnected into a grand tapestry referred to as the cosmic web. Within this web lie massive cosmic entities such as galaxy superclusters, great walls, and expansive voids, each contributing to the vast architecture of the cosmos. The sheer size and intricate connections between these elements reveal how matter organizes itself on the grandest of scales. One of the most well-known examples of these immense structures is the Sloan Great Wall. This massive galaxy supercluster stretches approximately 100 million light-years, serving as one of the largest known structures in the universe. It consists of a vast network of galaxies and galaxy clusters, arranged in a manner that highlights the large-scale organization of matter across vast swathes of the cosmos. This structure offers a stunning snapshot of how gravitational forces bring together galaxies and clusters into complex yet coherent formations. Similarly, the Hercules Corona Borealis Great Wall stands as a testament to the incomprehensible scale of the universe. Spanning around 10 billion light-years in length, it is considered one of the most colossal structures ever observed. This extraordinary formation of galaxy clusters and superclusters is intricately tied together by the gravitational pull of dark matter, forming a vast and interconnected superstructure that defies the usual patterns of cosmic uniformity. Its discovery has profound implications for our understanding of the universe, challenging the traditional concepts of homogeneity and isotropy. Instead of a universe that is uniformly distributed, The Hercules Corona Borealis Great Wall suggests that the cosmos may be far more complex, with large-scale variations that span billions of light years. Yet even in the midst of these dense and awe-inspiring galactic structures, vast voids exist, providing a counterpoint to the crowded filaments of galaxies and clusters. These cosmic voids are immense regions of space that stretch for hundreds of millions of light years, almost entirely devoid of matter. They serve as the gaps between the dense, interconnected threads of the cosmic web, illustrating the diversity of structures that shape the universe. Although these voids may seem empty, they are not devoid of interest. They contain dark matter and a sparse collection of galaxies. These voids offer a fascinating and essential part of the cosmic puzzle, highlighting the intricate balance between the full and empty regions of the universe. Exploring these enormous structures deepens our understanding of the cosmos in a multitude of ways. By studying their formation, scientists can unlock secrets about cosmic evolution, dark matter distribution, and the dynamic processes that govern the formation and interaction of galaxies. The interplay between superclusters and voids reveals the fundamental framework of the universe, offering new insights into how matter and energy have evolved throughout cosmic history. The evolution of galaxies themselves is a dynamic process that unfolds over billions of years. Galaxies begin to form through gravitational interactions between gas and dark matter, with small fluctuations in density leading to the collapse of material under its own gravity. This collapse ignites the birth of the first stars, marking the beginning of complex galactic structures. As galaxies grow and evolve, they undergo profound transformations in their morphology and star populations, driven by a combination of internal and external processes. One of the most significant events in the life of a galaxy is the merger. When galaxies collide, their sizes and shapes can be dramatically altered. Major mergers, where two large galaxies combine, can trigger intense periods of star formation, as gas is funneled into the galactic center. This influx of material can lead to the creation of elliptical galaxies, fundamentally reshaping the galaxy's structure and dynamics. During these interactions, stars, gas, and dark matter are redistributed, leading to a reshuffling of the galaxy's physical characteristics. The rate at which stars form within a galaxy is a crucial indicator of its evolution. In the early universe, galaxies often experienced high rates of star formation, creating a vibrant and dynamic cosmic environment. Over time, however, as galaxies exhaust their gas supply through star formation, the rate of new star births begins to slow. This process can lead to what's known as quenching, where star formation ceases, leaving behind older populations of stars. As a result, these galaxies can eventually evolve into passive red and dead systems, their stellar populations growing increasingly older and less active. Yet, galaxies do not remain static. Over the course of eons, galaxies continue to evolve, shedding and acquiring material. They can gain gas and dust from their surroundings or through interactions with smaller dwarf galaxies. Gravitational forces between galaxies can lead to further transformations, altering the galactic landscape and continually reshaping the universe at large. Magnetic fields, though often overlooked, play an essential role in shaping the structure of galaxies and other cosmic formations. These fields are present in various astrophysical environments, from individual galaxies to massive galaxy clusters and the vast expanse of intergalactic space. Magnetic fields influence a wide range of processes, from the dynamics of gas and dust to the formation of stars. Within galaxies, magnetic fields intertwine with the interstellar medium, the gas and dust that fills the spaces between stars, affecting the movement of charged particles and regulating the flow of material within the galaxy. This interplay can influence star formation by providing additional pressure that supports regions of gas against gravitational collapse. On larger scales, magnetic fields also affect the behavior of galaxy clusters and cosmic filaments. When galaxy clusters collide or interact, the magnetic fields present can influence the dynamics of the hot gas that fills these structures, triggering shock waves and shaping complex patterns of gas flow. These interactions play a critical role in redistributing matter and altering the structure of these enormous clusters. In the broader cosmic web, magnetic fields are thought to influence the gas dynamics within the filaments that connect galaxy clusters, potentially affecting how galaxies are distributed along these filaments. Understanding the role of magnetic fields in cosmic structures is crucial for developing a comprehensive understanding of astrophysical processes. Observing these fields, often through their effects on polarized light emitted by distant galaxies, provides valuable clues about their strengths and configurations. These insights not only enhance our knowledge of galaxy formation and evolution, but also reveal the underlying physics that governs the structure and development of the universe. One of the most significant challenges in modern astronomy is mapping the distribution of dark matter. Though invisible and undetectable by conventional means, dark matter exerts a profound influence on the universe, shaping the formation of galaxies and the overall structure of the cosmos. Despite its elusive nature, scientists have developed several methods to infer the presence and distribution of dark matter, often relying on its gravitational effects on visible matter and light. Gravitational lensing is one of the primary techniques used to map dark matter. When massive objects like galaxy clusters pass between Earth and more distant galaxies, their gravitational fields bend the light coming from those distant sources. This effect, known as gravitational lensing, distorts and magnifies the images of far-off galaxies, offering valuable information about the distribution of mass in the foreground clusters. By studying the degree of light bending, astronomers can map the concentration of dark matter associated with the lensing object. Another method involves studying the motion of galaxies within clusters. By measuring the velocities of these galaxies, astronomers can assess the gravitational pull acting upon them, revealing the total mass of the cluster, including the hidden dark matter. This technique, known as dynamical studies, helps astronomers estimate the distribution of dark matter around galaxy clusters. When combined with other observations, these methods provide a more comprehensive understanding of dark matter's role in the cosmic structure. These efforts to map dark matter are essential for understanding the fundamental forces shaping the universe. As dark matter remains an enigma, its gravitational effects offer one of the few windows into its properties, and its mapping is a crucial step in unraveling the mysteries of the cosmos. The cosmos is a vast and mysterious expanse, constantly unveiling new wonders and deepening our understanding of its intricate mechanisms. Among the most remarkable discoveries in modern astrophysics is the cosmic microwave background radiation, CMB. This faint glow, pervasive throughout the universe, acts as a cosmic relic from the early moments after the Big Bang. By studying tiny fluctuations in the temperature of the CMB, scientists can peer back into the universe's infancy, offering invaluable clues about its initial structure. These minute variations in temperature correspond to density differences in matter, which eventually gave rise to the large-scale structures we observe today, such as galaxies and clusters. The distribution of matter, both visible and invisible, is intricately encoded within the CMB. These fluctuations are believed to be a reflection of the presence of both ordinary visible matter, such as stars, gas, and dust, and the elusive dark matter. Dark matter, though invisible and detectable only through its gravitational influence, plays a central role in shaping the cosmic web. As it congregates in certain regions, dark matter helps map out a vast network of structures, acting as the scaffolding around which galaxies and galaxy clusters form. Through ongoing research, astronomers continue to refine their models of dark matter's distribution, enhancing our understanding of how it shapes not just galaxies, but the evolution of the universe itself. One of the most puzzling phenomena in galactic dynamics is the unexpected rotation speeds of stars, particularly in spiral galaxies. According to classical Newtonian mechanics, stars in the outer regions of a galaxy should orbit slower than those closer to the center. The mass concentrated in the central regions of galaxies from stars and gas should be enough to explain the motion of stars at various distances. However, observations consistently show that the stars at the outskirts of galaxies are moving at much higher speeds than expected. This discrepancy, known as the galaxy rotation problem, has led astronomers to propose the presence of dark matter as a key factor. Dark matter, a mysterious and invisible substance, does not emit or absorb light, making it undetectable through conventional means of observation. Yet it exerts a substantial gravitational force, contributing to the total mass of galaxies. This unseen matter is thought to form a halo around galaxies extending far beyond their visible edges. The gravitational influence of this dark matter halo provides the additional mass necessary to explain the observed faster than expected rotation rates of stars in the outer regions of galaxies. This halo stretches far beyond the galaxy's visible boundaries, helping to keep the stars in motion at much higher speeds than anticipated. Over the years, astronomers have conducted numerous studies to map the distribution of dark matter within galaxies and galaxy clusters. These efforts have provided crucial evidence supporting the hypothesis of dark matter's existence and its role in galactic dynamics. By examining the behavior of stars, gas, and other objects within galaxies, scientists can infer the gravitational effects of dark matter and map its concentration. The influence of dark matter extends beyond individual galaxies, affecting the interactions between galaxies, such as mergers and collisions. These interactions, in turn, influence the overall dynamics of cosmic structures. While dark matter remains the leading explanation for the galaxy rotation problem, alternative theories are being explored. Some researchers are investigating modifications to the laws of gravity as a possible explanation for the observed discrepancies. As technology advances and new observations are made, future experiments will continue to test these theories, pushing the boundaries of our understanding of the universe's fundamental nature. In addition to unraveling the mysteries of dark matter, studying the largest structures in the universe, galactic superclusters offers another critical piece of the cosmic puzzle. Superclusters are massive groupings of galaxy clusters and groups, representing the largest known structures in the cosmos. Their formation dates back to the early universe, shortly after the Big Bang, when regions of slightly higher density began to collapse under the influence of gravity. Over billions of years, these collapsing regions formed the first galaxies, which eventually coalesced into superclusters. The evolution of superclusters is intricately tied to the behavior of both dark and visible matter. Dark matter plays a vital role in providing the gravitational foundation for these vast structures. As dark matter halos form, they attract visible matter, such as gas and stars, and other dark matter, aiding in the formation and growth of superclusters. The merging of smaller galaxy clusters, along with the ongoing accretion of gas and galaxies, contributes to the continual expansion and growth of superclusters over cosmic time. Galactic interactions are a key component in the development of superclusters. When individual galaxy clusters collide or merge, it can trigger bursts of star formation and redistribute the galaxies within them. These collisions can lead to the formation of new galaxy types, such as elliptical galaxies arising from the merging of spiral galaxies. This process alters the overall diversity of galaxies within the supercluster and shapes its structure. The environments within superclusters also vary significantly. The dense cores may feature active star formation and intense galactic interactions, while the outskirts are quieter with fewer ongoing processes. By studying the dynamics of superclusters, astronomers gain crucial insights into the large-scale structure of the universe and the forces that drive its evolution. As we move from the grand scale of superclusters to the more intimate realm of individual stars, one of the most fascinating phenomena that scientists observe is the pulsation of certain stars. These pulsating stars, known as variable stars, undergo periodic changes in brightness due to fluctuations in their internal structure and energy balance. This pulsation is typically a result of thermal instability in the star's outer layers, causing it to expand and contract in a regular cycle. The most well-known pulsating stars include Cepheid variables and RR Lyrae stars, each exhibiting unique characteristics. The pulsation mechanism in stars such as Cepheids is driven by the interplay between radiation pressure and gravitational forces. When the outer layers of the star heat up, they expand, which increases the radiation pressure. However, this expansion leads to a temporary instability. As the star cools, gravity causes it to contract, leading to a cycle of expansion and contraction. This cycle causes the star's brightness to vary, and these variations can be observed over a period of time. In massive stars, the pulsation mechanism is influenced by the opacity of elements like helium and hydrogen in the outer layers, which changes with ionization and temperature. This creates a feedback loop that drives the star's expansion and contraction. The study of pulsating stars is not only intriguing from an astrophysical standpoint, but also has important applications in measuring astronomical distances. Cepheid variables, due to their predictable pulsation patterns, have been used as standard candles to calculate distances to far-off galaxies. By studying the pulsations of stars, astronomers can learn more about their internal structure, their evolutionary history, and their role in the broader cosmic framework. Among the most extreme and fascinating objects in the universe are magnetars, a type of neutron star characterized by their incredibly strong magnetic fields. These magnetic fields can be over 1,000 times stronger than those of typical neutron stars and far more powerful than any other magnetic fields in the universe. Magnetars form when a massive star undergoes a supernova explosion, collapsing its core into a neutron star. During this collapse, the core compresses dramatically, causing it to spin faster and amplify any pre-existing magnetic field. Some theories suggest that the rapid rotation and complex internal structure of neutron stars contribute to the strengthening of the magnetic field. The magnetic field of a magnetar can grow even stronger over time through a process known as magnetic flux emergence. As the neutron star cools and evolves, the magnetic field lines can become distorted and compressed, leading to the creation of extraordinarily strong magnetic fields. In some cases, these fields can reach magnitudes of 1 quadrillion Gauss, far exceeding typical values observed in other celestial bodies. The study of magnetars provides valuable insights into the extreme environments found within neutron stars and offers a window into the fundamental forces that govern the universe. Together, these cosmic phenomena, from the faint remnants of the Big Bang to the mysterious dark matter shaping the universe's structure, to the extreme conditions within magnetars, offer us a glimpse into the forces that have shaped and continue to shape the cosmos. Each discovery adds a layer of complexity to our understanding of the universe, driving the quest for knowledge and unveiling new mysteries at every turn. Magnets, or more precisely magnetars, are among the most fascinating objects in the universe. These ultra-dense remnants of massive stars are not only powerful in their gravitational pull, but they also produce intense bursts of electromagnetic radiation, including X-rays and gamma rays. This electromagnetic energy is intricately tied to their magnetic fields, which are among the most powerful in the cosmos. The energy associated with these magnetic fields is released in sudden explosive bursts when the magnetic field lines of the magnetar reconnect and realign. This process, called magnetic reconnection, results in the release of immense energy, contributing to the creation of these powerful bursts. These events can be observed as spectacular flashes of radiation, providing a glimpse into the extreme physics at play. Understanding the formation and behavior of magnetars offers profound insights into the interplay of fundamental forces, gravity, nuclear physics, and magnetism, operating under extreme conditions. Magnetars act as natural laboratories for studying matter in environments that are simply unattainable on Earth. The behavior of matter in these magnetic giants provides a deeper understanding of how matter behaves under conditions of intense gravity and magnetic fields, offering an invaluable window into the mysteries of astrophysical processes. Their study enriches our overall comprehension of the forces shaping the universe. One of the most energetic phenomena in the universe is the gamma ray burst, GRB, a highly energetic explosion that occurs in distant galaxies. Gamma ray bursts release an extraordinary amount of energy in the form of gamma radiation, often far exceeding what we would expect from other cosmic events. In fact, these bursts can release more energy in a matter of seconds than our sun will emit throughout its entire lifetime. Gamma ray bursts are generally classified into two categories, short and long bursts, each associated with different cosmic phenomena. Long gamma ray bursts, which last anywhere from several seconds to several minutes, are believed to result from the death of massive stars. When a large star exhausts its nuclear fuel, it may collapse under its own gravity, forming a black hole or neutron star. This collapse unleashes a staggering amount of energy, which creates powerful jets of high-energy particles. These jets move outward at nearly the speed of light, and when they interact with the outer layers of the dying star, they produce a flash of gamma radiation. This explosive event is observed as a long gamma-ray burst, and it is often accompanied by a supernova, an explosive death throes of the star. These events are so powerful that they can be seen from billions of light years away. Short gamma-ray bursts, on the other hand, last for less than 2 seconds. These bursts are thought to originate from the merger of compact objects such as neutron stars or black holes. When two neutron stars collide, the resulting explosion releases an immense amount of energy in the form of gamma rays. This process not only leads to the creation of these powerful bursts, but also contributes to the formation of heavy elements such as gold and platinum. These elements are synthesized through a process known as rapid neutron capture, or the R process, which occurs in the high-energy environment generated by these mergers. As the neutrons are rapidly captured by atomic nuclei, they form heavier isotopes, and through subsequent beta decay, elements like gold, platinum, and uranium are formed. This is how some of the heaviest elements in the universe are created. The study of gamma-ray bursts is a crucial avenue for understanding the life cycles of stars, the nature of black holes, and the processes behind the synthesis of elements in the universe. By observing these bursts and their afterglows across different wavelengths, X-rays, optical, and radio, astronomers can gather valuable information about the distance, location, and properties of the galaxies in which these bursts occur. This data allows scientists to explore the conditions under which these extraordinary events take place and the underlying mechanisms governing their production. Another important aspect of the universe's enrichment with heavy elements is the role of neutron star mergers. When two neutron stars collide, they create an environment rich in neutrons, which facilitates rapid neutron capture. This environment allows atomic nuclei to absorb neutrons at an incredibly rapid rate, much faster than they can undergo beta decay. As the neutron stars spiral inward and eventually merge, they release an immense amount of energy, ejecting neutron-rich material into space. These nuclei continue to absorb neutrons until the supply of free neutrons diminishes. At this point, some of these heavy nuclei undergo beta decay, converting neutrons into protons and resulting in the formation of even heavier elements. This process of neutron star mergers is responsible for the creation of many of the universe's heaviest elements, including gold, platinum, and uranium. When the gravitational waves generated by these mergers are detected, along with the electromagnetic radiation from the event, it is possible to trace the presence of these heavy elements in the aftermath of the collision. One notable example of this is the detection of gravitational waves from the neutron star merger event GW 170817, which occurred in 2017. Following this event, astronomers observed signatures of heavy elements, further confirming the critical role neutron star mergers play in the enrichment of the universe with essential building blocks for planets and life. As scientists continue to study neutron star mergers, they gain deeper insights into the fundamental physics that govern extreme astrophysical environments. This research not only sheds light on the origins of heavy elements, but also opens up new avenues for understanding the behavior of matter under the most intense conditions known in the universe. Another intriguing celestial mystery involves the enigmatic behavior of Tabby's star, or K-C 8462852, a star that has baffled astronomers for years due to its irregular dimming patterns. Observations of Tabby's star have revealed that its brightness dips at irregular intervals, with some dips being particularly dramatic. These unusual dimming events have led to a range of theories, some even suggesting the presence of an alien megastructure orbiting the star. However, this idea, while captivating, is not considered the most plausible explanation by most scientists. A more likely theory involves the presence of a large cloud of dust orbiting Tabby's star. This dust cloud could be absorbing and scattering the star's light in such a way that results in the observed fluctuations in brightness. Such clouds of dust could be remnants of a collision between celestial bodies, or they may originate from material shed by the star itself. Unlike planets, which may cause regular and predictable dimming when they transit in front of their host stars, the dust cloud scenario would explain the erratic and unpredictable nature of the dimming events. Alternatively, it is possible that the star itself is undergoing intrinsic variations in its luminosity, Just as our sun experiences fluctuations in brightness due to solar flares and sunspots, Tabby's star may be undergoing similar internal processes that cause its brightness to fluctuate. These variations could be driven by complex interactions within the star's atmosphere, leading to the observed irregular dimming patterns. The true cause of the dimming remains a subject of intense investigation, but Tabby's star continues to be a key object of study in the search for new understanding of stellar behavior. The dimming patterns observed in Tabby's star present a striking anomaly in the field of stellar astronomy. Unlike typical stars, the way in which this star's brightness fluctuates does not match the standard models used to explain such phenomena. For years, scientists have been trying to piece together the puzzle behind these mysterious dips in brightness. Despite numerous theories ranging from dust clouds to alien megastructures, no definitive answer has yet emerged. With each new observation, our understanding of the star becomes more layered, suggesting that we are far from uncovering the true cause. As technological advancements enable deeper and more accurate study of stars, there is hope that we might finally uncover the mechanism behind this cosmic enigma. Until then, Tabby's star remains one of the most captivating and perplexing mysteries in our galactic neighborhood, forcing astronomers to reassess long-held assumptions about stellar behavior. In a completely different part of the cosmos, binary star systems present another fascinating puzzle. These systems, consisting of two stars orbiting a shared center of mass, are more complex than the solitary stars we typically observe. The gravitational interactions between the two stars in a binary system can drastically affect the formation and evolution of any planetary bodies that might orbit them. Unlike a single star, which creates a relatively stable gravitational environment, the presence of a second star introduces a level of complexity that can alter the entire process of planetary formation. For example, the surrounding accretion disk, a collection of gas and dust that forms the building blocks for new planets, becomes unstable due to the gravitational tug-of-war between the stars. Rather than a steady, predictable environment for planet formation, the disk may elongate or fragment, leading to conditions where material could either clump together to form new planets or be ejected entirely from the system. The orbits of any planets that form are equally affected. Depending on the relative distance between the two stars, a planet might orbit only one star or be caught in a more complicated orbit that takes it around both. This can lead to unusual orbital configurations that, in some cases, might not be conducive to sustaining life or retaining a planet's atmosphere over long periods. Despite these challenging conditions, many binary systems have been found to host planets. This suggests that planetary formation can indeed occur in these complex gravitational environments, broadening our understanding of how stars and planets interact. The diversity of planetary systems observed in binary star systems offers new insights into the variety of conditions that can give rise to worlds in the universe, contributing to our broader comprehension of stellar dynamics. The life cycle of a star unfolds through several distinct stages, each driven by the delicate balance of forces at play in the cosmos, most notably nuclear fusion. It all begins in a cold, dense molecular cloud, where gravity pulls gas and dust together to form a protostar. As material collapses, the temperature and pressure at the core increase. When these conditions reach a critical point, nuclear fusion ignites, marking the birth of a star. During this phase, hydrogen atoms are fused into helium, releasing an enormous amount of energy. Once a star enters the main sequence phase, it remains in this stable state for much of its life, which can span billions of years. It is during this time that stars like our sun shine, balancing the inward pull of gravity with the outward pressure from nuclear fusion. But as the star's hydrogen fuel begins to deplete, it begins to evolve. For stars like the sun, once the hydrogen in the core runs out, the star expands into a red giant. The core contracts while the outer layers expand and cool, causing the star to take on a reddish hue. Fusion shifts from hydrogen to heavier elements like helium, carbon, and oxygen. Eventually, the star sheds its outer layers, creating a planetary nebula, while the remaining core becomes a white dwarf, a dense remnant that will slowly cool over billions of years. In contrast, more massive stars face a much more dramatic fate. After evolving into red supergiants, these stars undergo a series of fusion processes that create heavier and heavier elements until they reach iron, the heaviest element that can be created through fusion. At this point, the core becomes unstable as it can no longer generate energy through fusion. The collapse of the core leads to a catastrophic supernova explosion, one of the most spectacular and violent events in the universe. The remnants left behind might form a neutron star, or, if the star was massive enough, a black hole, marking the end of a grand stellar life, but also seeding the universe with heavy elements vital for the formation of new stars and planets. This life cycle demonstrates the exquisite balance of forces that govern the stars, a balance that shapes the very fabric of our universe. But what about the fate of a star after it experiences a supernova? The term surviving in this context refers not to the star itself continuing to exist, but to the remnants of the star, specifically the core, undergoing a dramatic transformation. When a massive star runs out of nuclear fuel, its core collapses under its own gravity. This collapse triggers an enormous release of energy, expelling the outer layers in a brilliant explosion. The core, however, doesn't disappear. It either becomes a neutron star, or in the case of very massive stars, a black hole. A neutron star is an incredibly dense remnant, where the protons and electrons merge to form neutrons under extreme pressure. These stars are typically only about 20 kilometers in diameter, but they can contain more mass than our sun. Some neutron stars spin rapidly, emitting beams of radiation that make them detectable as pulsars. These objects can survive for millions, even billions of years after the supernova, effectively surviving the explosion by transforming into a new and stable form. Black holes, on the other hand, represent a different kind of survival. The core of a massive star collapses to such an extent that the gravitational pull becomes so strong that not even light can escape. While the star itself no longer exists, the black hole is a remnant that continues to exert an immense gravitational influence on its surroundings. Despite the star's death, the black hole remains an active and intriguing object, continuing to shape its environment. These objects, both neutron stars and black holes, continue to influence the cosmos long after their progenitors have exploded, serving as remnants of stellar evolution that hold clues to the complex dynamics of the universe. Meanwhile, in a different corner of the cosmos, brown dwarfs exist in a category all their own. These objects, often referred to as failed stars, occupy a space between the largest planets and the smallest stars. They form in much the same way as stars, through the collapse of gas and dust under gravity, but unlike true stars, they never reach the critical mass needed to initiate nuclear fusion in their cores. As a result, brown dwarfs shine faintly, emitting mostly infrared radiation. Though they may never become full-fledged stars, brown dwarfs are unique and fascinating objects that bridge the gap between planets and stars, adding yet another layer to the complexity of our understanding of celestial bodies. The universe, in all its vastness, continues to unfold new mysteries and phenomena, from the odd dimming patterns of distant stars to the subtle intricacies of binary systems and the final dramatic stages of stellar evolution. Each discovery deepens our understanding of the forces that shape the cosmos, leaving us with more questions, more wonder, and more to explore. However, they do not gather enough mass to trigger sustained hydrogen fusion at their core, a process necessary for true stellar classification. Instead, their mass typically ranges between approximately 13 and 80 times the mass of Jupiter. This makes them too large to be classified as planets, but not massive enough to be considered full-fledged stars. The objects in question are known as brown dwarfs, and detecting them poses significant challenges due to their inherent characteristics. Unlike true stars, brown dwarfs do emit some heat, a residual form of thermal radiation generated during their formation. However, this heat is faint and gradually diminishes as the object cools over time. In contrast to the intense nuclear fusion occurring in stars, brown dwarfs have much lower luminosity. As a result, their faint emission makes them incredibly difficult to detect. Even with the use of traditional optical telescopes, they tend to blend into the cosmic backdrop, obscured by the immense expanse of space. Adding to the difficulty of detection is the typical environment in which brown dwarfs are found. They often form in star-forming regions, where numerous other celestial objects are also in the process of formation. This crowded backdrop creates an additional layer of complexity, making it harder to isolate and pinpoint individual brown dwarfs. Furthermore, many of these objects are located at significant distances from Earth, further limiting the effectiveness of optical telescopes in their detection. To overcome these obstacles, astronomers have developed specialized techniques aimed at identifying brown dwarfs, most notably infrared observations. Since these objects emit most of their energy in the infrared spectrum rather than visible light, infrared telescopes have proven indispensable. With advancements in technology, including more sensitive infrared detectors, astronomers are now able to detect these elusive objects with increasing efficiency. As a result, our catalog of known brown dwarfs continues to grow, shedding light on the fascinating range of objects that populate the universe. In addition to their elusive nature, brown dwarfs play an important role in our understanding of astrophysics. Their study has provided valuable insights into the process of star formation and the various types of objects that populate the cosmos. By studying the characteristics of these intermediate objects, scientists are able to refine their models of stellar evolution and better understand the diverse nature of celestial bodies. The role of massive stars, specifically their powerful stellar winds, is another key topic in astrophysical research. Stellar winds are streams of charged particles that flow away from a star at incredible speeds. These winds are driven by the immense energy and pressure created in the outer layers of massive stars, which are far more energetic than those of smaller stars. Unlike less massive stars, where winds are generated through more subtle processes, the winds from massive stars are primarily driven by radiation pressure. At the core of this phenomenon is nuclear fusion. In massive stars, fusion occurs at an extraordinary rate, releasing vast amounts of energy. This energy creates an outward pressure that pushes against the star's outer layers. The radiation produced by this intense fusion generates high-energy photons capable of imparting momentum to particles in the star's outer atmosphere. When this radiation pressure becomes strong enough, it overcomes the gravitational pull of the star, causing material to be ejected into space. This process leads to the expansion of the star's outer layers, which loses mass to the surrounding environment. In addition to radiation pressure, stellar winds from massive stars are influenced by the internal structure of the star itself. The convective motions within the star can create turbulence, aiding in the outward flow of material. Furthermore, if the star possesses a strong magnetic field, it can interact with the stellar wind, affecting its direction and velocity. This interaction can lead to the formation of shocks and other complex phenomena within the wind. The effects of stellar winds on the surrounding space are far-reaching. These winds not only contribute to the chemical enrichment of the interstellar medium by dispersing elements formed within the star, but they also play a crucial role in shaping the dynamics of galaxy formation and evolution. When massive stars reach the end of their life cycles and explode as supernovae, the material expelled during their lifetimes contributes significantly to the formation of new stars and planets. This recycling of material is a key aspect of the cosmic ecosystem, ensuring that the building blocks of life are continuously replenished. In the context of cosmic evolution, the study of stellar winds provides invaluable insights into the life cycle of massive stars and their profound impact on the universe. Understanding these winds allows astronomers to better comprehend the processes that govern star formation, galaxy evolution, and the distribution of elements throughout space. One of the greatest mysteries of cosmology is dark energy, an enigmatic force that constitutes about 70% of the total energy density of the universe. Discovered through observations of distant supernova and the cosmic microwave background radiation, dark energy is believed to be responsible for the accelerated expansion of the universe. This phenomenon was first revealed in the late 20th century, when astronomers observed that galaxies were receding from us at an increasingly faster rate the farther they were from Earth. Initially, it was believed that the expansion of the universe was slowing down due to the gravitational attraction of all the matter in the cosmos. However, further studies revealed an unexpected twist. Not only is the universe expanding, but the rate of this expansion is actually accelerating over time. This observation led to the theory that dark energy, acting as a kind of anti-gravitational force, is pushing galaxies apart at an ever-increasing pace. The nature of dark energy remains one of the most profound mysteries in modern cosmology. Various theories have been proposed to explain its properties. Some suggest that dark energy could be a constant energy density, uniformly filling space, a concept often associated with Albert Einstein's cosmological constant introduced in his theory of general relativity. Other theories propose that dark energy is dynamic, changing over time and influencing the expansion of the universe in varying ways. Regardless of the specific nature of dark energy, its existence has revolutionized our understanding of the cosmos. It indicates that a large portion of the universe behaves in ways that defy our conventional notions of gravity and matter. The implications of dark energy are far-reaching and fundamental, as they shape not only the large-scale structure of the universe, but also its ultimate fate. If dark energy continues to dominate the expansion of the universe, it could lead to scenarios such as the Big Freeze, where galaxies drift further apart, stars burn out, and the universe becomes an increasingly cold and empty place. The search for a deeper understanding of dark energy is ongoing, as cosmologists strive to unravel the complex and often surprising nature of the universe. The formation of the first stars, known as population 3 stars, represents a pivotal chapter in the history of the universe. This event took place approximately 500 million to 1 billion years after the Big Bang, during a period known as the Cosmic Dawn. At this time, the universe was composed primarily of hydrogen, helium, and trace amounts of lithium, with little to no heavier elements that would form later in the interiors of stars. Understanding the formation of these primordial stars requires delving into the conditions of the early universe. In the aftermath of the Big Bang, small density fluctuations in the nearly uniform gas distribution began to collapse under their own gravity. These regions, where dark matter had already clumped together, created gravitational wells that attracted the surrounding gas. As gas fell into these wells, it grew denser and hotter. Eventually, when the temperatures in the core reached critical levels, hydrogen atoms fused into helium, marking the birth of the first stars. These early stars were likely massive and luminous, vastly different from the stars we observe today. Their size and energy output led to unique evolutionary paths. As the first stars began their life cycles, they contributed to the reionization of the universe, breaking down the neutral hydrogen that filled the cosmos and paving the way for the formation of galaxies, stars, and ultimately the complex structures we see today. The study of these primordial stars continues to be a central focus of astrophysics, providing essential clues to the origins of the universe and the processes that shaped its evolution. In the early moments of the universe, massive stars, though short-lived, played a pivotal role in shaping the cosmos as we know it. These stellar giants, burning bright and quickly consuming their fuel, had rapid life cycles, burning out in a blaze of energy and heavy elements. When these stars met their fiery end, they exploded in spectacular supernovae, releasing vast amounts of energy and enriching the surrounding interstellar medium with the building blocks of life. This process of stellar death and rebirth was crucial in providing the heavy elements necessary for the formation of subsequent generations of stars, galaxies, planets, and ultimately, life itself. The remnants of these early stars, scattered across the universe, have left behind a cosmic legacy that continues to influence the evolution of galaxies and planetary systems. Today, astronomers continue the search for evidence of these first stars, known as population 3 stars, by using powerful telescopes to peer deep into the distant universe. Their observations allow scientists to look back in time to a period long before the first galaxies formed. Through the study of these early stars, researchers gain valuable insights into the processes that govern star formation, galaxy evolution, and the chemical evolution of the universe. These insights illuminate the complex and interconnected story of how our universe became the rich, diverse expanse we see today. It is a story that began with the birth of the first stars and continues to unfold in the galaxies, nebulae, and planetary systems that dot the cosmos. The first second after the Big Bang was an extraordinary and tumultuous period in the history of the universe. This time, known as the Planck epoch, spanned the very first moments from the birth of the universe to the end of the first second, encompassing a series of dramatic transformations. Initially, the universe existed as a singular, infinitely hot and dense point, filled with an extremely high-energy state of matter and radiation. The temperature was so high that no conventional matter could exist in stable forms. Instead, particles such as quarks and gluons existed in a fluid-like state known as quark-gluon plasma. The early universe was a chaotic and violent place, with particles constantly annihilating each other and converting between matter and energy in a cycle that seemed to have no end. As the universe expanded, it began to cool rapidly, and with this cooling came the separation of fundamental forces. The four known forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, gradually emerged from an initially unified state. These forces began to govern the behavior of particles, which were still in an extremely energetic state. During this time, which is often referred to as the quantum era, the universe was a place of extreme conditions, where the laws of physics as we understand them today were in their infancy. Despite this chaos, the foundations for everything that would come to be, atoms, galaxies, stars, were being laid down. Around 1 microsecond after the Big Bang, the universe had cooled enough for quarks to combine and form protons and neutrons, the building blocks of atomic nuclei. These particles came together in the first moments of what is called Big Bang nucleosynthesis, a process that occurred within the first few minutes of the universe's existence. During this brief but crucial period, the first light elements, primarily hydrogen and helium with trace amounts of lithium, were formed. These elements became the raw material for everything that would follow, providing the fuel for the formation of the first stars and galaxies. By the end of the first second, the universe had expanded and cooled sufficiently to allow electrons to combine with protons, forming neutral hydrogen atoms in a process known as recombination. At this stage, the universe was no longer a hot, dense plasma. It had transitioned into a state where matter could finally begin to coalesce into the first atoms. This transition set the stage for the formation of the first stars and galaxies, and ultimately, the universe we observe today. It is hard to overstate the importance of this early period, as it laid the groundwork for the complex, structured cosmos we inhabit, a cosmos rich with stars, galaxies, and the possibility of life. Yet one of the most profound mysteries in cosmology remains unsolved: the apparent imbalance between matter and antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe a universe dominated by matter with very little antimatter in sight. Matter, composed of particles such as protons and electrons, has its counterpart in antimatter, which consists of antiparticles like antiprotons and positrons. If the universe had produced these in equal amounts, they would have annihilated each other upon contact, leaving only radiation behind. This would have resulted in a universe devoid of any substantial matter. Yet, the universe we see today is filled with matter, creating a cosmic mystery that has puzzled scientists for decades. To explain this discrepancy, researchers have turned to the concept of baryogenesis, the process by which matter was generated in the early universe to account for the excess of matter. Baryogenesis suggests that certain conditions in the early universe favored the production of baryons, particles like protons and neutrons, over antibaryons. These conditions must have occurred during the first few seconds after the Big Bang. Experimental observations have suggested that some physical processes may have exhibited a preference for matter-producing interactions. One key example is CP violation, a phenomenon in which the laws of physics treat matter and antimatter differently under specific conditions. In reactions involving particles and their antiparticles, the laws of physics sometimes favor one over the other, leading to an imbalance. While CP violation has been observed in certain particle decays, it appears to be insufficient to explain the full extent of the matter dominance in the universe. This leaves open the possibility that additional factors or unknown physical processes may have been at play in the early universe, contributing to the matter-antimatter asymmetry. The question remains one of the most intriguing challenges in modern cosmology and particle physics, driving ongoing research and exploration into the fundamental nature of our universe. The universe, in all its vastness, holds within it mysteries that continue to baffle scientists and challenge our understanding of reality. One such enigma is the matter-antimatter asymmetry, the reason why the universe is predominantly made up of matter rather than antimatter. At the heart of this mystery lies a concept known as inflation, an event that might have occurred in the very early moments of the universe, where it expanded at a rate faster than the speed of light. The inflationary period could have played a pivotal role in shaping the universe's matter-dominant nature. Yet, the mechanisms that created this imbalance between matter and antimatter are still unclear, and they remain an active field of research. Understanding why matter outweighs antimatter in our universe could hold the key to unraveling some of the deepest secrets of the cosmos. It might lead us to new, yet undiscovered particles, forces, or interactions that govern the intricate dance of particles at the fundamental level. Each step forward in this quest reveals more about the complexity of the universe itself, as well as the origins of reality as we know it. The questions surrounding this matter-antimatter asymmetry are not just abstract concepts. They point toward a profound understanding of the laws that govern the universe and the forces that shape its very fabric. Another major cosmic mystery is the elusive nature of dark matter, which constitutes around 25% of the universe's total mass energy content. Despite its massive contribution to the cosmos, dark matter cannot be observed directly through electromagnetic radiation, such as light. Instead, its existence is inferred through its gravitational influence on visible matter and the structure of the universe at large. Without dark matter, galaxies would not be able to rotate in the way they do. If they did, they would simply tear themselves apart. This discrepancy led scientists to propose that some unseen mass, now known as dark matter, is providing the necessary gravitational pull to hold galaxies together. The exact nature of dark matter, however, remains one of the most significant unresolved puzzles in astrophysics. Several candidates have been proposed to explain its mysterious presence. One prominent theory suggests that dark matter might be composed of weakly interacting massive particles, WIMPs, hypothetical particles that have mass and interact through the weak nuclear force and gravity. Because these particles interact only weakly with ordinary matter, they are incredibly difficult to detect. Researchers are actively working on experiments aimed at directly observing WIMPs or their byproducts, but as of now, none have been conclusively identified. Another contender for dark matter is the axion, a hypothetical, ultralight particle predicted by certain theories of particle physics. Axions would be generated by quantum chromodynamics, the theory that explains the strong interactions between particles like quarks and gluons. If axions exist, they could help account for the missing mass in the universe, while simultaneously solving some unresolved puzzles in particle physics. However, like WIMPs, the detection of axions remains elusive. Despite the challenges, the search for dark matter continues with vigor. The presence of dark matter has profound implications for the large-scale structure of the universe. It acts as a scaffold around which galaxies and other cosmic structures form, influencing their distribution and behavior. If dark matter were absent, the arrangement of galaxies would be drastically different. In essence, dark matter shapes the cosmos in ways we are only beginning to understand. As scientists develop more sophisticated instruments and experiments, the hope is that one day dark matter's true nature will be uncovered. One of the more speculative and intriguing ideas that have emerged from studies of dark matter is the concept of shadow galaxies, galaxies made entirely of dark matter. Traditional galaxies are composed of visible matter, stars, dust, and of course, dark matter. However, the idea of shadow galaxies proposes a structure that exists solely within the realm of dark matter, without any visible components like stars. These hypothetical entities could form in regions of space where dark matter is especially concentrated. Though they would have a similar gravitational influence as normal galaxies, shadow galaxies would be entirely invisible to conventional telescopes. The very idea that such galaxies could exist is a testament to the deep complexity and hidden wonders of the universe. In theoretical terms, Shadow galaxies could form through the gravitational collapse of dark matter in areas where ordinary matter is sparse. These structures would not emit light, absorb radiation, or interact with regular matter in any detectable way, making them nearly impossible to observe directly. Current astronomical techniques rely heavily on detecting electromagnetic radiation from stars and other visible matter, meaning that the search for shadow galaxies relies on indirect evidence. This could include detecting gravitational effects that suggest the presence of additional mass without observable matter. While no direct evidence of shadow galaxies has been found yet, the concept remains a fascinating area of ongoing research. In parallel to the quest for understanding dark matter, another cosmic mystery has captured the attention of astronomers: fast radio bursts, FRBs. These extremely brief but immensely powerful bursts of radio waves were first discovered in 2007. They last only a few milliseconds, yet during this brief period, they release more energy than the sun does over several days. The origins of these bursts, which come from distant galaxies, are still not fully understood, and their sudden appearance has sparked a great deal of scientific curiosity. Several theories have been proposed to explain the origins of FRBs. One leading hypothesis suggests that these bursts are the result of magnetars, highly magnetized neutron stars. These stars possess magnetic fields that are billions of times stronger than the Earth's, and they can experience violent outbursts known as starquakes, which release enormous amounts of energy in the form of radiation, including radio waves. According to this theory, when a magnetar undergoes such a violent event, it sends out a burst of radio waves that can travel across vast intergalactic distances, where they are detectable by astronomers. The discovery of a repeating fast radio burst from a magnetar in our own galaxy has provided support for this hypothesis. However, magnetars are not the only potential cause of FRBs. Another possibility is that they could be the result of neutron stars colliding. Neutron stars are the remnants of massive stars that have gone supernova, and when two of these dense objects spiral toward each other and eventually collide, the event can release an immense amount of energy. Such a cataclysmic collision would likely produce powerful bursts of electromagnetic radiation, including radio waves that resemble the characteristics of FRBs. As scientists continue to explore these cosmic phenomena, the mysteries of dark matter, shadow galaxies, and fast radio bursts only deepen, pushing the boundaries of our knowledge and challenging us to look further into the unknown realms of the universe. With every new discovery, the universe reveals more of its profound complexity, reminding us that there is still so much left to uncover in the vast, uncharted expanse of space. Some scientists have also proposed a connection between fast radio bursts, FRBs, and exotic astrophysical phenomena, such as interactions involving black holes or even phenomena linked to cosmic inflation. These bursts, with their unpredictable origins and immense energy, present a vast array of potential sources, highlighting the intricate complexity of the universe. This complexity presents a significant challenge for researchers, who must devise innovative methods to detect and study these enigmatic signals in greater detail. The ongoing quest to understand the nature of FRBs goes beyond simply explaining these high-energy events. It holds the promise of transforming our broader understanding of the universe itself. By investigating the characteristics and distribution of these bursts, astronomers gain a unique window into several profound cosmic phenomena. For example, their study can reveal crucial insights into the evolution of galaxies, the structure and behavior of the intergalactic medium, and the physics of extreme high-energy environments. As technological advancements continue to evolve, the mystery of fast radio bursts will only deepen, opening new layers of knowledge about the cosmos and its fundamental workings. One particularly intriguing area of research is the formation of supermassive black holes in the early universe. These colossal objects found at the centers of most galaxies, including our own Milky Way, have sparked intense scientific curiosity. Recent observations have uncovered supermassive black holes with masses equivalent to millions or even billions of times the mass of our Sun. Remarkably, many of these supermassive black holes existed less than 1 billion years after the Big Bang. Understanding how such massive objects could form so quickly in the early universe presents a profound puzzle. one that challenges our current theories about cosmic evolution. One prevailing theory suggests that these supermassive black holes may have originated from the direct collapse of massive clouds of gas in the early universe. Following the formation of the first stars and galaxies, dense regions of gas could collapse under their own gravity, forming massive seeds that eventually grew into full-fledged black holes. This process might have occurred more efficiently in the high-density conditions of the early universe, where gas was abundant and could cool rapidly. In these early stages, black holes could form directly, without the need for intermediate stellar formation. Alternatively, the growth of supermassive black holes could have involved the merging of smaller black holes or rapid accretion of matter onto an initial seed black hole. This scenario posits that smaller black holes, potentially formed from the remnants of the first generation of massive stars, could collide and merge over time, gradually leading to the formation of supermassive black holes. As these black holes gathered mass from their surroundings, either from nearby gas and dust or from additional mergers, they could accelerate their growth exponentially. The environment of the early universe played a crucial role in these processes. The rapid expansion and cooling that followed the Big Bang led to the formation of dense molecular clouds, environments that could have facilitated black hole formation and growth. Moreover, intense star formation rates and active galactic nuclei during this period may have provided additional fuel for black holes, allowing them to grow at astonishing rates. Observations of distant quasars, which are powered by supermassive black holes, provide valuable data that challenges existing models and theories about galaxy formation and evolution. These observations continually reshape our understanding of the universe's early epochs, bringing us closer to unlocking the mysteries surrounding the formation of these cosmic giants. The mystery of how these supermassive black holes could form so early in the universe exemplifies the intricate and dynamic nature of cosmic evolution. Their early existence reflects the complex processes that shaped the cosmos in its infancy, and studying them continues to inform our broader understanding of the universe's development. Around 2.4 billion years ago, Earth underwent a dramatic shift known as the Great Oxidation Event, GOE. This event marked a crucial turning point in the history of our planet, the moment when molecular oxygen began to accumulate in significant quantities in the Earth's atmosphere. The primary driver of this transformation was the evolution of photosynthetic microorganisms, particularly cyanobacteria. These microscopic organisms harness the energy of sunlight to convert carbon dioxide and water into organic matter, releasing oxygen as a byproduct. Before this event, Earth's atmosphere contained very little free oxygen, which posed serious limitations on the types of life that could thrive. The rise of cyanobacteria triggered a slow yet profound increase in atmospheric oxygen. Over several hundred million years, these microorganisms spread across the oceans, gradually altering the chemical composition of Earth's atmosphere. The oxygen released during this process reacted with dissolved iron in the oceans, forming substantial deposits of iron oxide, which are visible today in the geological record as banded iron formations. These deposits stand as enduring evidence of Earth's dramatic shift in atmospheric conditions. The biological consequences of the GOE were equally transformative. As oxygen accumulated in the atmosphere, it became toxic to many of the anaerobic organisms that had previously dominated Earth's ecosystems. However, this rise in oxygen eventually paved the way for the evolution of aerobic organisms, life forms that could utilize oxygen to produce energy more efficiently than their anaerobic counterparts. The advent of aerobic respiration marked the beginning of a new chapter in life's evolution, enabling the emergence of more complex organisms and setting the stage for the development of multicellular life. The Great Oxidation Event also had a profound impact on Earth's biosphere, setting the course for the eventual emergence of terrestrial life. By altering the planet's atmosphere and enabling more complex metabolic processes, this event initiated a cascade of evolutionary changes that continue to shape the trajectory of life on Earth. Studying this pivotal moment in Earth's history enhances our understanding of the intricate interplay between biological processes and environmental transformations. The GOE serves as a reminder of the dynamic nature of our planet and the interconnectedness of its biological and atmospheric systems. The missing baryon problem represents a significant puzzle in modern astrophysics. Baryons, particles such as protons and neutrons, are the fundamental building blocks of atoms, and they make up the majority of the mass we observe in the universe. Current measurements suggest that baryonic matter should account for nearly 1/6 of the total energy density of the universe. However, when scientists attempt to account for all the visible baryonic matter in galaxies and other cosmic structures, a substantial portion remains unaccounted for. This discrepancy has given rise to the term missing baryons. One plausible explanation for the missing baryons is that a large portion of this matter exists in regions of the universe that are difficult to detect. A significant portion of baryonic matter may reside in the hot diffuse gas found between galaxies, an area known as the intergalactic medium. While this gas is composed of baryons, it is often too diffuse and too hot to emit light that is easily observable. Recent advancements in astronomical techniques, such as X-ray observations, have begun to uncover this hidden baryonic matter. These observations suggest that the missing baryons may indeed be lurking in the intergalactic medium, providing a possible solution to one of the universe's most perplexing mysteries. As researchers continue to refine their observational tools and techniques, they are gradually piecing together the puzzle of missing baryons, bringing us closer to a complete understanding of the matter that makes up the universe. The formation of large-scale structures in the universe has undoubtedly played a significant role in the distribution of baryons, those elusive building blocks of matter that are essential to understanding the cosmos. Over time, these baryons, which we often think of as being tightly bound within stars or galaxies, might have been expelled into the vast reaches of space, scattered and dispersed through the powerful winds generated by star formation and supernova explosions. The impact of these cosmic forces is profound, as they would have sent baryons tumbling out of galaxies and into the surrounding emptiness, leaving them in forms that are not immediately detectable. Rather than being bound tightly to stars or galaxies, these particles could be floating freely, hidden in regions of space that we can't easily observe. This dispersion of baryons raises questions about what we cannot see in the universe, forming what is known as the missing baryon problem. This mystery of where these missing baryons are hiding continues to captivate cosmologists. The discovery of these hidden baryons would not only solve a piece of the puzzle about the composition of the universe, but it would also offer new insights into the evolution of cosmic structures, from the birth of galaxies to their ultimate fate. As scientists delve deeper into the study of the universe, the search for these elusive baryons reminds us just how much there still is to uncover in our cosmic landscape. The more we learn, the more we realize how much is yet to be discovered. Shifting from the hidden matter to the strange behavior of light itself, we encounter one of the most mind-bending consequences of gravity: gravitational lensing. This phenomenon, first predicted by Einstein's theory of general relativity, is a reminder that gravity doesn't just pull objects together, it bends the very fabric of space and time. When light from a distant star or galaxy passes near a massive object, such as a galaxy cluster, the massive object warps the space around it, causing the light to bend. To our eyes, this may seem like a distortion or visual trick, but it's actually a fundamental result of the way light follows the curves of space-time. In essence, what we perceive as a straight line in space is altered by the gravitational fields of large objects, creating astonishing visual effects. Gravitational lensing can be broken down into three main categories: strong lensing, weak lensing, and microlensing. Strong lensing occurs when the gravitational field is particularly intense, causing dramatic visual distortions. In the most extreme cases, it can create multiple images of a distant object or even form complete rings around a massive object, known as Einstein rings. This occurs when the light source, the lensing mass, and the observer are almost perfectly aligned. Weak lensing, by contrast, produces more subtle distortions in the background galaxies, and astronomers can use these distortions to map the distribution of dark matter in the universe. Finally, microlensing happens when a smaller object, like a planet, passes in front of a distant star. The gravitational field of the planet bends the light from the star, allowing researchers to detect bodies that would otherwise be invisible. The implications of gravitational lensing go far beyond merely observing these visual effects. It is an invaluable tool for astronomers, allowing them to study the mass of galaxies and galaxy clusters. This, in turn, helps refine our understanding of both visible and dark matter, two of the most mysterious components of the universe. Even more astonishing, gravitational lensing can aid in the detection of exoplanets. When a planet passes in front of a star, it may amplify the light from the star in such a way that astronomers can detect it, even though the planet itself might be too small and faint to see directly. By continuing to study gravitational lensing, we gain a clearer picture of the universe's structure and evolution, while also revealing the fundamental ways that gravity shapes the cosmos. Beyond the bending of light, the concept of traveling at the speed of light challenges our understanding of physics itself. According to Einstein's theory of relativity, no object with mass can reach the speed of light. As an object moves faster and faster, its mass increases, meaning that it requires more and more energy to continue accelerating. To reach the speed of light, an object would need an infinite amount of energy, something that is not possible with our current understanding of physics. This creates a natural speed limit in the universe, making it impossible for objects with mass, such as humans, to travel at light speed. Even if we could somehow imagine traveling at the speed of light, the experience would be utterly beyond our comprehension. For massless particles like photons, which do travel at the speed of light, time itself seems to cease to exist. From the perspective of light, the journey from one point in space to another is instantaneous, obliterating any sense of past or future. In this state, everything occurs simultaneously, as if all moments in time exist as one. Moreover, as an object approaches the speed of light, space itself begins to warp. This phenomenon, known as length contraction, causes distances in the direction of travel to shorten. As a result, destinations that were once far apart may appear to come closer together, defying all normal experiences of space and time. This distortion of reality, while theoretical, suggests that the speed of light is not just a barrier to travel, but a profound transformation of the way we perceive the universe. These ideas stretch the very fabric of our understanding, challenging the limits of science and the way we view the cosmos. Yet, as we probe deeper into the mysteries of the universe through gravitational lensing, dark matter research, or even the speed of light itself, we are reminded of the vastness and complexity of the cosmos. The more we learn, the more we realize just how much we still have yet to discover. However, this contraction comes with tremendous energy requirements and logistical difficulties that, at present, are insurmountable. Traveling at light speed, while a concept rooted in theoretical speculation, opens the door to a deeper exploration of the fundamental laws of physics that govern our universe. This pursuit not only challenges our current understanding, but also raises profound questions about the very nature of time, space, and reality itself. It urges us to reconsider the boundaries of human experience, questioning our place in the cosmos. Though our human limitations may confine us, the boundless curiosity and relentless thirst for knowledge propel us forward in our quest to uncover the intricate fabric of the universe. One of the most captivating and mind-bending consequences of Einstein's theory of relativity is time dilation, a phenomenon with profound implications for space travel. As an object approaches the speed of light, time for that object slows relative to an observer at rest. This means that astronauts traveling at high velocities would experience time quite differently than people on Earth. For instance, a few years might pass for the travelers, while decades could elapse for those remaining behind. This time discrepancy was powerfully demonstrated in the famous thought experiment known as the twin paradox. In this scenario, one twin embarks on a journey into space, traveling at a velocity close to the speed of light, while the other stays on Earth. Upon the return of the traveling twin, they would find that they have aged significantly less than their earthbound counterpart. This time dilation is a striking reminder of the strikingly different realities that can unfold as one approaches relativistic speeds. It illustrates how such travel can create radically divergent experiences, not just for the travelers, but for entire timelines. In practical terms, time dilation presents formidable challenges for long-duration space missions. If humanity were ever to explore distant galaxies or venture through interstellar space, astronauts would need to contend with the effects of time dilation as they journeyed at high speeds for extended periods. For any crewed spacecraft traveling into deep space, careful planning would be essential to mitigate the psychological and social effects of prolonged isolation, as well as the shifting relationship between the crew's perception of time and Earth's temporal flow. As we set our sights on future aspirations for space travel, time dilation underscores the need for the development of innovative propulsion systems capable of approaching relativistic speeds. It raises fundamental questions, not only about the nature of time itself, but also about how humanity might adapt to the profound implications these relativistic effects have on aging, human biology, and our perception of time. As the vastness of space stretches across the fabric of existence, it brings into sharp focus the idea that exploring the cosmos irrevocably alters our relationship with the passage of time. In the same vein, gravitational waves represent another revolutionary breakthrough in our understanding of space and time. These ripples in the fabric of space-time are caused by the acceleration of massive objects, such as colliding black holes or neutron stars. Predicted by Einstein's general theory of relativity, gravitational waves travel at the speed of light, carrying vital information about their origins and the nature of the objects that produce them. When two massive bodies orbit one another and eventually merge, they create disturbances in spacetime that propagate outward, akin to ripples in a pond created by a stone. Detecting these waves presents a daunting challenge, as their effects on spacetime are incredibly subtle. The minute distortions in distance caused by a passing gravitational wave can be as small as a fraction of a proton's diameter. To detect such tiny changes, scientists rely on highly sophisticated instruments like interferometers. The most prominent of these is the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. LIGO consists of two massive facilities in the United States, each with arms extending several kilometers arranged in an L shape. It employs lasers and mirrors to measure how light beams are altered when a gravitational wave passes through. As the wave passes, it stretches one arm of the L shape while compressing the other, which changes the distance the light travels, causing a shift in the interference pattern. By analyzing these shifts, scientists can infer the properties of the gravitational waves, such as their amplitude, frequency, and the events that generated them. Since the first detection of gravitational waves in 2015, numerous cosmic events have been observed, providing unprecedented insights into the universe's most violent and energetic processes. This groundbreaking discovery not only confirmed aspects of Einstein's general theory of relativity, but also revolutionized the way we observe the cosmos. Gravitational waves provide a unique glimpse into events that would otherwise be invisible, such as black hole mergers and neutron star collisions. They open up a new frontier in astrophysics, allowing us to study the universe in ways never before possible. Meanwhile, wormholes, fascinating theoretical constructs in the field of physics, also inspire much discussion and speculation. Wormholes arise from the equations of general relativity and are essentially hypothetical tunnel-like structures that could connect two distant points in spacetime. If such structures exist, they could potentially offer shortcuts through the universe, making faster-than-light travel a possibility. The very concept of wormholes, though, presents numerous scientific challenges and profound questions. The idea of a traversable wormhole suggests that one could enter a wormhole at one end and emerge at the other almost instantaneously. This tantalizing possibility has captured the imagination of scientists and science fiction enthusiasts alike. However, for a wormhole to remain stable enough for such travel, theoretical models suggest that it would require exotic matter with negative energy density, something that has yet to be discovered and remains purely speculative. Moreover, the stability of wormholes is another significant hurdle. Many models propose that wormholes would collapse almost immediately, rendering them useless for any kind of transportation. Even if a stable wormhole could be found or created, it would raise paradoxical questions about causality and time travel. The implications for our understanding of history and the universe itself are mind-boggling, as any disturbances in the timeline could lead to inconsistencies in reality itself. Despite these challenges, the concept of wormholes serves as a catalyst for exploring the very nature of space-time, inspiring scientists to push the boundaries of general relativity and quantum mechanics. It encourages innovative ideas and fresh approaches to understanding the universe and our potential ability to navigate it. Though wormholes may remain elusive, their potential for faster-than-light travel continues to fuel speculation and drive the frontiers of theoretical physics. The expansion of the universe also provides profound insights into the nature of space and time. Referred to as the Big Bang, the universe began from an extraordinarily hot and dense state, expanding rapidly ever since. This expansion is not simply a movement of galaxies through space, but rather the stretching of space itself. As a result, the relationship between distance and time becomes increasingly complex and dynamic, influencing the very fabric of space-time itself. As the universe continues to expand, galaxies and cosmic structures are gradually moving away from each other. This phenomenon is described by Hubble's law, which states that the farther away a galaxy is, the faster it appears to be receding. However, this doesn't mean the galaxies are moving through space. Rather, it is the space between the galaxies that is expanding. This revelation complicates the way we perceive distances in the universe, introducing a new layer of complexity to our understanding of time and space on cosmic scales. Additionally, the expansion of the universe leads to the concept of cosmological redshift. As light travels through the expanding universe, its wavelength stretches, causing it to shift toward the red end of the spectrum. This redshift provides essential information about the rate at which objects are receding from us and enables astronomers to track the expansion of the universe over time. It serves as a critical tool in determining the age of the universe and understanding the forces that influence its growth and evolution. Together, these discoveries, time dilation, gravitational waves, wormholes, and the expanding universe, fundamentally reshape our understanding of the cosmos. They challenge conventional thinking, provoke new questions, and inspire an insatiable curiosity that drives humanity's eternal quest to understand the universe in all its vast and mysterious complexity. The universe is in constant flux, with its vast expanse governed by the intricate relationship between space-time, mass, and energy. At the core of this dynamic lies the expansion of the universe, influenced by an enigmatic force known as dark energy. This mysterious presence drives the acceleration of the universe's growth, altering the structure and evolution of space-time on the largest scales. As research into dark energy advances, it not only deepens our understanding of the universe's expansion, but also opens up profound questions about its ultimate fate. Every new discovery reshapes our perception of the cosmos, urging us to reconsider the nature of space, time, and our place within this vast and ever-changing universe. This expansion of space-time is far from simple. The geometry of the cosmos and its continued growth are intertwined with the properties of dark energy. As scientists study these forces, they uncover the many layers of complexity in the fabric of space-time. These findings are more than just theoretical. They are fundamental to answering the deepest questions about the universe. In time, as our comprehension of the universe's expansion continues to evolve, it transforms our understanding of reality itself, forcing us to reevaluate how we exist within the cosmos. The prospect of traveling faster than light has captured the imagination of many, offering tantalizing possibilities for the future of exploration. However, this idea poses significant challenges to our understanding of physics, specifically according to Einstein's theory of relativity. As an object approaches the speed of light, its mass increases. This means that achieving faster than light speeds would require an unimaginable amount of energy, effectively making it impossible for any object with mass to exceed this cosmic speed limit. However, entertaining this hypothetical scenario unveils fascinating consequences that challenge the foundations of physics. One of the most profound implications is the potential violation of causality, the principle that cause must always precede effect. If faster than light travel were possible, events could be experienced in reverse order. A traveler moving faster than light might arrive at a destination before they left, leading to paradoxes like the well-known grandfather paradox, where actions in the past could alter or negate the present. These paradoxes would fundamentally disrupt our understanding of time and reality, forcing us to reconsider how we interpret the flow of events. Another intriguing concept associated with faster-than-light travel involves tachyons, hypothetical particles that are theorized to travel faster than light. These particles would have imaginary mass and could, in theory, enable instantaneous communication across vast distances. Yet, despite their theoretical existence, tachyons have never been observed or detected in any experimental setting, making them purely speculative at this point. The notion of tachyons raises intriguing questions about how information could be transmitted faster than light without violating the principles of causality. If faster-than-light travel could somehow be achieved, it could open entirely new ways of exploring the universe. Concepts such as warp drives and wormholes could potentially create shortcuts through space-time, linking distant points in the cosmos. However, these ideas remain firmly in the realm of science fiction for now, facing numerous scientific and technological hurdles that have yet to be overcome. Nevertheless, the very possibility of faster-than-light travel continues to inspire deep contemplation and motivates further investigations into the laws governing space and time. The quest to understand the nature of time is inextricably linked to gravity. Einstein's theory of general relativity predicts that the flow of time is influenced by gravitational fields, with time passing more slowly in stronger gravitational environments. This phenomenon, known as gravitational time dilation, demonstrates the fundamental connection between gravity and the passage of time. The closer an object is to a massive body, like a planet or star, the more time slows for it relative to someone farther away. For instance, imagine two clocks, one situated at sea level and another on top of a mountain. Due to the stronger gravitational field at sea level, the clock at the lower elevation will tick ever so slightly slower than the one at a higher altitude. Although this effect is imperceptible in daily life, it has been measured with high precision using atomic clocks. Gravitational time dilation also has practical applications, especially in systems like GPS, where such small discrepancies must be accounted for to maintain accuracy. In more extreme conditions, such as near a black hole, the effects of gravitational time dilation become even more dramatic. As objects approach the event horizon, the point beyond which nothing can escape the black hole's gravitational pull, time slows down drastically for them compared to observers farther away. This creates a surreal scenario where time can be stretched to its limits, illustrating how gravity can warp the very fabric of space-time. These concepts challenge our conventional understanding of time as a linear and unchanging constant. Instead, they reveal how time is deeply affected by the presence of mass and the curvature of space around it. As our exploration of the universe progresses, the ways in which gravity shapes the passage of time will continue to illuminate the complex interactions that govern the cosmos. At the heart of Einstein's general theory of relativity lies the understanding that mass and energy are not distinct entities, but rather interconnected. Both mass and energy act as sources of gravitational influence, causing the fabric of space-time to curve around them. This curvature is what dictates how objects move through space and experience time. Einstein's famous equation, E = mc squared, encapsulates this relationship, showing that energy and mass are interchangeable. A small amount of mass can be converted into a vast amount of energy, and vice versa. This fundamental equivalence means that both massive objects, like planets and stars, and concentrated forms of energy, such as radiation, contribute to the curvature of space-time. For example, the mass of a star causes space-time to curve, and this curvature dictates how planets orbit around it. In this sense, gravity is not a force in the traditional sense, but an effect of the curvature of space-time itself, guiding the movement of objects. The relationship between mass, energy, and space-time curvature also helps explain phenomena such as gravitational lensing, where light from distant stars or galaxies is bent as it passes near a massive object. This bending of light reveals the hidden structures of the universe, showing how the fabric of space-time influences not only physical matter, but also the very paths that light takes across the cosmos. The evolution of the universe is also shaped by the interplay of mass, energy, and the curvature of space-time. The energy density of the universe, including the mysterious force of dark energy, drives the expansion of the cosmos. As the universe evolves, the curvature of space-time is constantly altered, influencing the behavior of celestial bodies and the overall structure of the universe. This deep connection is foundational to our understanding of the cosmos and remains central to the study of physics as we continue to unravel the mysteries of existence. Among the most extreme and fascinating objects in the universe are black holes. These cosmic anomalies form from the remnants of massive stars that have collapsed under their own gravity. The result is an incredibly dense core, creating a gravitational field so strong that not even light can escape once it crosses the event horizon, the boundary that marks the point of no return. Black holes warp the fabric of space-time around them, bending the very geometry of space. As objects or light pass close to a black hole, their paths are dramatically curved by its immense gravitational pull. The closer an object gets to a black hole, the more extreme this curvature becomes. In some cases, the gravitational forces near a black hole can lead to phenomena such as spaghettification, where objects are stretched and compressed into long, thin shapes due to the intense tidal forces. The impact of black holes on space-time extends beyond their immediate vicinity. The presence of a black hole can influence the motion of nearby stars, gas clouds, and other celestial bodies. Stars in close orbits around supermassive black holes, for example, can exhibit incredibly high orbital velocities, providing astronomers with evidence of the black hole's presence. By studying the gravitational effects of black holes on surrounding objects, scientists can infer their existence and mass, even if the black holes themselves remain hidden from direct observation. Black holes, in their extreme and enigmatic nature, offer a unique window into the workings of the universe. They challenge our understanding of space-time and serve as a reminder of the many mysteries still left to uncover in our quest to understand the cosmos. The study of black holes plays a crucial role in enhancing our understanding of some of the most profound concepts in physics, particularly general relativity. These mysterious cosmic entities, which warp space-time to extreme degrees, push the boundaries of our comprehension of fundamental forces such as gravity, time, and their interactions. The unique conditions surrounding black holes, where gravity becomes so intense that not even light can escape, create a laboratory for testing the very fabric of the universe. As scientists continue to probe the mysteries of these enigmatic objects, they not only expand our understanding of black holes themselves, but also ignite new questions that challenge the foundational laws of physics and the structure of the cosmos. In examining black holes, scientists are forced to confront phenomena that go beyond our everyday experiences, where the behavior of matter and energy defy conventional logic. For example, the event horizon of a black hole represents a boundary where space-time itself is stretched beyond recognition, creating a region of infinite density. The implications of this stretch in space-time are far-reaching, as they suggest a deep connection between gravity and the nature of time itself, forcing us to reconsider the very principles that govern how our universe operates. Moving beyond black holes, the search for life in our solar system also sparks a deep sense of curiosity and wonder. While Earth remains the only known cradle of life, several intriguing places within our cosmic neighborhood may harbor the essential elements required for life as we know it: water, chemical nutrients, and energy sources. Among the most promising candidates for extraterrestrial life are Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. Europa stands out due to its thick icy shell, beneath which lies a vast ocean of liquid water. This subsurface ocean could possess the right conditions for life, particularly when considering the potential for chemical reactions between the ocean and the rocky mantle below. These reactions could provide the chemical building blocks needed for life, making Europa a prime target for astrobiological research. The moon's potential as a habitat for life is one of the driving forces behind missions like NASA's Europa Clipper, which aims to explore this icy world in greater detail. Enceladus, like Europa, also harbors a subsurface ocean beneath its icy exterior. But what makes Enceladus especially intriguing is the discovery of plumes of water vapor and organic molecules erupting from its surface, suggesting the presence of hydrothermal activity deep within the ocean. The combination of liquid water, organic molecules, and energy from hydrothermal vents creates an ideal environment for the possible emergence of life. This exciting possibility has led to scientific missions focused on studying Enceladus's geysers, with hopes of finding more evidence of microbial life. Further out in the solar system, Titan, Saturn's largest moon, presents a very different but equally fascinating environment. Unlike Europa and Enceladus, Titan's surface is not covered in water, but instead features lakes and rivers of liquid methane and ethane. These hydrocarbons, along with Titan's thick atmosphere rich in organic compounds, suggest that Titan could serve as a unique laboratory for studying non-water-based biochemistry. Scientists hypothesize that life could, in theory, arise in such an alien environment using solvents other than water. Titan's atmosphere is rich with organic molecules, and its surface conditions provide a unique opportunity to study the chemistry that could lead to the formation of life, albeit in a form radically different from what we know on Earth. Mars, of course, continues to be the most traditional focus in the search for extraterrestrial life. Past missions have uncovered significant evidence of ancient riverbeds and minerals that suggest water was once abundant on the red planet. Current rovers and orbiters are focused on finding definitive signs of past life, whether microbial or otherwise, particularly in areas that may have once harbored liquid water. Scientists are particularly interested in exploring potential subsurface environments on Mars, where water might still exist in liquid or briny forms, hidden beneath layers of ice or rock. This search for life on Mars, both past and present, continues to fuel our fascination with our neighboring planet, with missions like Perseverance and Curiosity constantly pushing the boundaries of what we know. The study of life beyond Earth challenges our understanding of biology and the conditions necessary for life to thrive. Each of these environments, Europa, Enceladus, Titan, and Mars, offers unique challenges and opportunities, forcing us to rethink what we know about life's potential in the universe. As technology advances and new missions are launched, the search for extraterrestrial life continues to inspire scientists and laypeople alike, encouraging us to expand our view of the cosmos and the conditions that might support life elsewhere. In addition to exploring the potential for life within our solar system, scientists are also increasingly focused on exoplanets, planets orbiting stars beyond our sun. The detection of biosignatures on these distant worlds is a central goal of modern astronomy. Biosignatures are chemical indicators, such as gases or patterns, that suggest the presence of life. These signatures can be detected even across vast distances, thanks to advances in technology like spectroscopy. Spectroscopy allows scientists to analyze the light that passes through an exoplanet's atmosphere, identifying specific absorption lines corresponding to different gases. By studying the light from distant stars, scientists can infer the chemical composition of a planet's atmosphere and search for gases like oxygen, methane, and carbon dioxide, substances that are often produced by living organisms. On Earth, oxygen is primarily produced through photosynthesis, and methane is a byproduct of microbial activity. The simultaneous presence of these two gases on an exoplanet could be a strong indication that life exists or has existed there. This is because in the absence of life, these gases would typically react with one another and would not remain in significant quantities in a planet's atmosphere. This is where the power of telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope comes into play. These instruments are capable of conducting detailed spectral analyses of exoplanets, particularly those that pass in front of their host stars, known as transiting exoplanets. When a transiting exoplanet moves in front of its star, some of the star's light filters through the planet's atmosphere, giving scientists a unique opportunity to capture spectroscopic data. This data can reveal crucial information about the atmospheric composition of the planet, including potential biosignatures. As these observations become more advanced and more planets are studied, our understanding of the potential for life beyond Earth will only deepen, inspiring further exploration of the universe and the search for signs of life elsewhere. Exploration missions to study the moons and planets within our solar system, such as Europa and Enceladus, provide us with invaluable insights into potential biosignatures. These missions are designed to probe subsurface oceans where microbial life could potentially exist, or to analyze the chemical environments that might harbor life. They also serve as comparative examples to guide our search for biosignatures beyond our solar system. Despite the numerous challenges associated with the search for microbial life on distant exoplanets, advancements in technology and observational techniques continue to expand our ability to probe these worlds. As we refine our search strategies, the potential discovery of biosignatures could drastically alter our understanding of life's existence in the universe, offering profound insights into the very nature of life itself. The prospect of finding microbial life on other planets raises fascinating possibilities. Such life could take forms that are vastly different from anything we know on Earth, shaped by the unique conditions of each celestial body. Given the sheer variety of extreme environments found across the universe, extraterrestrial life forms may not resemble terrestrial organisms in any recognizable way. Instead, they could evolve to survive under conditions that we deem inhospitable, such as extreme radiation, freezing temperatures, or unusual atmospheric compositions. Take, for instance, the possibility of microbial life on Mars. The surface conditions there are cold, dry, and exposed to intense radiation. Life on Mars, if it exists, might resemble hardy extremophiles on Earth, like tardigrades or certain bacterial spores. These microbes would have developed thick protective cell walls or biofilms to retain moisture and shield themselves from radiation. They could even exist in dormant states during periods of harsh conditions, only reviving when the environment becomes more favorable. Subsurface aquifers, where liquid water might still be present, could provide a haven for these microbial forms of life. On moons like Europa or Enceladus, which harbor subsurface oceans beneath thick ice layers, microbial life could resemble organisms found in Earth's deep-sea hydrothermal vents. These life forms would likely rely on chemosynthesis rather than photosynthesis, converting chemical energy from mineral-rich waters into sustenance. To survive in such extreme environments, these organisms would need unique biochemical adaptations, such as specialized enzyme systems that enable them to withstand high pressures and freezing temperatures. In stark contrast to Earth, where oxygen is the dominant gas due to photosynthetic organisms, life on other planets with different atmospheric compositions might evolve to utilize alternative metabolic processes. Imagine a planet with a methane-heavy atmosphere. Life forms there might evolve to use methane as their primary energy source, resulting in biochemistry that is completely different from what we observe on Earth. These microbes could display unusual shapes, colors, or structures, depending on how their metabolism interacts with their environment. Beyond carbon-based life, we must also consider the possibility of silicon-based life forms. Silicon shares some chemical similarities with carbon, making it a potential foundation for alien biology. If life on another world is based on silicon, it could manifest in ways that challenge our fundamental understanding of life. The diversity of planetary environments across the universe suggests that if microbial life exists elsewhere, it may appear in forms that stretch the limits of our current definitions of what constitutes life. The search for microbial life encourages a broader perspective on biological possibilities. As we continue to explore planets and moons across the solar system and beyond, the diversity of life forms we might encounter compels us to think more expansively about life's resilience and adaptability in a variety of environments. The exploration of these distant worlds invites us to imagine the potential forms of life that could exist beyond Earth, while simultaneously deepening our appreciation for the diverse organisms that thrive in extreme conditions here on our own planet. However, distinguishing between biological and geological signatures from a distance remains one of the most challenging tasks in astrobiology and planetary science. To make these distinctions, scientists employ a variety of methods and advanced analytical techniques to examine the chemical compositions and spectral signatures of celestial bodies. By analyzing the light reflected or absorbed by a planet's atmosphere or surface, researchers can identify specific absorption lines linked to various chemical compounds. Certain gases, such as oxygen, methane, and ozone, can indicate biological processes since these are typically associated with the metabolic activities of living organisms. The simultaneous presence of both methane and oxygen is particularly intriguing. These gases tend to react chemically and are unlikely to coexist in stable amounts in the atmosphere unless replenished by a biological source. In contrast, geological processes such as volcanic activity can also release gases like carbon dioxide and sulfur dioxide, which could be mistaken for biological signatures. To make sense of these detections, researchers must analyze the surrounding geological context, considering the composition and other features of the region. The presence of certain signatures in specific patterns or concentrations may indicate biological activity rather than geological processes. Additionally, biological signatures are often spatially localized or clustered, in contrast to the more uniform distribution of geological features. For instance, microbial mats on Earth form distinct patterns that can be traced to biological activity. Geological formations, on the other hand, tend to have a more uniform spread. Isotopic ratios also provide valuable insights, as life processes typically favor certain isotopes over others, leaving telltale markers in atmospheric gases or surface materials. With the continuous advancement of space exploration technology, we are increasingly capable of detecting and analyzing potential biosignatures from afar. Spacecraft equipped with sophisticated spectrometers and imaging tools will allow for more detailed examinations of planetary surfaces and atmospheres. The integration of multiple lines of evidence, atmospheric data, geological context, and advanced analytical techniques will help scientists navigate the complex distinction between biological and geological signatures. As our understanding deepens, we'll be better equipped to identify definitive evidence of life beyond Earth. Meanwhile, the prospect of communicating with extraterrestrial intelligence presents its own set of enormous challenges. The vastness of space and the complexities of language and technology make such an endeavor daunting. The closest known star system to Earth, Proxima Centauri, is over 4 light-years away. This means that any signal sent from Earth would take over 4 years to reach this star, creating significant delays in any potential response. In some cases, this could result in communication gaps lasting decades or even centuries. Furthermore, extraterrestrial life forms may have developed entirely different methods of communication, potentially using forms of communication that are unrecognizable to us. They might rely on light, sound in frequencies we can't perceive, or even chemical signals to exchange information. This raises a fundamental question. Even if we receive a signal from another civilization, will we be able to recognize it as communication? And if we do, will we be able to decode its meaning? These challenges underscore the complexity of the search for intelligent life beyond Earth and highlight the many hurdles that must be overcome before we can begin to understand whether we are truly alone in the cosmos. The concept of language, when viewed through the lens of extraterrestrial communication, becomes a vast, complex puzzle that could differ fundamentally across species, each with its own unique way of perceiving and conveying meaning. This difference in linguistic systems, cognitive structures, and communication modes could significantly complicate our attempts to send and interpret messages. Yet it is not just the linguistic barrier that presents challenges. The technological aspect plays a pivotal role as well. Our current methods of signal transmission, such as radio waves and electromagnetic signals, might not be the optimal means for communicating with all forms of intelligent life. Different species, particularly extraterrestrial ones, may have evolved technologies or sensory capabilities so distinct from ours that our signals could be completely incomprehensible or even perceived as mere background noise. Without a shared framework or common understanding of technology, the likelihood of establishing meaningful communication with extraterrestrial civilizations diminishes. The technological gulf between civilizations might be so vast that even with our best efforts, the transmission of clear, interpretable signals could be an insurmountable challenge. But the difficulties don't stop at the technological level. There are deeper, more philosophical questions to ponder. If extraterrestrial civilizations exist, would they even be interested in contacting us? Their motives, if they do indeed have any, could be so alien to our understanding that the very notion of communication might be irrelevant to them. It is possible that advanced extraterrestrial societies might purposefully choose not to engage with humanity, either out of disinterest or a desire to avoid disturbing us. The ethics of communication between civilizations become even more complex in this light, leaving us to wonder if an advanced alien species would choose silence over interaction. This question leads us to a broader contemplation. Could an extraterrestrial civilization deliberately refrain from revealing its presence in order to avoid causing disruption to the natural course of life on Earth? These ethical and philosophical considerations are woven into the fabric of the challenges we face in our quest to establish contact with potential extraterrestrial intelligences. The vastness of these challenges extends beyond technological and philosophical considerations into realms of planetary protection, which plays a critical role in safeguarding other worlds from contamination during our explorations. Planetary protection, in essence, aims to ensure that Earth's life forms do not contaminate extraterrestrial ecosystems and vice versa, to maintain the integrity of scientific research. This proactive approach to safeguarding celestial bodies starts long before any spacecraft is launched. A rigorous planning process, accompanied by stringent sterilization protocols for all spacecraft and equipment, is essential. Every tool, rover, and lander that ventures beyond Earth's atmosphere is carefully cleaned and decontaminated to prevent any Earth-originating microbes or organic material from hitching a ride to another planet or moon. These protocols become even more vital when missions target celestial bodies that could harbor life or support habitable conditions such as Mars or the icy moons of Jupiter and Saturn. Every mission is assessed and classified based on its potential for contamination, which in turn determines the level of sterilization required. For missions targeting bodies believed to harbor life or where life could potentially exist, the highest degree of sterilization is mandatory. This involves employing advanced techniques such as dry heat sterilization, chemical cleaning agents, and meticulous microbiological testing to ensure that no Earth-based organisms make their way to alien worlds. In addition to sterilization procedures, scientists must also be prepared to monitor the environments of the planets and moons they study. If a spacecraft lands on a celestial body, it is crucial that scientists distinguish between native life forms, if present, and any Earth-originating microbes. This challenge becomes even more significant when considering the return of extraterrestrial samples to Earth. These samples, which might contain traces of alien life or biochemistry, are handled within specially designed containment facilities. These facilities are designed to prevent any biological contamination from escaping and affecting Earth's delicate biosphere. Finally, the international collaboration between spacefaring nations ensures that these planetary protection measures are adhered to. Treaties such as the Outer Space Treaty stress the importance of avoiding harmful contamination of space and other celestial bodies. By fostering global cooperation and following standardized protocols, nations can collectively protect both Earth and the alien environments we seek to explore. The discovery of extraterrestrial life, should it occur, would revolutionize our understanding of biology and the fundamental principles of life. If we were to encounter life forms that evolved independently of Earth, the implications would be profound. It would open up new avenues of research, providing insights into the immense diversity of biological processes that could exist in the universe. The very nature of life as we know it might be challenged, as we discover new biochemical pathways, alternative genetic structures, and different metabolic mechanisms that do not conform to the carbon-based, water-dependent models that dominate our scientific thinking. The discovery of life in extreme environments, such as organisms surviving in the harsh conditions of other planets, would further expand our understanding of life's adaptability. Organisms thriving in extreme conditions like high radiation, freezing temperatures, or immense pressure could prompt us to reassess the limits of life on Earth. Studying these extraterrestrial organisms might inspire biotechnological innovations and provide solutions to environmental challenges that we face here on Earth. Equally intriguing are the evolutionary implications of discovering extraterrestrial life. If organisms exhibit an evolutionary trajectory distinct from life on Earth, we would need to reevaluate our understanding of the forces that drive evolution. Universal factors like environmental pressures, genetic mutations, and evolutionary convergence might take on new meanings. A discovery of life forms with evolutionary histories that diverged from our own would raise crucial questions. Could life, in some form, arise across the cosmos under similar conditions? Or is the path of evolution intrinsically tied to the unique conditions of specific planets? This inquiry would challenge the very assumptions we hold about life's origin and evolution, potentially altering the course of biological science forever. The discovery of intelligent extraterrestrial life could redefine not only our understanding of the cosmos, but also challenge the very foundations of philosophy, consciousness, and human existence. It beckons us to ask, what is intelligence? How do we define consciousness? And where do we fit into the vast, potentially populated universe? These profound questions challenge the very concept of intelligence itself, suggesting that it might not be an exclusively human trait, but perhaps a phenomenon woven into the fabric of biological evolution itself, widespread across the universe or rare and elusive. The possibility of intelligent life elsewhere forces us to reconsider the anthropocentric view that has long placed humans at the center of existence, prompting a reevaluation of what constitutes life and intelligence in ways we've never before imagined. As we look beyond Earth, the existence of extraterrestrial life, particularly intelligent forms, could bring about a seismic shift in how we perceive biology. This revelation could lead us toward a richer understanding of life's complexity, perhaps revealing an unexpected diversity of life forms that would transform our understanding of biology and life's potential. The very definition of habitability, once centered on simplistic ideas of temperature and proximity to stars, has undergone a revolution over the past few decades. When the concept of the habitable zone first emerged, it was thought to be a straightforward region where conditions were just right for liquid water to exist, neither too hot nor too cold, akin to the conditions on Earth. This model assumed that water, in its liquid form, was the key to life, closely mirroring Earth's own conditions. However, as we ventured deeper into the study of planetary science, our understanding of habitability expanded dramatically. It became evident that a planet's distance from its star was merely one of many factors influencing its ability to harbor life. The true potential for habitability involves a variety of elements, including atmospheric composition, pressure, temperature, and geological activity. All of these factors interplay to create conditions that may support or prevent liquid water from existing on a planet's surface. As a result, scientists began to realize that the traditional concept of a habitable zone was far too simplistic. It required a much more nuanced view that incorporated these factors and more. This refined perspective of habitability was further expanded with the advent of new technology and the discovery of exoplanets. Modern instruments, such as the James Webb Space Telescope, have unveiled planets with atmospheres rich in greenhouse gases, hinting at the possibility of life existing beyond the narrow band traditionally considered habitable. These worlds, residing outside the conventional habitable zone, might still harbor conditions capable of sustaining life, perhaps in environments that challenge our preconceived notions of what life can endure. In parallel, research into the icy moons of Jupiter and Saturn has revealed subsurface oceans hidden beneath thick layers of ice. These worlds, once thought to be barren, now present tantalizing possibilities for life forms that might thrive in environments we once thought inhospitable. The definition of the habitable zone continues to evolve as scientists grapple with the diversity of possible conditions that could support life. Some astrobiologists now consider that life might not only exist in environments similar to Earth's, but could also flourish in extreme conditions, such as the deep, dark oceans beneath frozen moons, or even the barren, freezing surface of Mars. This expanded view marks a fundamental shift in our understanding of where life could emerge and how adaptable biological systems can be. The search for extraterrestrial life now includes far more than just identifying planets with conditions resembling those of Earth. It encourages us to explore an expansive range of possibilities, that including alternative life forms that may not adhere to the same biochemistry that governs life on our planet. Moreover, the discovery of extremophiles, organisms that thrive in environments once thought uninhabitable, has been a transformative force in this quest. These organisms live in some of Earth's most extreme conditions: boiling hot springs, acidic waters, deep-sea hydrothermal vents, and even environments that are rich in radiation. Extremophiles have shown us that life can not only survive but thrive under conditions that challenge our understanding of biology. Their existence has broadened our definitions of habitability and sparked new ideas about where and how life could exist elsewhere in the universe. As scientists continue to study extremophiles, they uncover the extraordinary biochemical mechanisms that allow these organisms to adapt to and thrive in environments that would kill most other life forms. This research holds enormous implications for the search for life beyond Earth. Understanding how extremophiles metabolize, reproduce, and survive in extreme conditions could provide critical clues for detecting life elsewhere. For example, scientists now know that certain byproducts of extremophiles' metabolic processes could serve as biosignatures, markers of life, that could be detected on distant exoplanets. These biosignatures could be found in atmospheric gases such as methane or sulfur compounds, or even in the composition of distant planets' soil. In this way, extremophiles not only teach us about life's adaptability, but also guide the design of technologies that could detect signs of life on other worlds. Extremophiles also play an important role in advancing technology, particularly in fields such as biotechnology and astrobiology. The unique properties of extremophiles have already led to advances in areas like bioremediation, where these organisms help break down environmental pollutants, and pharmaceuticals, where their resilience inspires the development of new medical treatments. Additionally, studying extremophiles has contributed to innovations in life detection technologies, such as biosensors capable of identifying life in environments ranging from the boiling depths of the oceans to the frigid, radiation-rich surfaces of distant moons. As humanity prepares for the possibility of discovering extraterrestrial life, we must consider a multifaceted approach that spans science, ethics, and society. Scientific preparation is, of course, paramount. Advancements in telescopes, space probes, and other observational technologies will be crucial in gathering the data needed to identify biosignatures and signs of life on distant planets. Missions to Mars, the icy moons of Jupiter and Saturn, and exoplanet exploration will be instrumental in this process. In parallel with these technological advances, fostering interdisciplinary collaboration will be key. Astrobiologists, planetary scientists, ethicists, and sociologists must come together to navigate the complexities of what it would mean to encounter extraterrestrial life. These discussions will not only improve our scientific preparedness, but also help us understand the profound ethical questions surrounding the discovery of intelligent life forms. What rights would such beings have? How should we treat them? How do we prevent contamination between Earth and extraterrestrial ecosystems? Ethical frameworks will be essential in guiding our interactions with extraterrestrial life. International efforts to establish planetary protection protocols will ensure that we do not contaminate alien environments, while also protecting Earth's biosphere from potential harm. These protocols will need to be established and followed with great care, keeping in mind the broader implications of human interaction with alien worlds. Public engagement also plays a vital role in preparing for such a discovery. Transparency in scientific findings, as well as clear communication about what we may or may not find, will help manage public expectations and mitigate any fear or anxiety that might arise. The discovery of extraterrestrial life could be one of the most profound moments in human history, and preparing both the public and the scientific community for this possibility is as important as any technological advancement we make. In sum, the search for extraterrestrial life is not just an exploration of distant planets. It is a journey that forces us to confront the very nature of life, intelligence, and our place in the universe. The discoveries we make along the way will challenge our assumptions and expand our understanding in ways that are as unpredictable as they are profound. The future of astrobiology, planetary science, and even philosophy depends on how we approach this grand and transformative search. The idea of discovering life beyond Earth has fascinated humanity for centuries, and the growing field of astrobiology offers the potential to change our understanding of life itself. Educational initiatives that focus on the science of astrobiology, alongside the ethical and social implications of finding extraterrestrial life, can deepen public appreciation for the universe's complexity. These initiatives can also encourage a sense of readiness, curiosity, and responsibility. The more we engage with the interdisciplinary aspects of science, communication, and ethics, the better equipped we will be to face the profound possibility of encountering life beyond our planet. The universe is full of potential dangers, many of which remain hidden from view. One such danger lies in the ever-present threat of solar flares. If a massive solar flare were to strike Earth, the impact could be immediate and far-reaching, disrupting the delicate technological and infrastructural networks that modern society relies on. Solar flares are enormous bursts of energy from the sun, releasing radiation across the entire electromagnetic spectrum. These bursts include X-rays, gamma rays, and electromagnetic waves, all of which have the potential to wreak havoc on Earth's technology. In extreme cases, the flare can produce a coronal mass ejection, where a significant volume of solar plasma is expelled into space. If such an eruption were directed toward Earth, the plasma could interact with our planet's magnetic field, sparking a geomagnetic storm. This phenomenon can have widespread consequences. For instance, satellite systems, which are crucial for communication, navigation, and weather monitoring, could be severely impacted. A powerful solar flare could cripple their functionality, causing radio communications to break down and GPS systems to become unreliable. In a worst-case scenario, this could throw transportation systems into chaos. Astronauts aboard the International Space Station or other space missions could also face serious danger. Enhanced radiation exposure would require stringent safety protocols to protect them from harm. On an even larger scale, geomagnetic storms triggered by solar flares could affect Earth's electrical infrastructure. The powerful magnetism could induce fluctuations in electrical currents, damaging transformers and leading to widespread power outages. In fact, such events are not merely theoretical. A solar storm in 1989 caused a blackout in Quebec, leaving millions without power. This serves as a stark reminder of the vulnerability of our modern society to the whims of cosmic phenomena. To mitigate these risks, utilities and energy companies must be prepared with preventive measures, including the installation of protective circuitry and contingency protocols during solar events. Despite the disruption caused by solar flares, the storms can also create stunning visual displays, especially near the Earth's polar regions. The auroras, caused by the interaction of solar particles with Earth's atmosphere, are a mesmerizing sight and a reminder of the sun's power. However, the broader implications of solar activity point to a sobering reality: our reliance on technology that is vulnerable to cosmic events. As we deepen our understanding of solar flares, the importance of closely monitoring solar activity and developing mitigation strategies becomes ever more apparent. While the possibility of solar flares wreaking havoc is unsettling, another, even more daunting, cosmic threat looms: potentially hazardous asteroids. These space rocks, which occasionally pass near Earth, are far more common than most people realize. According to NASA, a potentially hazardous asteroid is any object that comes within about 4.8 million kilometers of Earth's orbit and has a diameter of at least 150 meters. The risk they pose is real, though the vast majority of them pose little to no danger to our planet. Each year, astronomers detect dozens of these objects. As observational technology advances, this number continues to grow. At present, there are thousands of known near-Earth objects, and hundreds of these have been classified as potentially hazardous. Most of these asteroids follow stable orbits that keep them far from Earth's path. However, gravitational forces from other celestial bodies can alter their trajectories, which makes continuous monitoring essential. The frequency with which these objects approach Earth varies, with some making close passes every few years, while others may take centuries to orbit back to a position near our planet. These approaches can range from a few thousand kilometers to millions of kilometers in distance. Although many of these objects are monitored closely, The potential for a large asteroid to impact Earth remains a significant concern. The catastrophic consequences of such an event, while rare, highlight the importance of ongoing observation and risk assessment. In response to these threats, space agencies worldwide have developed robust programs to detect and track near-Earth objects. NASA's Near-Earth Object Observations Program, for example, aims to identify, characterize, and catalog asteroids that might pose a risk to our planet. This surveillance not only helps in identifying potential threats, but also allows scientists to develop strategies to deflect or redirect any dangerous asteroid that may be identified in the future. As if solar flares and asteroids were not enough to consider, there is also the potential threat of gamma-ray bursts. These incredibly energetic explosions in space are the result of events like the collapse of massive stars or the merger of neutron stars. Gamma-ray bursts release highly concentrated beams of gamma radiation that can travel vast distances across the cosmos. If such an event were to occur within just a few thousand light years of Earth, the consequences could be catastrophic. The most immediate effect of a gamma-ray burst directed at Earth would be the ionization of our atmosphere. The intense radiation could strip away large portions of Earth's ozone layer, which serves as a vital shield against harmful ultraviolet UV radiation from the sun. With a diminished ozone layer, the Earth would be exposed to much higher levels of UV radiation, leading to an increase in skin cancer rates and other UV-related health problems. Plant life would also suffer, disrupting ecosystems and destabilizing the balance of life on Earth. The radiation could directly affect biological systems, damaging cellular processes and potentially causing widespread harm to living organisms. Even if life were to survive, the resulting environmental upheaval could cause mass extinctions similar to those that have occurred throughout Earth's history, triggered by drastic changes to the environment. These various cosmic threats, solar flares, potentially hazardous asteroids, and gamma-ray bursts, serve as a reminder of the fragile balance of life on Earth and the many dangers that lie beyond our planet. As we continue to explore and understand the cosmos, the need for vigilance, preparedness, and innovation becomes increasingly clear. The future of our planet may depend on our ability to navigate the complexities of space and protect ourselves from the cosmic forces that surround us. Moreover, the electromagnetic pulse, EMP, generated by a gamma-ray burst could have far-reaching consequences on Earth, inducing widespread electrical disruptions that would ripple through our technological infrastructure. This intense burst of radiation has the potential to trigger failures in power grids, satellite communications, and critical systems, bringing much of modern society to a halt. The impact wouldn't just be limited to immediate disruptions. Recovery efforts would be severely hampered, and the ongoing challenges of navigating a post-burst world would only grow more complex. The chain reaction would cripple essential services, such as healthcare, transportation, and communication, throwing us into a precarious position. Though gamma-ray bursts, GRBs, are rare and typically occur light years away from Earth, their possible effects highlight the vulnerability of our planet in the face of cosmic events. Continued research into these powerful phenomena enhances our understanding, helping us prepare for the unpredictable challenges the universe might throw our way. The burst, though distant in space and time, serves as a reminder of how fragile the systems that underpin our civilization can be, making the study of such cosmic forces all the more crucial. On a different note, the concept of a rogue planet, one that drifts aimlessly through interstellar space without a star to call home, poses another potential risk to our solar system. The odds of such a planet entering our solar system are incredibly slim, but the potential consequences of such an event would be extraordinary. If a rogue planet were to stray close enough to our solar system, its size, trajectory, and speed, in conjunction with the gravitational forces of other planets, would determine the extent of its influence. As this rogue planet approached, its gravitational pull could have profound effects on the orbits of nearby celestial bodies. Depending on the size and velocity of the rogue planet, it could disrupt the orbits of the outer planets, causing chaotic interactions in the gravitational dance between objects in the solar system. These disturbances could send comets, asteroids, and other objects hurtling into the inner solar system, or conversely, eject them into deep space. The risk of collisions between these bodies and Earth would increase dramatically, potentially threatening our planet's safety. In addition to this, a rogue planet might also affect the Oort cloud, a vast, distant region filled with icy bodies that surrounds our solar system. The gravitational force exerted by the rogue planet could disturb the cloud, sending a flood of comets toward the inner solar system. If any of these comets were to collide with Earth, the consequences could be catastrophic, potentially triggering mass extinctions or other planet-altering events. If the rogue planet were to enter the solar system at high velocity, it may not stay for long. It could pass through and exit the solar system, leaving behind only transient gravitational effects that might not be catastrophic. However, in the unlikely event that it collided with a planet, say Jupiter or Earth, the results could be devastating, with potential consequences ranging from massive explosions to the alteration of planetary orbits. Despite the intriguing possibility of a rogue planet entering our solar system, the likelihood of such an event causing significant harm to Earth remains extremely low. Nevertheless, ongoing research into the movements and behaviors of celestial bodies helps scientists anticipate and prepare for the rarest of events. By studying cosmic dynamics, we continue to better understand the forces that shape our universe, ensuring that we're ready for any unexpected challenges that may arise. Cosmic radiation, an ever-present danger for space travelers, also poses significant long-term health risks. Unlike Earth, which is shielded from harmful radiation by its atmosphere and magnetic field, astronauts in space are directly exposed to high-energy particles from outside the Earth's protective envelope. This radiation, primarily composed of galactic cosmic rays, GCRs, and solar particle events, SPEs, becomes a much greater concern on missions beyond low Earth orbit, such as trips to the Moon or Mars. One of the most alarming long-term effects of cosmic radiation exposure is an increased risk of cancer. The high-energy particles can damage the DNA within cells, causing mutations that, over time, may lead to the formation of cancerous cells. Research has shown that prolonged exposure to cosmic radiation significantly heightens the likelihood of developing cancer, particularly for long-duration missions. This risk demands that space agencies prioritize the development of spacecraft with enhanced radiation shielding and carefully select launch windows during periods of lower solar activity to minimize exposure. Beyond cancer, cosmic radiation can also affect the brain and central nervous system. Studies have suggested that the radiation may impair cognitive function, leading to memory loss, diminished spatial awareness, and other cognitive challenges. These effects could seriously compromise an astronaut's performance and decision-making abilities, making it essential for scientists to better understand these risks and develop strategies to counteract them. Moreover, there's growing evidence that cosmic radiation could have detrimental effects on the cardiovascular system. In animal studies, exposure to cosmic rays has shown signs of changes in heart function and blood vessel structure, suggesting that astronauts may face an increased risk of heart disease over time. As human missions continue to venture farther into space, the need for protective measures becomes even more urgent. Researchers are working tirelessly to develop solutions that ensure astronauts' health and safety on deep space missions, ensuring that humanity can continue to explore the cosmos without putting the well-being of our spacefarers at risk. Supernova, one of the most powerful and awe-inspiring events in the universe, have profound and far-reaching effects on their surrounding environment. These stellar explosions, which occur when a massive star runs out of nuclear fuel, expel enormous amounts of energy and matter into the interstellar medium. This release of energy causes shockwaves to travel at incredible speeds, compressing nearby gas and dust and initiating the birth of new stars in regions previously devoid of significant activity. The explosion of a supernova not only releases vast amounts of energy, but also disperses heavy elements, such as carbon, oxygen, and iron, into space. These elements, created through nuclear fusion within the dying star, are essential for the formation of planets and life as we know it. When a supernova occurs, it enriches the surrounding interstellar medium with these building blocks, setting the stage for the creation of new stars and planetary systems. This process plays a crucial role in the chemical evolution of galaxies, allowing for the diversity of elements that form the foundation of life on Earth and elsewhere in the universe. Through the expulsion of these heavy elements, supernovae contribute to the cosmic recycling process, enriching future generations of stars with the ingredients necessary for forming habitable planets. This celestial event not only marks the end of one star's life, but also acts as the catalyst for the formation of new worlds and the continuation of the cycle of life in the universe. The impact of supernovae on the fabric of space is immeasurable, shaping the very dynamics of galaxies and influencing the formation of new cosmic bodies. The cosmic forces at play in the universe are vast, intricate, and often unpredictable, with events such as supernova explosions, the collisions of neutron stars, and solar phenomena significantly shaping the interstellar landscape. Among the most powerful and fascinating of these events is the supernova, a stellar explosion that marks the dramatic end of a massive star's life. However, far from simply being a destructive event, a supernova plays a crucial role in the ongoing cycles of star formation and galactic evolution. As the shockwaves generated by a supernova surge outward into the surrounding space, they clear vast regions of gas and dust. This sweeping action eliminates material that could otherwise obstruct the birth of new stars. As these shockwaves propagate through the interstellar medium, they create enormous bubbles, compressing the gas and dust within them. This compression provides the necessary conditions for the ignition of star formation in neighboring regions. The dense clouds of hydrogen gas, once compressed, collapse under the force of gravity, giving birth to new stars. These supernova remnants, the glowing remnants of the original explosion, often become stellar nurseries where new generations of stars are born. In addition to their role in creating new stars, supernovae also regulate the structure of galaxies. The immense energy released during a supernova explosion has a profound impact on the dynamics of the interstellar medium. It generates pressure that counteracts gravitational collapse in certain areas, preventing an uncontrolled clumping of matter. This delicate balance between expansion and collapse helps maintain the structural integrity of galaxies, influencing their shape, size, and overall evolution over billions of years. In this sense, supernovae are not just destructive forces. They are also vital catalysts for the ongoing cycles of stellar birth, life, and death, contributing to the ever-changing nature of the universe itself. In a similar vein, the collision of two neutron stars near our solar system would be a cataclysmic event of extraordinary magnitude. Neutron stars are the remnants of once massive stars that have undergone supernova explosions. These stars collapse under their own gravity, forming incredibly dense objects primarily composed of neutrons. When two neutron stars merge, they release a burst of energy and gravitational waves, ripples in the fabric of space-time, predicted by Einstein's theory of general relativity. These waves, which travel at the speed of light, distort space itself and can be detected by advanced instruments such as LIGO and Virgo. A neutron star merger would present astronomers with a rare and invaluable opportunity to study these phenomena and further deepen our understanding of fundamental physics. In addition to the gravitational waves, such a merger would also produce an intense burst of electromagnetic radiation, including gamma rays. This gamma ray burst is one of the most luminous events in the universe, capable of releasing more energy in a fraction of a second than the sun will emit over its entire lifetime. If a gamma ray burst were directed toward Earth, the consequences could be catastrophic. The intense radiation would strip away the ozone layer, exposing the planet to harmful ultraviolet radiation. This would pose a significant risk to life on Earth, potentially triggering widespread ecological damage and presenting a serious health threat to living organisms. The aftermath of a neutron star merger is also significant in the creation of heavy elements. Through a process known as R-process nucleosynthesis, the collision of these ultra-dense objects leads to the formation of elements such as gold, platinum, and uranium. These heavy elements are then scattered across the surrounding space, enriching the interstellar medium with the building blocks for future star and planetary systems. If such an event occurred relatively close to Earth, it could influence the chemistry of the region. potentially impacting the formation of new stars and planets in the vicinity. While the likelihood of a neutron star collision near our solar system is exceedingly low, the event serves as a stark reminder of the dynamic, often violent nature of the cosmos. These collisions offer astronomers invaluable insights into stellar evolution, the behavior of matter under extreme conditions, and the origins of some of the heaviest elements in the universe. They highlight the complex interplay of forces that drive the evolution of stars, galaxies, and the very fabric of the cosmos itself. Similarly, phenomena closer to home, such as coronal mass ejections, CMEs, from our Sun, also have profound consequences for both Earth and our technology. A CME is a massive burst of solar wind and magnetic fields that is released from the solar corona into space. These ejections consist of billions of tons of plasma, and they travel at speeds up to 3 million miles per hour. When a CME interacts with Earth's magnetic field, it triggers geomagnetic storms that can disrupt communication systems, GPS signals, and even power grids. The electric currents induced by these storms can overload transformers and lead to widespread power outages, similar to the 1989 blackout in Quebec caused by a CME. As our reliance on technology and electricity grows, the risks associated with CMEs have become a growing concern for utility companies and governments. The high-energy particles in a CME also pose risks to astronauts working outside the protection of spacecraft. These particles can lead to acute radiation sickness or increase the long-term risk of cancer from prolonged exposure. Space agencies actively monitor solar activity to give astronauts ample warning of increased solar activity, allowing them to take necessary precautions and shelter in safe zones within their spacecraft during heightened solar storms. However, CMEs are not entirely destructive. When charged particles from a CME collide with Earth's atmosphere, they produce spectacular auroras near the polar regions. The aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere are natural light displays that occur when the charged particles excite gas molecules in the atmosphere, causing them to emit beautiful colors of light. While CMEs present certain challenges to our technology, they also offer a fascinating glimpse into the dynamic relationship between our planet and the Sun. A phenomenon that could alter Earth's relationship with the Sun in a more profound way is a geomagnetic reversal, also known as a polar shift. This event occurs when the Earth's magnetic poles, the North and South poles, flip. This natural process has occurred multiple times throughout Earth's history, with the most recent reversal taking place approximately 780,000 years ago. While such shifts do not directly affect the planet's axis or climate, they can have significant consequences for life on Earth. During a polar shift, the Earth's magnetic field could weaken temporarily, reducing its protective shield against cosmic radiation and solar winds. This could expose Earth to higher levels of harmful radiation, potentially increasing the risks of skin cancer and other health issues for both humans and animals. Additionally, technological systems that rely on a stable magnetic field, such as satellite operations and aviation systems, could experience disruptions, as navigation data could become unreliable. A polar shift may also influence global climate patterns. Though the magnetic field does not directly affect Earth's climate, changes in the field could influence atmospheric circulation over long periods of time. Alterations in jet streams and weather patterns could lead to more extreme weather events and shifts in climate zones. This, in turn, could create challenges for ecosystems and agriculture, as species would need to adapt to changing environmental conditions. Thus, whether it is the cataclysmic force of a supernova, the cosmic collision of neutron stars, the dynamic phenomena of solar eruptions, or the subtle shifts in Earth's magnetic poles, these events underscore the complexity and interconnectedness of the universe. While many of these processes are far beyond our control, they also provide essential insights into the forces that shape the cosmos, reminding us of the ever-changing and awe-inspiring nature of the universe we call home. As Earth's magnetic field fluctuates, it could significantly impact societal infrastructure that relies on magnetism, including navigation systems across various modes of transport. Aviation, maritime navigation, and even land-based travel may all experience disruptions, especially if these changes are not closely monitored or accounted for. In particular, systems that depend on the Earth's magnetic field, such as GPS and compass-based navigation, could provide inaccurate data depending on the timing of geomagnetic fluctuations. These changes may require significant updates to current technology and navigational protocols in order to maintain safe operations, especially during a geomagnetic polar shift. A polar shift, a natural and gradual process that typically takes thousands of years to unfold, is a remarkable phenomenon that occurs when the Earth's magnetic poles swap places. While this shift is slow, it has the potential to bring about a range of societal disruptions, making it essential to understand its effects well in advance. Although it is a natural process, being prepared for the potential consequences is critical. Research into geomagnetic reversals continues to grow, and scientists are working diligently to understand the long-term impacts such shifts could have on both the environment and technology. A vital area of ongoing scientific investigation revolves around space weather, specifically phenomena like solar flares, coronal mass ejections, and solar winds, all of which can directly affect Earth's magnetic field. These solar activities have far-reaching consequences for both the atmosphere and various technological systems on Earth. Solar flares can disrupt satellite communications, GPS systems, and even power grids, making the tracking and prediction of space weather a priority. The forecasting of space weather relies on a blend of cutting-edge observational technologies and sophisticated data modeling techniques. Satellites, ground-based observatories, and a variety of space instruments are key players in this process. One of the primary institutions involved in space weather forecasting is the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, SWPC, which works alongside NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar and Heliospheric Observatory, SOCHO. These spacecraft capture data across multiple wavelengths, giving scientists detailed images of the sun's activity. By monitoring this solar activity, they can identify patterns and predict when solar storms might strike Earth, allowing for early warnings about the potential dangers of coronal mass ejections, CMEs, or solar flares. This real-time data is then combined with advanced modeling techniques, simulating how solar emissions travel through space and interact with Earth's magnetic field. These numerical models can predict the timing, intensity, and potential impact of space weather events. By analyzing past trends and integrating these insights with current solar activity, scientists can issue more accurate forecasts. Historical data is also crucial for determining the likelihood of future solar events, which allows experts to issue timely advisories to industries dependent on sensitive technologies. These warnings are particularly important for sectors like aviation, satellite communications, and power grid operations. When heightened space weather conditions are forecasted, these industries can take protective measures to mitigate potential damage. For instance, satellite operators may adjust the orbits of their spacecraft, while power grid operators can switch off certain systems to prevent overloading. Early alerts are key to minimizing damage and ensuring operational safety. In parallel, continued advancements in technology and modeling capabilities are enhancing our ability to predict space weather with greater precision. As our understanding of the sun's behavior improves, so does our ability to track and forecast potentially dangerous solar phenomena. These improvements in forecasting methods offer the promise of greater preparedness for the societal and technological impacts of space weather. On a much broader scale, humanity's ambition to terraform Mars, making the planet habitable for human life, has garnered significant interest. The process of terraforming would involve altering the Martian environment to create conditions that support human habitation, including the introduction of liquid water and the thickening of the atmosphere and increasing the planet's surface temperature. Achieving these goals is no small feat, and there are several strategies on the table, each with its own set of challenges. One of the key approaches to warming Mars involves using greenhouse gases such as carbon dioxide, methane, and ammonia. By introducing these gases into the Martian atmosphere, scientists aim to amplify the greenhouse effect, raising the planet's surface temperature. One method might involve releasing carbon dioxide from the polar ice caps, or even developing technologies to manufacture and release gases directly. Another possibility is redirecting asteroids rich in volatile compounds to collide with Mars, releasing gases into the atmosphere over time. This process would gradually thicken Mars' atmosphere and raise temperatures sufficiently to allow liquid water to exist on the surface. Another crucial challenge is addressing the thin Martian atmosphere, which is predominantly composed of carbon dioxide and lacks sufficient pressure to support liquid water. To make Mars more habitable, scientists propose generating a thicker atmosphere by releasing gases that trap heat or by constructing large industrial facilities to maintain the necessary atmospheric components. Additionally, protecting Mars' atmosphere from the solar wind, which erodes it due to the planet's weak magnetic field, is another potential strategy. Artificial magnetic fields could be installed, or other stabilization technologies could be developed to shield the atmosphere from the harsh solar winds. Water is a fundamental component in any terraforming effort, and while Mars has polar ice caps, transporting liquid water to other regions could be essential for creating stable lakes or oceans. Strategies to achieve this might include warming the ice caps to release water vapor or using geothermal energy to melt subsurface ice. As the planet's surface becomes more hospitable, microbial life could be introduced to help enrich the soil and prepare the environment for more complex life forms. The prospect of terraforming Mars is not without its ethical dilemmas. The potential to alter another world raises profound questions about the responsibility we have, particularly if microbial life exists on Mars. Moreover, we must consider the long-term sustainability of such efforts. Ethical concerns must be taken into account as humanity pursues this ambitious goal, ensuring that any steps taken are responsible and considerate of the broader implications. Finally, the idea of establishing a permanent base on the Moon presents its own unique challenges. The Moon's extreme environment, with temperature swings from -250 degrees Fahrenheit during the night to over 200 degrees Fahrenheit during the day, creates a series of hurdles for any human habitation. These drastic temperature fluctuations could pose significant threats to infrastructure and human health. To address this, advanced insulation and thermal management technologies would be required to ensure the safety and comfort of astronauts during extended missions. With advancements in technology and international cooperation, however, humanity's pursuit of a permanent lunar base could become a reality, serving as a critical stepping stone for future exploration and settlement beyond Earth. The Moon, despite being a neighbor to Earth, presents a harsh and challenging environment for human exploration and habitation. It has a very thin atmosphere, which offers minimal protection from cosmic radiation and solar particles. This lack of shielding is a significant concern for astronauts who would be exposed to harmful radiation during extended stays on the lunar surface. Prolonged exposure to this radiation could have severe health implications, such as an increased risk of cancer and other radiation-induced illnesses. To mitigate these dangers, effective protective shielding must be developed. One promising approach is using the Moon's own natural soil, known as lunar regolith, which could be used to design habitats that provide some degree of protection. Additionally, deploying other materials capable of blocking or absorbing radiation will be crucial to ensure astronauts' safety. Developing technologies that can establish a sustainable life support system while maintaining these protective measures is essential for the long-term success of a permanent lunar base. Beyond health risks, logistical challenges pose a major hurdle in the effort to establish a permanent presence on the Moon. The transportation of materials needed for construction, life support systems, and habitat modules will require substantial planning and resources. Regular missions from Earth to the Moon will not only be costly, but also incredibly complicated, necessitating highly efficient supply chains and reliable transportation systems. To ease this burden, utilizing local resources such as lunar regolith will be vital. This approach, known as in situ resource utilization (ISRU), would reduce the dependency on Earth-based shipments and make the process of building a lunar base more sustainable. Infrastructure development is also key to the success of a lunar base. Power generation systems will need to be established, as well as reliable communication networks and transportation systems on the Moon's surface. Solar panels could serve as the primary power source during the lunar day, harnessing the abundant sunlight available. However, the moon's long nights, lasting about 14 Earth days, present a challenge in storing and managing energy. Efficient energy storage solutions, such as advanced batteries or other technologies, will be critical for providing continuous power during the dark phases of the lunar cycle. Communication systems must also be robust, ensuring that astronauts maintain reliable contact with mission control on Earth. This will be essential for both safety and access to crucial data, whether for scientific research or emergency procedures. All these challenges require innovative solutions, cutting-edge technology, and perhaps most importantly, international cooperation. The success of a permanent lunar base will not only benefit space exploration, but will also provide insights that could be applied to future missions to Mars and beyond. The experience and technologies developed in establishing a sustainable base on the moon could help pave the way for human exploration throughout the solar system. Speaking of exploration, the idea of harnessing the resources of asteroids represents one of the most exciting frontiers for the future of space exploration. Asteroids are rich in a variety of valuable materials, such as metals, water, and other volatile compounds, all of which can be used for a range of purposes in space. Mining these celestial bodies could drastically reduce the cost of launching materials from Earth, creating an entirely new paradigm in space resource utilization. One of the most important resources found in asteroids is water, which can be extracted and processed through a process known as electrolysis. Water can be split into hydrogen and oxygen, both of which are essential for sustaining human life. Hydrogen, in particular, holds promise as a fuel source. When combined with oxygen, it can be used to create rocket fuel, which is vital for long-duration space missions. Establishing refueling stations in low Earth orbit or at lunar bases could revolutionize space travel. By refueling spacecraft with water mined from asteroids, space missions could venture further into the solar system with fewer logistical challenges. This would reduce the reliance on Earth-based propellants, making long-distance travel more feasible and cost-effective. Asteroids are also abundant in valuable metals, such as platinum, nickel, and iron. These materials could be used not only to manufacture equipment and structures in space, but also to build advanced spacecraft. The ability to mine these resources directly in space would reduce the dependence on Earth for materials, lowering costs and streamlining space missions. To achieve this, advanced technologies for extracting and refining materials on asteroids will be essential. Innovations in robotics and autonomous systems will play a significant role in ensuring the safety, efficiency, and success of asteroid mining operations. Another exciting possibility in asteroid resource utilization is the potential to create building materials. By processing asteroid regolith, it may be possible to manufacture bricks or other construction materials for habitats and infrastructure. These materials could be used to support human settlements on the Moon, Mars, or even in orbital stations. This capability would significantly reduce the need to transport heavy materials from Earth, making it more feasible to create sustainable habitats in space. While the potential is great, challenges remain. Developing proven technologies for asteroid mining and processing is just the beginning. Safety, sustainability, and the legal and ethical implications of asteroid mining will need to be addressed, especially under international space treaties. As technology continues to advance, however, the idea of creating a resource-rich environment in space becomes more and more plausible, offering an exciting future for space exploration. Looking even further ahead, interstellar travel is one of the greatest challenges that humanity will face. Reaching distant star systems requires revolutionary propulsion technologies capable of traveling vast distances in a reasonable amount of time. Several concepts for interstellar travel have been proposed, each pushing the boundaries of our current understanding of science and technology. One such concept involves fusion propulsion systems, which harness the energy generated by nuclear fusion reactions, the same process that powers the sun. Fusion drives could provide vastly greater thrust and efficiency than traditional chemical rockets. One idea, known as Project Orion, involves detonating nuclear bombs behind a spacecraft to propel it forward, while other, more controlled methods, such as the direct fusion drive, could use helium-3 and deuterium to create thrust. However, achieving the necessary conditions for sustained nuclear fusion in a spacecraft remains one of the most formidable challenges of space exploration. Another concept under investigation is the use of light sails. These large reflective sails could be propelled by powerful lasers aimed at them from Earth or orbital stations. Initiatives like the Breakthrough Starshot project are already exploring the possibility of sending small, lightweight probes to nearby star systems, such as Alpha Centauri, at a significant fraction of the speed of light. While lasers could accelerate these probes to unprecedented speeds, challenges remain in building the infrastructure needed and ensuring that the sails can withstand the extreme energy involved. Antimatter propulsion stands out as one of the most theoretical yet potentially powerful technologies. Antimatter reactions produce energy far more efficiently than conventional fuels. When matter and antimatter collide, the resulting release of energy could propel a spacecraft at speeds approaching that of light, dramatically reducing travel times to other star systems. However, producing and storing antimatter remains an immense challenge. Creating even tiny amounts of antimatter requires vast amounts of energy, and containing it safely in spacecraft is a technological hurdle that has yet to be overcome. As we look to the future, the challenges are immense, but the potential rewards are even greater. The development of advanced propulsion systems, resource utilization technologies, and sustainable habitats could not only revolutionize space exploration, but also change the course of human history, potentially allowing humanity to explore and settle new worlds beyond Earth. The theoretical concept of the warp drive introduces an incredibly compelling vision of how humanity might one day travel between the stars. Rooted in the principles of general relativity, this concept proposes a way to bend or warp the fabric of space-time itself, allowing a spacecraft to essentially surf on a cosmic wave that enables it to exceed the speed of light. The key idea is that by manipulating space-time in this way, a spacecraft could traverse vast interstellar distances without breaking the fundamental laws of physics. Though the idea has captured the imagination of many, its practical implementation remains squarely within the realm of theoretical physics. The mathematics behind warp bubbles has been laid out, but the actual materials, energy sources, and technologies needed to bring such a dream into reality are still beyond our understanding. As we explore these various propulsion technologies, it becomes clear how immense the challenge is. But that challenge is not insurmountable, and the research we undertake now could lay the groundwork for a new era of space exploration. At the same time, this pursuit broadens our understanding of the universe and ignites curiosity in future generations about the infinite possibilities of the cosmos. The dream of interstellar travel is not limited to warp drives alone. Space elevators, an ambitious vision for future space transportation, represent another potential breakthrough. A space elevator is a structure designed to stretch from the surface of the Earth into space, providing an efficient and cost-effective means of transporting materials and people to orbit. This technology could reduce our reliance on traditional rocket systems, which are both expensive and resource-intensive. However, building such an elevator is far from straightforward. It requires overcoming enormous engineering, material science, and logistical challenges. At the heart of the space elevator concept lies the need for incredibly strong materials capable of withstanding the tremendous tensile forces generated by the tether. Current materials like steel or Kevlar are simply inadequate for the task, given their weight and relative lack of strength. Researchers are looking into more advanced substances like carbon nanotubes and graphene, which have exceptional strength-to-weight ratios. These materials could, in theory, allow us to build a cable long enough to reach geostationary orbit, approximately 36,000 kilometers above the Earth's surface. However, developing these materials to a point where they are both reliable and affordable is still a work in progress, and many challenges remain in scaling up production methods. Once the materials issue is addressed, the next hurdle is the design of the space elevator itself. The tether would need to be anchored to a stable location on Earth, preferably near the equator, to minimize the impact of Earth's rotation. An elevator climber, which would function similarly to a lift, would ascend and descend along the tether. This climber would require a robust propulsion system to reach such extreme altitudes, possibly relying on energy beams transmitted via lasers or advanced systems like magnetic levitation. However, maintaining a space elevator involves more than just building it. Given the vast distances it would span, the tether would be vulnerable to micrometeoroid impacts, space debris, and even the harsh conditions of the Earth's atmosphere. To ensure the elevator's structural integrity, continuous monitoring and maintenance would be necessary. Automated systems powered by artificial intelligence could be deployed to constantly assess the condition of the tether, performing preventive maintenance and reducing downtime. Regular inspections and rapid response systems would be crucial in minimizing potential damage from space hazards. Despite these formidable challenges, the space elevator remains an inspiring symbol of the future of space exploration. The technical and engineering hurdles are immense, but as research progresses in materials science and structural engineering, the dream of a space elevator draws closer to reality. If realized, it could revolutionize humanity's access to space, changing the way we explore the universe and making interplanetary travel and even interstellar exploration far more feasible. The potential benefits of artificial gravity in space colonization offer yet another exciting frontier. Long-duration space travel and habitation present significant health risks for astronauts and colonists, primarily due to the effects of prolonged exposure to microgravity. Without the constant force of gravity, the human body undergoes a range of adverse changes, including muscle atrophy, bone density loss, and cardiovascular issues. To mitigate these effects, the introduction of artificial gravity through rotating habitats or centrifuge systems could create environments that mimic Earth's gravitational pull, helping astronauts maintain physical health during extended missions. One of the most important applications of artificial gravity is in preventing the loss of muscle and bone mass, which occurs when the body is deprived of gravity. In rotating habitats, centrifugal force could simulate the effects of gravity, helping to preserve astronaut health and enabling extended missions to distant planets like Mars, the Moon, or beyond. This simulated gravity would make it possible for humans to live in space for much longer periods, reducing the risks of long-term space travel. Moreover, the presence of artificial gravity could make everyday tasks on space missions much more manageable. In a microgravity environment, simple actions like eating, cooking, and sleeping become far more difficult due to the absence of gravitational forces. With artificial gravity, astronauts would be able to perform these tasks more easily, using familiar Earth-based appliances and furniture. This would not only improve the quality of life on long missions, but would also make space habitats feel more like home, alleviating the psychological stress often associated with the isolation of space. Artificial gravity could also have a profound impact on agriculture in space colonization. Growing crops in microgravity poses several unique challenges, such as the distribution of water and the development of root systems. Artificial gravity could help create conditions more similar to Earth's gravity, allowing crops to grow in a way that is more conducive to their natural development. This would be crucial for sustaining long-term space colonies, as it would reduce the dependency on Earth for food supply. Being able to cultivate food in space would allow colonies to become more self-sufficient, a vital aspect of ensuring their survival over extended periods. These concepts, the warp drive, space elevators, and artificial gravity, are all part of a larger vision for the future of space exploration and colonization. Each represents a monumental challenge, yet they also offer the potential for groundbreaking advancements that could change the course of humanity's history. As we push the boundaries of physics, engineering, and material science, we move closer to unlocking the mysteries of the universe and establishing a human presence in the stars. While these ideas may seem distant, the research and innovations of today lay the foundation for the spacefaring civilizations of tomorrow. The journey to the stars may one day be closer than we think. Artificial gravity holds the potential to revolutionize space exploration and human life in space. As space missions become more advanced, researchers have identified the importance of simulating Earth-like conditions in space, one of the most crucial being gravity. In space, where microgravity prevails, The absence of gravity can significantly impact both biological and material systems, altering how living organisms and materials behave. By introducing artificial gravity, we could recreate some of the critical physical forces present on Earth, which would enhance the quality and scope of space-based experiments. A controlled environment where gravity is simulated could allow scientists to explore a broader spectrum of phenomena, from biological processes such as cellular growth and human health to the behavior of new materials and advanced technology. By replicating Earth's gravitational forces, artificial gravity could improve the accuracy and reliability of experiments, leading to breakthroughs in fields like medicine, engineering, and environmental science. This could, in turn, accelerate the development of life-saving technologies and materials with profound implications not only for space colonization, but also for improving life here on Earth. As humanity looks toward the possibility of space colonization, whether on the Moon, Mars, or beyond, artificial gravity may be one of the key enablers of successful habitation. Human health and daily living in space are inextricably linked to the presence of gravity. Without it, astronauts face a multitude of health risks, including bone density loss, muscle atrophy, and fluid shifts. By implementing artificial gravity, astronauts could experience a more Earth-like environment, where their bodies would be better able to function for extended periods, potentially allowing for longer missions and even permanent settlements. Artificial gravity would also support critical activities such as agriculture, an essential element for long-term space habitation. Plants need gravity to grow in a way that mimics the natural processes of nutrient uptake, root growth, and the transport of water and nutrients. In a microgravity environment, plants struggle to thrive, making it challenging to develop sustainable food sources in space. By simulating gravity, it would be possible to cultivate crops in a way that supports human nutrition, reducing reliance on resupply missions from Earth. Beyond the physical challenges of space colonization, another significant obstacle is the protection of astronauts from cosmic radiation. As missions venture beyond low Earth orbit, LEO, such as trips to Mars or asteroids, cosmic radiation becomes an increasingly critical concern. Cosmic radiation, composed of high-energy particles like protons and heavy ions, can penetrate spacecraft and the human body, posing severe risks such as cancer, neurological damage, and other radiation-related health issues. Long-duration missions require innovative solutions to safeguard astronauts from this invisible threat. One of the most promising strategies for addressing cosmic radiation is the use of shielding materials. High-density materials, such as lead or specialized polymers, can absorb or deflect radiation, offering some degree of protection. However, a more efficient approach might lie in utilizing resources available in space itself. In situ resource utilization, ISRU, allows spacecraft to gather materials like lunar regolith or Martian soil, using them to create protective shielding. This method not only enhances radiation protection, but also reduces the need to transport heavy materials from Earth, making it a more sustainable solution. In addition to passive shielding, research into advanced materials is underway. Polyethylene and hydrogen-rich compounds, for example, have shown great potential in reducing radiation exposure. These materials, known for their ability to absorb cosmic radiation, could be incorporated into spacecraft design, offering an extra layer of defense against radiation. An even more innovative approach to radiation protection could involve the creation of designated radiation bunkers within spacecraft. These specialized areas, reinforced with heavy shielding, could serve as safe havens for astronauts during solar flares or periods of intense cosmic radiation. Equipped with life support systems, these bunkers would allow crew members to take refuge during heightened radiation events, ensuring their safety during the most dangerous phases of a mission. To further enhance safety, spacecraft could be outfitted with continuous radiation monitoring systems that provide real-time data on radiation levels. This would enable astronauts to make informed decisions about when to seek shelter and when it is safe to resume activities. In addition, active radiation mitigation methods are being explored, such as using magnetic or electric fields to create a protective barrier that deflects high-energy particles. Though still in the early stages of development, these active methods could complement passive shielding and provide astronauts with an additional layer of protection. Mission planning will also play a critical role in minimizing radiation risks. By carefully considering the timing of solar events and designing missions to avoid periods of intense solar activity, space agencies can reduce astronauts' exposure to harmful radiation. Monitoring solar weather and adjusting mission operations accordingly will be key to ensuring astronaut safety throughout their journey. Addressing the challenge of cosmic radiation requires a multifaceted approach, combining advanced materials, spacecraft design, active mitigation techniques, and strategic mission planning. As our understanding of cosmic radiation continues to evolve, collaborative research efforts between scientists, engineers, and space agencies will be crucial to developing effective protection strategies and ensuring the safety and well-being of astronauts on long-duration space missions. Artificial intelligence, AI, is another critical technology poised to transform space exploration. As space missions become increasingly complex, AI can significantly enhance our ability to execute them efficiently and effectively. From data analysis to operational automation, AI can support both human and robotic systems in working seamlessly together, improving decision-making and optimizing mission performance. One of the most impactful applications of AI in space exploration is its ability to analyze vast amounts of data generated during missions. Space missions produce an enormous quantity of data from telescopes, satellites, and planetary landers, among other sources. AI algorithms can process this data quickly and accurately, identifying patterns and anomalies that might otherwise go unnoticed. For example, in the search for exoplanets, AI can sift through vast data sets to identify potential signals of planetary bodies orbiting distant stars, accelerating the discovery process. AI can also enhance the autonomy of spacecraft and rovers, especially as missions venture farther from Earth. The communication delay between Earth and distant spacecraft can hinder real-time decision-making, making it challenging to adjust operations or make critical decisions on the fly. With AI-powered systems, spacecraft can autonomously adjust their trajectories, perform scientific experiments, and navigate uncharted terrain without waiting for instructions from mission control. This autonomy is especially vital in environments like Mars or asteroids, where quick responses to dynamic conditions are often necessary. In addition, AI can optimize mission planning and resource management, ensuring that spacecraft operate efficiently and safely. AI systems can calculate optimal trajectories, manage fuel consumption, and regulate life support systems, helping to prevent costly delays or mission failures. By predicting potential system failures before they occur, AI can also contribute to proactive maintenance, ensuring spacecraft remain operational for the duration of long missions. Another area where AI will play a crucial role is in human-robot collaboration in space habitats. As astronauts live and work in space, AI can assist with day-to-day tasks such as scientific experiments, maintenance, and health monitoring. With its ability to analyze data in real time, AI can provide astronauts with valuable insights into their health and the status of onboard systems, allowing them to focus on the more complex aspects of their missions. The integration of AI into space exploration will undoubtedly revolutionize the way we explore and inhabit space. With its ability to automate routine tasks, enhance data analysis, and support human decision-making, AI will become an indispensable tool in the quest to understand and explore the cosmos. The future of space exploration is not just about reaching new destinations. It's about using the power of AI to ensure that those missions are safer, more efficient, and more successful. In the near future, robotic assistants equipped with advanced artificial intelligence, AI, will become an integral part of space exploration. These robotic systems will be capable of performing a variety of routine tasks, from managing daily chores to monitoring the health of astronauts, ensuring that all living conditions aboard spacecraft and habitats remain optimal. This will allow human crew members to focus on more complex and creative endeavors, such as solving problems and tackling challenges that demand human ingenuity. Looking ahead, the integration of AI into space exploration promises to open new frontiers of possibility. By enhancing data analysis capabilities, AI will enable more efficient, autonomous operations, revolutionizing mission planning and fostering more effective collaboration between humans and robots. With these advancements, AI will become an essential partner in humanity's quest to explore not just our solar system, but eventually, the vast expanse of space beyond. As these technologies evolve, they will lead to a new era of space exploration, one characterized by streamlined operations, rapid discoveries, and the potential to venture farther into the cosmos than ever before. When it comes to building large-scale habitats in space, the challenges are immense. The unique conditions of the extraterrestrial environment require innovative and forward-thinking approaches. Whether the goal is to establish colonies on the Moon, Mars, or in orbit around Earth, a wide range of strategies can be employed to create safe, functional, and sustainable living conditions for astronauts and future space pioneers. One of the most promising approaches to habitat construction in space is the concept of in situ resource utilization, ISRU. This strategy involves using local resources, such as lunar regolith or Martian soil, to create building materials on site rather than relying on costly and logistically complicated shipments of materials from Earth. For instance, regolith could be processed into bricks or other structural components, drastically reducing the weight and cost of payloads launched from Earth. Current research in 3D printing technology also shows great promise, allowing complex structures to be built using these locally sourced materials. Another key strategy involves modular habitat designs. This approach centers on developing prefabricated modules on Earth that can be assembled and customized in space. These modules, once launched, can be connected and rearranged to form a larger habitat, providing flexibility in both design and function. Over time, habitats can be expanded, rearranged, or adapted to meet the changing needs of their inhabitants. Such modular systems could include living quarters, laboratories, greenhouses, and recreational facilities, creating a well-rounded and comprehensive living environment for astronauts. But constructing space habitats is not just about building structures, it's also about safeguarding human life. Space is a hostile environment, and habitats must be designed to protect inhabitants from the dangers posed by cosmic radiation and micrometeoroid impacts. Various shielding techniques are being explored, such as using thick walls made of advanced protective materials, or even burying habitats underground or covering them with local soil. These strategies can significantly reduce the risks posed by space's harmful radiation and debris. Furthermore, maintaining a stable atmosphere and temperature inside the habitat is crucial to the health and comfort of its residents. Closed-loop life support systems, which recycle air, water, and waste, will be vital for ensuring long-term sustainability, reducing reliance on resupplies from Earth. Energy is another critical consideration in habitat design. Reliable power sources are essential, particularly in environments where conventional energy systems might not function efficiently. Solar panels are a commonly proposed solution for generating electricity, though energy storage systems must be developed to ensure a continuous power supply during periods of darkness, such as the long lunar night. Additionally, nuclear power systems may play a role in providing a stable and continuous energy source for habitats, ensuring that astronauts can live and work in space for extended periods without worrying about energy shortages. Ultimately, the construction of large-scale habitats in space involves a multifaceted approach that combines the use of local resources, flexible modular designs, protective shielding, and reliable energy systems. These efforts will require collaboration across governments, private aerospace companies, and international partners. By working together, humanity will overcome the formidable challenges of extraterrestrial construction, paving the way for sustainable living environments as we venture further into the cosmos. As humanity looks to the future of space exploration, long-term human survival in space presents several significant challenges that must be addressed to ensure the health and safety of astronauts during extended missions, such as those to Mars or for the establishment of permanent colonies on the Moon. These challenges are multifaceted, spanning the physiological, psychological, and logistical domains, and they highlight the complexities of sustaining human life beyond Earth's protective atmosphere. One of the most pressing concerns is the impact of microgravity on the human body. In the weightless environment of space, Astronauts are no longer subjected to the constant force of gravity, which leads to a range of health issues. Prolonged exposure to microgravity can result in muscle atrophy, bone density loss, and changes in cardiovascular function. Without the resistance provided by gravity, astronauts' muscles weaken, and their bones can lose up to 1 to 2% of their mass per month. To counteract these effects, astronauts will need specialized exercise regimens that simulate gravitational forces, along with careful attention to nutrition and physical health. Another major challenge is the exposure to cosmic radiation, which poses a significant risk to astronaut health. Unlike Earth, where the atmosphere and magnetic field provide protection, space travelers are directly exposed to galactic cosmic rays and solar particle events. These high-energy particles can increase the risk of cancer, acute radiation sickness, and even long-term damage to the nervous system. Effective radiation shielding must be integrated into the design of space habitats, and strategies will need to be developed for shielding astronauts during periods of solar activity, such as by using safe regions of the spacecraft or reinforced bunkers. The psychological challenges of long-duration space travel are equally daunting. Isolation, confinement, and the stresses of living in a small, enclosed space for extended periods can lead to mental health issues such as anxiety, depression, and interpersonal conflicts. The lack of natural environments and social structures can exacerbate these challenges, making it essential to develop strategies for crew cohesion and mental health support. Regular psychological assessments, recreational activities, and opportunities for personal space will be critical in ensuring the well-being of astronauts as they endure long missions in the isolation of space. In the end, overcoming these challenges will require careful planning, innovative solutions, and ongoing research. As we continue to push the boundaries of space exploration, the collaboration of scientists, engineers, medical professionals, and psychologists will be crucial to ensuring that humanity can thrive in the harsh and unfamiliar environments of outer space. Only through these collective efforts can we hope to make the dream of space colonization a reality and ensure the survival of the human species as we venture beyond our home planet. The sustainable presence of humans in space requires overcoming a host of challenges, particularly in the realm of resource management. Life support systems, which include ensuring a reliable supply of water and oxygen, along with efficient waste recycling, are critical components that must be developed to operate effectively for extended missions. These systems will need to be robust enough to function autonomously, ensuring that astronauts can survive and thrive in space for prolonged periods without the constant need for resupply missions from Earth. One promising solution to reduce dependency on Earth-based resupply involves the utilization of local resources on planetary bodies. Propellant production, for example, can be achieved by using in-situ resource utilization, ISRU techniques, which extract and process raw materials directly from planetary surfaces. This approach significantly diminishes the logistical burden of sending fuel from Earth, thus allowing for more efficient exploration and longer missions, particularly on destinations such as Mars and the Moon. Ensuring the availability of food for astronaut extended missions is another crucial aspect of space sustainability. Careful planning is required to ensure food can be preserved, stored, and replenished over long durations. Advances in food preservation technology, along with potential breakthroughs in space-based agriculture, may pave the way for growing crops in space, reducing the need to rely entirely on prepackaged supplies. This would not only help meet nutritional needs, but also provide psychological benefits by allowing astronauts to engage in meaningful tasks like gardening or farming during their mission. Achieving long-term survival in space goes beyond the physical challenges of life support and sustenance. The psychological well-being of astronauts is equally important. The isolation, confinement, and harsh environment of space can take a toll on mental health, making it essential to develop strategies for psychological support. These strategies may include creating space habitats that mimic Earth-like environments, providing virtual connections with loved ones, and ensuring that astronauts have sufficient recreational activities to maintain morale. Additionally, logistical support systems will need to be carefully designed to support astronauts on missions that may last years, especially if humanity aims to establish a permanent presence on other planets or moons. Continued research and innovation will be vital for developing countermeasures to the many risks astronauts face, such as radiation exposure and muscle atrophy. These innovations will not only support the health and well-being of astronauts, but also ensure that they have the necessary resources and systems to live and work in space for extended periods. As humanity pushes further into the cosmos, addressing these challenges will be vital to the success of future space missions, as well as any potential colonization efforts. The ability to live and work in space sustainably will be the cornerstone of humanity's efforts to explore and inhabit other worlds. Gravitational assists, also known as gravity slingshot maneuvers, are one of the most powerful techniques employed in space exploration to propel spacecraft on their journeys through the solar system and beyond. This technique uses the gravitational pull of a planet to increase the spacecraft's velocity without expending additional fuel. By flying close to a planet, a spacecraft can gain speed by stealing a bit of the planet's momentum, altering its trajectory, and enabling it to travel much farther with less energy. The principle behind gravitational assists is rooted in the conservation of momentum and energy. As a spacecraft approaches a planet, it falls into the planet's gravitational field and accelerates. Instead of landing, the spacecraft swings around the planet, gaining velocity as it escapes the gravitational pull. By carefully timing the spacecraft's approach and trajectory, mission planners can maximize the amount of energy transferred during the maneuver, enabling the spacecraft to reach distant destinations that would otherwise require massive amounts of fuel. This technique has been used to great effect in several landmark space missions. The Voyager spacecraft, for example, used gravitational assists from multiple planets, including Jupiter and Saturn, to achieve incredible speeds on their journey toward the outer planets and even into interstellar space. Through meticulous planning of timing and trajectory, the Voyager missions were able to reach their destinations much more efficiently than if they had relied solely on conventional propulsion. In addition to boosting speed, gravitational assists also provide a means for trajectory adjustments. By planning the spacecraft's approach to specific planets, mission designers can alter the craft's path to align with various celestial targets, such as asteroids or other planets. This flexibility makes it possible to explore multiple destinations in a single mission, thus maximizing the scientific return on investment. It also allows for more ambitious mission objectives, reducing the need for additional fuel or multiple launches. Moreover, gravitational assists can extend mission lifetimes by reducing the amount of fuel required for propulsion. Spacecraft can travel faster and farther with less fuel, enabling longer missions and the exploration of more distant regions of space. As spacecraft rely on planetary flybys rather than continuous thrust, mission planners can extend the length of missions, making them more feasible and cost-effective. By utilizing the gravity fields of multiple planets, future space missions might be able to visit a variety of destinations, making groundbreaking scientific discoveries without the need for excessive fuel supplies. In short, gravitational assists have become a fundamental maneuver in modern space exploration. By harnessing the gravitational energy of planets, spacecraft can achieve higher speeds, alter their trajectories, and conserve fuel. This approach has enabled a range of ambitious missions, including those that have taken humanity's exploration efforts beyond the solar system. As spacecraft technology continues to advance, gravitational assists will remain an indispensable tool for navigating the vast expanse of space. In the future of space travel, nuclear propulsion technologies could revolutionize the way humanity explores the cosmos, offering significant advantages over traditional chemical propulsion systems. Nuclear propulsion, particularly in its two main forms, nuclear thermal propulsion and nuclear electric propulsion, could drastically reduce travel times and increase the range of space missions, enabling humanity to explore distant planets and moons with greater efficiency and speed. Nuclear thermal propulsion operates by using a nuclear reactor to heat a propellant, such as hydrogen, which is then expelled through a rocket nozzle, generating thrust. This method offers much higher specific impulse than chemical rockets, meaning that more thrust is generated per unit of fuel. As a result, nuclear thermal propulsion could drastically shorten travel times to distant destinations, such as Mars, potentially cutting the journey from several months to just a few weeks. This reduction in travel time would minimize the risks posed by long-term space travel, including radiation exposure and the physical effects of prolonged weightlessness on astronauts' health. On the other hand, nuclear electric propulsion uses a nuclear reactor to generate electricity, which powers electric thrusters such as ion or Hall effect engines. Unlike nuclear thermal propulsion, which produces immediate thrust, nuclear electric propulsion delivers continuous low-thrust acceleration over an extended period. This efficiency makes it ideal for long-duration missions targeting deep space destinations, such as the outer planets or asteroids. With this type of propulsion, spacecraft can slowly build up significant speeds over time without needing to carry large quantities of fuel. Both types of nuclear propulsion technologies offer distinct advantages. Nuclear thermal propulsion excels in providing quick bursts of thrust for missions to relatively nearby destinations such as Mars, while nuclear electric propulsion is well suited for deep space missions that require consistent acceleration over many years. Together, these propulsion methods could open up new possibilities for scientific exploration, enabling multiple destinations to be reached within a single mission. Faster missions also mean that more scientific objectives can be included, enhancing the overall scientific return of any given mission. In conclusion, nuclear propulsion presents a promising frontier for space travel, offering higher efficiency, reduced travel times, and the potential to explore farther reaches of the solar system. As these technologies continue to evolve, they will play a pivotal role in humanity's journey to the stars, enabling us to push the boundaries of space exploration in ways previously thought impossible. Moreover, nuclear propulsion systems have the potential to revolutionize space exploration, opening up pathways for far-reaching and ambitious missions. These could include human expeditions to Mars, the establishment of permanent outposts on the Moon, or even the exploration of the outer planets. However, before nuclear propulsion can become a widespread and reliable method for interplanetary travel, several significant hurdles need to be overcome. Key challenges include designing nuclear reactors that are safe and reliable for use in space, addressing public concerns and regulatory restrictions related to nuclear materials, and securing substantial investments for the necessary research and development. Despite these obstacles, nuclear propulsion represents a compelling avenue for advancing the efficiency and capabilities of future space missions, offering the promise of faster, more powerful propulsion systems that could support humanity's ambitious quest to explore the solar system and beyond. As research progresses and technology evolves, nuclear propulsion may become a cornerstone of humanity's ability to undertake deep space missions, providing the means to travel faster and farther than current propulsion systems allow. By harnessing the power of nuclear energy, we could unlock new possibilities for missions that were once thought to be out of reach, potentially reshaping the future of space exploration. With the right technological breakthroughs and international collaboration, nuclear propulsion could offer the key to reaching the distant frontiers of our solar system and beyond. At the cutting edge of astronomical research, space telescopes like the James Webb Space Telescope, JWST, are dramatically expanding the scope of our understanding of the universe. Designed to observe the cosmos in infrared wavelengths, the JWST fills gaps left by its predecessor, the Hubble Space Telescope, which primarily observes in optical and ultraviolet light. By operating in the infrared spectrum, JWST has the ability to peer through dense clouds of dust that often obscure celestial objects, allowing scientists to uncover phenomena that were previously hidden from view. This unique capability has already led to groundbreaking discoveries in the realms of star and planetary system formation. One of the key advantages of infrared observations is the ability to detect cooler objects that may be invisible in optical light. This opens up new avenues for studying regions of space where stars and planetary systems are born, dense clouds of gas and dust that block visible light. Through the observation of infrared wavelengths, JWST can capture detailed images and data from young stellar nurseries, providing critical insights into the processes that drive star formation and the early stages of planetary system development. In addition to its stellar capabilities, JWST is also revolutionizing our understanding of distant galaxies. By observing light from galaxies that has traveled vast distances across the cosmos, the telescope can study how these galaxies have evolved over billions of years. As light from these far-off galaxies stretches, or redshifts, its wavelengths shift from visible to infrared. JWST is uniquely equipped to detect this redshifted light, enabling astronomers to look back in time just a few 100 million years after the Big Bang. This provides a window into the early universe, offering clues about the formation of galaxies, stars, and other cosmic structures during the universe's infancy. Moreover, the advanced technology of JWST allows for detailed studies of exoplanets and their atmospheres. By analyzing the light passing through or reflecting off these distant worlds, astronomers can identify chemical signatures that may indicate the presence of water, carbon dioxide, methane, or even potential biosignatures, key components in the search for extraterrestrial life. This research expands our knowledge of the diverse environments in which planets exist and helps to identify which exoplanets might harbor conditions conducive to life. JWST's high-resolution imaging capabilities also enable it to map and study features within our own solar system, including the atmospheres of planets and the composition of distant comets. By studying these smaller-scale phenomena, scientists can gain deeper insights into the dynamic processes that govern planetary atmospheres and the evolution of celestial bodies within our own solar neighborhood. Through these observations, JWST is paving the way for future missions to better understand our solar system's formation and its continued evolution. Space telescopes like the James Webb Space Telescope are not just pushing the limits of what we can observe, they are opening new frontiers in our understanding of the universe. By allowing us to observe celestial phenomena previously hidden by dust, and by offering unprecedented insights into the formation of stars, galaxies, and planetary systems, JWST is set to shape the course of astronomical research for decades to come. The groundbreaking discoveries made by JWST are bound to reshape our conception of the cosmos and ignite new scientific endeavors in the years ahead. In situ resource utilization, ISRU, is a game-changing concept that focuses on the ability to harness and utilize local resources found on planets or moons. This approach could significantly reduce the need for transporting materials from Earth, offering a sustainable solution for long-term space exploration and habitation. For NASA's Artemis program on the Moon and future missions to Mars, ISRU is critical for establishing permanent human presence beyond our planet. Technologies are currently being developed to extract and process essential resources such as water, oxygen, and construction materials directly from local environments. Water is one of the most critical resources for ISRU, as it is essential for both life support and rocket fuel. On the Moon, frozen water is believed to be present in permanently shadowed craters, while Mars harbors significant quantities of subsurface ice. Extracting water from these sources is a primary focus of current research. Techniques such as drilling into icy layers followed by melting and purifying the water are being explored. Advanced sensors and surface rovers are also being developed to identify potential ice deposits and assess their composition, guiding future extraction efforts. Oxygen is another vital resource that ISRU aims to produce on Mars. The Martian atmosphere is composed of about 95% carbon dioxide, which provides a potential source of oxygen. The Mars Oxygen ISRU experiment, MOXIE, which is part of NASA's Perseverance rover mission, demonstrates the feasibility of this concept. MOXIE uses electrochemical processes to extract oxygen from carbon dioxide in the Martian atmosphere, offering valuable insights into the viability of large-scale oxygen production for future human missions to Mars. Another promising area of ISRU development is the use of local materials for construction. Lunar regolith and Martian soil can be processed to create building materials such as bricks or concrete-like substances, which can be used to construct habitats and other necessary infrastructure. Techniques such as sintering or 3D printing are being explored to allow astronauts to build structures on site without relying on supplies from Earth. This not only reduces the cost and complexity of transportation, but also supports the creation of sustainable habitats that will be crucial for long-term stays on the Moon or Mars. The ability to use local resources to support human exploration and habitation beyond Earth is key to the success of future space missions. As ISRU technologies evolve, they will enable humanity to establish self-sustaining colonies on the Moon, Mars, and potentially other celestial bodies. These advancements will reduce reliance on Earth, making it possible to sustain human life in space for extended periods of time and facilitating the development of permanent outposts in the solar system. Through innovative research and the implementation of cutting-edge technologies, ISRU holds the promise of making long-term space exploration a reality. Efforts to develop technologies that enable the production of fuel and other essential consumables from local resources are gaining momentum. One of the key areas of exploration involves conversion processes, such as extracting hydrogen or methane from Martian soil or ice. These methods, when combined with atmospheric extraction technologies, have the potential to produce propellants for return missions or further exploration. By utilizing in-situ resources, missions can significantly reduce their reliance on Earth-based supplies, thus enhancing the overall sustainability of space exploration. This growing field of research is foundational for the future of human exploration and potential habitation on other planets. Current efforts focus on extracting water, producing oxygen, creating building materials, and manufacturing fuel, all from resources found locally on planets like Mars or the Moon. The continued advancement of these technologies is critical to establishing a viable, long-term human presence on planets beyond Earth. As these methods demonstrate their effectiveness in space environments, they will dramatically increase the feasibility of sustained human exploration and habitation, paving the way for missions that extend not just to the Moon or Mars, but to the farthest reaches of our solar system and beyond. Among the most promising advancements in space communication is the use of lasers for interstellar communication. Laser communication, or optical communication, leverages the unique properties of laser light, including its ability to focus into narrow beams that can travel vast distances with minimal dispersion. This capability is crucial for overcoming one of the most significant challenges in interstellar communication: the sheer distance between stars. Unlike traditional radio waves, which disperse and degrade as they travel, laser beams can remain tightly focused, significantly improving the efficiency of long-distance transmission. One of the standout advantages of laser communication is its higher data transmission rate. Unlike radio waves, which have limited bandwidth, lasers can carry a vastly larger volume of information. This increased data capacity allows for the transmission of richer, more complex data, including high-resolution images and even video streams. This is vital for missions to distant star systems, where communication with spacecraft or probes would otherwise be severely limited by slower transmission speeds. For example, initiatives like the Breakthrough Starshot program aim to send tiny, light-powered spacecraft to the nearest star systems, such as Alpha Centauri. Laser communication could be the key to sending and receiving high-speed transmissions from these far-flung missions, enabling the return of invaluable scientific data. Additionally, lasers offer exceptional directionality. A laser beam can be tightly focused, reducing the risk of signal loss over long distances. In contrast, radio waves tend to spread out over time, causing the signal to weaken as it travels, which complicates long-distance communication. This precision also holds significant potential for enhancing the likelihood of detecting signals from distant civilizations. The ability to concentrate a laser beam means that even faint signals from extraterrestrial sources could be detected more efficiently, increasing the chances of successful communication across interstellar distances. However, using lasers for interstellar communication is not without its challenges. One of the major hurdles is the need for extreme precision in aiming and aligning the laser systems, especially given the vast distances between stars. This requires highly sophisticated tracking systems capable of adjusting for the relative motion of both the emitter and the receiver. Atmospheric interference is another factor to consider, particularly for ground-based laser systems, which can be affected by factors like clouds or turbulence. While space-based systems would face fewer atmospheric obstacles, the challenges of long-distance laser communication would remain. Additionally, advanced technology for encoding and decoding messages is critical for ensuring that communications are successful. Effective modulation techniques are necessary to convert data into a form suitable for laser transmission and to guarantee that the message is accurately received. This involves not just transmitting the laser signal, but also developing protocols to interpret the incoming data correctly. As we continue to refine our laser technologies, the feasibility of using lasers for interstellar communication becomes more realistic. This could open up new avenues for scientific discovery, whether through sending messages to distant civilizations or communicating with probes exploring the farthest reaches of our galaxy. Recent advancements in spacesuit technology are also playing a pivotal role in the future of space exploration. These innovations aim to improve functionality, safety, and comfort for astronauts as they prepare for missions to the Moon, Mars, and beyond. One of the most notable developments is the NASA Artemis spacesuit, officially known as the Exploration Extravehicular Mobility Unit, XEMU. These suits are designed specifically for lunar exploration, allowing astronauts to perform surface operations with greater mobility and agility than ever before. The XEMU suits represent a significant leap forward in terms of mobility. Unlike previous suit models, which were often restrictive and cumbersome, the new design incorporates articulated joints and sleeves, allowing astronauts to move with more freedom. This increased range of motion is crucial for tasks such as collecting samples, operating tools, and conducting scientific experiments on the Moon's surface. The suits also feature a flexible torso system that enables astronauts to bend, twist, and move with ease, all while maintaining essential life support functions. Equally important are the advancements in the life support systems integrated into the XEMU suits. These spacesuits are equipped with advanced ventilation and thermal control systems that regulate temperature and manage moisture, ensuring that astronauts remain comfortable despite the extreme conditions on the lunar surface. With temperatures ranging from -250 degrees Fahrenheit at night to over 200 degrees Fahrenheit during the day, effective temperature control is essential. The new suits utilize innovative materials and technologies that help manage heat more effectively, ensuring astronauts can stay cool in the heat of the day and warm during the frigid lunar nights. As we move forward with these technological innovations, the future of space exploration appears more promising than ever. Advances in fuel production from local resources, interstellar laser communication, and spacesuit design are all integral components of humanity's drive to expand beyond Earth. With each step forward, we bring ourselves closer to a future where the Moon, Mars, and the stars themselves are within reach. The journey has just begun, and the possibilities for discovery and human habitation in space are limitless. Advancements in spacesuit technology have been progressively integrated with state-of-the-art communication systems, marking a significant leap forward in astronaut safety and operational effectiveness. These upgraded systems are not merely an enhancement, but a necessity for the new age of space exploration, where astronauts are required to venture beyond Earth's atmosphere for extended periods. With these improved systems, astronauts can maintain uninterrupted contact with mission control and fellow crew members, even when conducting extravehicular activities, EVAs, such as spacewalks on the lunar surface. This seamless communication network ensures that astronauts have immediate access to vital guidance and support, especially when navigating the perilous environment of space. Whether it's troubleshooting a malfunction or receiving real-time instructions for complex tasks, these advancements ensure that astronauts are never alone in their mission. The communication systems have been meticulously designed to function with optimal efficiency, even in the challenging conditions of the lunar environment. Background noise, interference, and other disruptive factors are minimized, providing clear and reliable communication that enhances safety throughout these crucial operations. Furthermore, the emphasis on astronauty has been significantly enhanced in recent designs. The new spacesuits offer multi-layered protection against various hazards, including micrometeoroid impacts, dangerous levels of radiation, and the extreme temperature variations found in space. Innovations in material science have introduced specialized fabrics and composites, which contribute not only to the durability of the suits, but also their ability to withstand the harshest conditions. These materials provide astronauts with an extra layer of protection, ensuring that their well-being remains a top priority as they venture farther into the unknown. The latest spacesuits also feature a highly sophisticated helmet design, equipped with a wider visor and a state-of-the-art heads-up display, HUD technology. This system delivers crucial data to the astronaut while enhancing visual clarity, ensuring that they remain fully informed even in the midst of challenging activities. The visor also provides protection from harmful solar radiation, a critical feature for safeguarding astronauts on the lunar surface, where exposure to solar rays can be dangerously intense. With these innovations, the suits not only prioritize the health and safety of astronauts, but also ensure they have all the necessary tools for effective mission execution. Looking forward, the future of spacesuit technology is being shaped by the growing ambition to explore beyond the moon. There is a mounting interest in designing suits capable of supporting missions to Mars and other distant celestial bodies. The Martian environment presents a new set of challenges, including drastically lower gravity, unpredictable dust storms, and atmospheric pressure vastly different from Earth's. Researchers are working diligently to develop suits that can accommodate these unique challenges, ensuring that astronauts can perform tasks and survive in environments that are nothing short of hostile. This forward-thinking approach to spacesuit design reflects the broader commitment to future exploration. As humanity sets its sights on Mars and beyond, the technology required to support astronauts in these extreme conditions will continue to evolve. From mobility to life support functions, communication systems, and safety features, each advancement plays a pivotal role in ensuring that astronauts can operate effectively and safely in outer space. The integration of nanotechnology stands at the forefront of this revolution in space exploration, offering transformative solutions that could reshape the very nature of space missions. Nanotechnology, by manipulating matter on an atomic or molecular scale, has the potential to dramatically enhance materials, structures, and systems used in space exploration. The development of nanomaterials such as carbon nanotubes and graphene promises to produce lighter, stronger, and more resilient spacecraft and habitats. These materials can withstand the extreme conditions of space, including intense radiation, temperature fluctuations, and micrometeoroid impacts, making them ideal for future missions. Moreover, these advanced materials can reduce the overall cost of space missions by lowering the mass of spacecraft, making them more efficient and cost-effective to launch. Beyond structural improvements, nanotechnology also plays a critical role in energy management and storage. For instance, solar panels crafted with nanomaterials can convert sunlight into electricity with much higher efficiency than traditional systems. This development could enable spacecraft to generate greater power, ensuring that astronauts have the energy required to run life support systems, scientific instruments, and communication networks during long-duration missions. Advanced batteries, also enhanced with nanotechnology, could offer longer-lasting power supplies, reducing the need for frequent resupply missions from Earth. In addition to energy and materials, nanotechnology can revolutionize astronaut health monitoring. Nanosensors embedded in spacesuits could continuously monitor astronauts' vital signs, track radiation levels, and assess environmental conditions inside spacecraft. These sensors would provide real-time feedback, alerting astronauts in mission control to potential health risks or environmental hazards such as hazardous gas concentrations or equipment malfunctions. By facilitating early detection of problems, nanotechnology could significantly enhance astronaut safety during long-duration missions to distant worlds. Another vital application of nanotechnology in space exploration lies in the field of in-situ resource utilization, ISRU. As space missions venture farther from Earth, the need for sustainable practices becomes more pressing. Nanomaterials could optimize the extraction and processing of local resources, such as regolith lunar soil, to produce materials for construction, life support, and fuel. This would reduce the dependency on Earth-based supplies and increase the self-sufficiency of space missions, making future exploration more sustainable and cost-effective. Nanotechnology also promises to revolutionize propulsion systems. Concepts like solar sails, constructed from lightweight nanomaterials, could allow spacecraft to harness solar radiation for propulsion, providing a highly efficient means of traveling vast distances in space. This technology holds great potential for missions targeting distant planets, asteroids, or even interstellar space, offering a revolutionary approach to deep space exploration. In conclusion, the integration of nanotechnology into space exploration promises to unlock new capabilities and improve the sustainability of future missions. By advancing materials, energy systems, health monitoring, resource utilization, and propulsion, nanotechnology has the potential to shape the future of human space exploration, enabling us to reach farther and explore more efficiently. As research in this field progresses, these innovations will not only enhance our ability to explore the cosmos, but also pave the way for humanity to establish a permanent presence beyond Earth. In parallel, space-based solar power is emerging as a promising solution for harnessing renewable energy. Unlike terrestrial solar systems, which are affected by weather patterns and the day-night cycle, space-based solar power systems can operate continuously, 24 hours a day. These systems capture sunlight in space where there are no atmospheric disturbances and can transmit this energy back to Earth or use it for space-based applications. This continuous, reliable energy source could play a critical role in powering future space missions and even provide a sustainable energy solution for Earth's growing energy needs. As technology advances, the potential for space-based solar power to revolutionize both space exploration and global energy production becomes increasingly tangible. However, despite the promise of space-based solar power as SBSP, a range of formidable challenges and potential benefits accompany this pioneering concept. The very nature of the endeavor, harnessing solar energy from space, introduces unique complexities that require innovative solutions, careful planning, and significant investment. A major hurdle in realizing space-based solar power is the daunting challenge of deploying large-scale solar arrays and associated infrastructure into orbit. The process of launching and positioning these arrays is not only costly, but also highly intricate. Building the necessary technologies and developing cost-effective spacecraft capable of safely transporting these massive components to their destinations is crucial for the long-term feasibility of space solar systems. Additionally, once these solar arrays are placed in orbit, the need for detailed engineering and careful planning to ensure the systems operate reliably in space's harsh environment cannot be overstated. Whether the arrays are stationed in low Earth orbit or geostationary orbit, they must be able to withstand extreme conditions, including radiation, micrometeoroids, and temperature variations. Maintenance and longevity are also primary considerations to ensure the solar arrays remain functional over time. The next significant challenge lies in energy transmission. Solar energy collected in space would need to be converted into microwaves or laser beams for efficient transmission back to Earth. Developing the technology to beam this energy through space and into the atmosphere without significant loss or interference is a technical feat that demands innovative breakthroughs. Once the energy reaches the ground, it must be converted back into usable electricity. This step poses another set of technical and safety issues. For example, ground-based receivers designed to capture the transmitted energy must be constructed in a way that prevents harm to living organisms or damage to critical infrastructure. The design and implementation of these energy beaming and receiving systems would need to account for not only efficiency, but also safety, making them both a technological and regulatory challenge. Despite these challenges, the potential of space-based solar power is vast. One of the most compelling advantages is its ability to provide continuous energy generation, unaffected by the variations in weather or time of day that influence terrestrial solar power systems. Solar arrays in space receive uninterrupted sunlight, a key factor in ensuring a steady and reliable energy output. This capability could significantly improve the efficiency of energy production, far surpassing conventional solar panels on Earth, which are hindered by atmospheric interference. The uninterrupted nature of solar energy in space presents an opportunity for power generation on a scale never before possible. Furthermore, the integration of space-based solar power systems could have far-reaching implications for meeting global energy demands and advancing sustainability. By providing a constant renewable energy source, space-based solar power could reduce our reliance on fossil fuels, helping mitigate climate change and promote environmental sustainability. Such systems would not only contribute to Earth's energy grid, but could also bolster energy security and resilience, diversifying the global energy supply and ensuring a more robust infrastructure against energy crises. Beyond terrestrial applications, space-based solar power holds immense promise for supporting future space exploration missions. As human presence in space grows, with aspirations for lunar colonies, Mars missions, and beyond, the energy demands of space habitats, spacecraft, and scientific equipment will only increase. In this context, harnessing solar energy directly in space could provide a sustainable power source essential for the long-term viability of future colonies on the Moon or Mars. Solar power could facilitate a continuous, reliable energy supply, thereby supporting extended human presence on other celestial bodies without the logistical burden of transporting vast amounts of fuel or energy from Earth. While the challenges of space-based solar power, from the deployment to energy transmission and cost considerations, are substantial, the rewards of a continuous renewable energy source for both Earth and future space missions cannot be overstated. Ongoing research and development in this area are crucial to overcoming these obstacles and unlocking the transformative potential of space-based solar power. As advancements continue, space-based solar power could revolutionize the way we generate and consume energy, with profound implications for both our planet and the future of human space exploration. In parallel with the development of space-based solar power, 3D printing technologies are making waves in the field of space exploration, revolutionizing construction, manufacturing, and sustainability for long-duration missions. The unique challenges of space environments, including microgravity, limited resources, and the need for autonomous operations, are pushing the boundaries of additive manufacturing. 3D printing in space allows astronauts to produce tools, components, and even entire habitats directly on site, significantly reducing reliance on supplies shipped from Earth. A key adaptation of 3D printing for space is the development of specialized printers capable of operating in microgravity conditions. These printers must be able to utilize materials that are suited for the space environment, such as lunar regolith or Martian soil, which can be processed into feedstock for 3D printing. This innovative approach to utilizing local resources reduces the need to transport heavy construction materials from Earth, supporting the concept of in situ resource utilization, ISRU, a critical factor for future lunar and Martian colonies. By leveraging local resources, 3D printing can enable self-sufficiency in space, a critical feature for the sustainability of future space missions. The design of 3D printers for space must also address significant constraints in terms of size, weight, and functionality. Space missions operate under strict limitations regarding payload, meaning that equipment such as 3D printers must be compact, portable, and capable of functioning autonomously or remotely. To meet these needs, companies like Icon and Redwire Space are pioneering innovations in printer designs specifically engineered to handle the extreme conditions of space. These printers are built to function in microgravity, ensuring that the printing process remains stable, controlled, and precise, even in the absence of gravity. One of the most exciting applications of 3D printing in space is its ability to create complex geometries and customize parts on demand. This capability opens up a wide range of possibilities for astronauts, allowing them to manufacture replacement parts, tools, or even structural components as needed, instead of relying on extensive inventories stored on spacecraft. NASA has already demonstrated the feasibility of this technology aboard the International Space Station, ISS, where astronauts successfully 3D printed a variety of mechanical parts and tools during real spaceflight operations. These successful tests have shown that 3D printing is not only practical, but also a game changer for space exploration, enabling astronauts to respond to unforeseen challenges and produce critical resources without waiting for supplies from Earth. The intersection of space-based solar power and 3D printing is a fascinating one, with both technologies offering immense potential for the future of human space exploration. As we continue to push the boundaries of space travel, the integration of these technologies could play a pivotal role in ensuring that future missions are self-sustaining, efficient, and capable of meeting the growing energy and resource needs of astronauts in space. With continued innovation and investment, both space-based solar power and 3D printing technologies could become central pillars of humanity's presence in space, offering sustainable solutions for energy production and resource utilization in the cosmos. Advancements in bioprinting technologies are rapidly opening new possibilities in the realms of healthcare and space exploration. One of the most exciting potential applications lies in the creation of living tissues and even entire organ structures. In the context of space, where astronauts face significant health challenges during long-duration missions, this innovation could be revolutionary. Imagine a future where bioprinters could create tissues to heal injuries or replace damaged organs, allowing astronauts to maintain their health in environments far from Earth. Researchers are investigating bioinks, special materials capable of encapsulating living cells, which may make these groundbreaking applications a reality. These bioinks could enable the printing of functional biological materials, pushing the boundaries of space medicine and significantly enhancing the well-being of astronauts. In parallel, 3D printing technologies are transforming space exploration by addressing some of the most pressing challenges faced by astronauts: construction, manufacturing, and sustainability. 3D printing has the ability to use local resources such as regolith on the Moon or Mars to everything from tools to habitat components. By offering on-demand production, these technologies help reduce reliance on Earth-based supply chains, making missions more self-sufficient. As this technology continues to evolve, it could significantly enhance the efficiency of space missions, enabling astronauts to build, repair, and manufacture critical items without waiting for shipments from Earth. 3D printing's role in future space exploration and habitation is poised to expand. With the capability to manufacture necessary components on-site, this technology will be integral in overcoming the unique logistical and operational demands of living and working in space. As research progresses, 3D printing could become one of the cornerstones of sustainable space exploration, providing astronauts with the tools to not only survive, but thrive in the harsh, isolated environment of space. Swarm robotics, another transformative technology, promises to redefine how we approach tasks in space. Inspired by the collaborative behavior of natural swarms, such as those seen in insects and birds, this technology enables multiple robots to work together in harmony, each contributing to a larger mission. The scalability and flexibility of swarm robotics offer significant advantages over traditional single robot systems, particularly when exploring distant planets, moons, and asteroids. A swarm of small, autonomous robots can be deployed to perform a variety of tasks simultaneously. These could range from surveying terrain and conducting scientific experiments to building habitats or gathering resources. Each robot can work independently while still communicating and coordinating with others, ensuring efficient and comprehensive data collection. This capability is particularly valuable for large-scale planetary explorations or tasks requiring detailed surface mapping. For instance, swarms could be used to evaluate potential landing sites, assess resource availability, and analyze geological features, all in a fraction of the time it would take a single robot. The redundancy and resilience of swarm robotics is another compelling advantage. If one robot fails or encounters an obstacle, the remaining robots can continue the mission without disruption, ensuring that critical tasks are completed even when some systems fail. This is crucial in space, where repairs can be difficult or impossible. By deploying multiple robots, mission planners can rest assured that even in the face of unexpected challenges, the mission will stay on track. Swarm robotics also optimizes resource utilization and energy management. Each robot can be tailored to perform specific functions, ensuring that tasks are divided efficiently. For example, while some robots focus on gathering resources, others might assist with construction or data collection. This division of labor not only reduces the overall workload, but also ensures that energy, such as solar power collected during surface operations, is used effectively. As a result, missions can last longer and accomplish more with the available resources. In the context of construction and in situ resource utilization, swarm robotics offers exciting possibilities. A swarm of robots could be deployed to construct habitats, repair equipment, and even manufacture components using local materials. For example, lunar regolith could be collected and transformed into building materials, allowing astronauts to create structures far more efficiently than a single robot ever could. The cooperative nature of these robots also means they can adapt to changing conditions in real time, adjusting construction plans as needed based on environmental variables or evolving mission objectives. Beyond construction, swarm robotics holds tremendous potential for scientific research and exploration. With multiple robots equipped with a range of sensors and instruments, swarms can collect data from various locations simultaneously. This ability to gather diverse data sets in parallel makes it possible to conduct extensive surveys, atmospheric sampling, and geological assessments in much less time than would be possible with a single robot. The collaborative nature of swarm robotics allows researchers to study planetary environments more comprehensively, unlocking new insights into distant worlds. The future of swarm robotics in space is bright, with potential applications ranging from exploration and scientific discovery to the creation of sustainable habitats. As the technology continues to advance, swarm robotics could become an indispensable tool for missions to the Moon, Mars, and beyond, enabling more efficient, resilient, and comprehensive space exploration than ever before. Together with innovations like bioprinting and 3D printing, swarm robotics will be a key player in the next phase of human exploration in the solar system, helping to establish a permanent, self-sustaining human presence on other worlds.